Over the next 5 hours, we're going to cover object-oriented design patterns for software engineering interviews, all taught through real-world production scenarios. We'll start by covering OOP principles, then we'll move to solid principles, and then after that we'll be covering 14 creational, structure, and behavioral design patterns. All of them would also include examples from real-world production systems like payment processing, notification services, and order management. These are the skills that object-oriented interview rounds at companies like Google, Amazon, and other tech companies look for. So let's get started. Now here's exactly what we'll be covering in this course today. In the first section of this course, we'll spend an hour on object-oriented principles through the interview lens. In that, we'll cover encapsulation, abstraction, inheritance, and polymorphism with 3 production worked examples. That would include payment processing and notification dispatch. After that, we'll cover composition versus inheritance and abstract class versus interfaces problem, which are 2 of the very frequently tested trade-off questions in interviews. In the second section of this course, we'll spend an hour on solid principles for interviews. So as part of that, we'll cover all 5 solid principles with 5 production code examples showing clean design alongside the design violations like God classes, interview bloat, and tight coupling. Then as part of the third section of this course, we'll be spending 45 minutes on creational design patterns. So as part of that, we'll be covering factory method, abstract factory design pattern, builder pattern, and Singleton Pattern with 3 production code examples, including notification channel creation and user profile validation. After that, in the fourth section of this course, we'll spend 50 minutes on structural design patterns. So as part of that, we'll be covering adapter pattern, decorator pattern, facade pattern, and also proxy pattern. Alongside that, we'll also be covering 4 production examples in that section. So that will include third-party payment API integration, data stream processing, and database query caching. After that, in the fifth section of this course, we'll be spending 55 minutes on behavioral design patterns. So as part of that, we'll be covering strategy design pattern, observer design pattern, command pattern, state pattern, chain of responsibility pattern, and template method pattern. This would also include 6 production worked examples, including order lifecycle management, pricing strategies, and request validation chains. In addition to that, we'll also learn how to combine multiple design patterns in a same design problem as part of the interviews. And in the end, in the 6th and final section of this course, we'll close with 45 minutes on pattern selection and anti-patterns. So as part of that, this section ties together everything from the earlier sections into a decision framework for choosing the right pattern and avoiding common mistakes that interviewers test for. Also, every section in this course includes interview practice questions, decision frameworks, and a summary with interview tips for quick revision. In this section, we'll cover 6 topics: encapsulation, and specifically encapsulation as information hiding, not just access modifiers. The next will be abstraction and how to design clean interfaces. Then we'll cover inheritance, including where it works well and where it creates coupling risks. Then we'll cover polymorphism and how to design for extensible behavior. Then the composition versus inheritance trade-off, which is a single design decision that comes up in almost every LLD OOD interview. And finally, we'll also cover abstract classes versus interfaces with a decision framework you can actually apply during an actual interview. Now, let me walk you through the, where OOP shows up across the different stages of an LLD interview, because it is not limited to one moment. During requirements clarification, the interviewer is already watching whether you can identify the right objects and assign them clear responsibilities. When you move into class design, they're checking whether your classes have well-defined boundaries and clean interfaces. Then comes the extensibility probe, where the interviewer asks something like, okay, how would you add a new type of X? That directly tests your use of polymorphism and open-close thinking. And after that, you get trade-off questions like, okay, why did you use composition here instead of inheritance? And that tests design maturity. And during the code walkthrough, they will check whether your classes are properly encapsulated, whether your methods express behavior rather than just the data access. So OOP is not just one part of the interview, it runs through the entire conversation from start to finish. Now, let us start with encapsulation. When most people hear the word encapsulation, they think of, access modifiers. Make the field private, add a getter, add a setter, and then call it encapsulated. That is not necessarily what encapsulation actually means, and it is not necessarily what interviewers are actually looking for. Encapsulation means that a class controls access to its own internal state and exposes only what other classes need to interact with it. The keyword here is controls. This is a design decision. For every piece of internal state, you are deciding essentially, should external code be able to see this? Should external code be able to change this? And if it can change it, under what conditions? The reason that this matters is that encapsulation protects invariants. An invariant is a condition that must always be true for the object to remain in a valid state. Think about a bank account. The balance should never go negative. That is an invariant. If you expose a public setBalance method, any code anywhere in the system can set the balance to, let's say, -500 and break the invariant. Encapsulation prevents that by making the balance field private and forcing all modifications to go through behavior method that enforces those rules. Now the bank account class on this slide shows this pretty clearly actually. The balance field is private, there is no setBalance method anywhere. The only way to reduce the balance is through the withdraw method, which checks two things. That the withdrawal amount is positive and the amount does not exceed the current balance. If either check fails, it throws an exception. If both pass, it reduces the balance and it records the transaction. This means that no matter how many classes interact with the bank account object, the invariant is always maintained by the class itself. External code cannot put the account in an invalid state. That is real encapsulation. And here's something important for interviews as well. Interviewers explicitly check whether your classes expose raw state or enforce rules through behavior methods. If you have a field that has constraints on what values it can hold and you put a setter on that field, that is a design red flag. The setter bypasses the constraint. The behavior method enforces it. This is a misconception that costs candidates in interviews, and it is worth addressing here directly. Many engineers believe that making fields private and then adding a getter and a setter for every single field counts as encapsulation. It necessarily does not. Think about what happens when every field has a public getter and a public setter. You have made every field essentially effectively public. The private keyword is just a formality. Any code in the system can now read any field through the getter and write any value to any field through the setter. Now you have added boilerplate code without gaining any actual protection. Now, for example, the UserProfile class here, in the first example shows exactly this problem. It has a password field that is marked private, but then it exposes a getPassword method that returns the raw password string and a setPassword method that accepts any string with no validation. There is no hashing, there is no password policy enforcement, there is no minimum length check. Anyone with a reference to that object can read the password directly and set it to an, let's say, empty string. Now, let's look at the stronger version here. The password is stored as a hash, not as a raw text. There is no getPassword method at all. Instead, the class provides two behavior methods. The authenticate method takes a raw password, hashes it, and compares it against the stored hash. It returns true or false. The change password method requires the current password for verification before it allows the change, and it enforces a minimum length of 8 characters. The difference here is fundamental. In the first version, the external code reaches into the object, pulls out the data, and makes decisions about that data. In the second version, external code tells the object what to do, and the object handles that logic internally. The first approach is data access, the second approach is behavior. Encapsulation is about exposing behavior, not data. Now, when the interviewer says that, okay, let's encapsulate this properly, they're checking exactly this distinction. A class full of getters and setters for every field is a data bag. It stores values but does not protect them. An encapsulated class exposes methods that describe what you can do with the object and not what the data the object holds internally. Let us look at a more complete example that shows how encapsulation works across multiple related behaviors. Now, as you can see in this slide, this user account class manages authenticated state, and every method it enforces a business rule. Here the class has 5 fields: user ID, email, password hash, failed login attempts, and a locked flag. None of these have setters. The user ID is marked final, which means it is set once in the constructor and then it never changes. The email can only be changed through the change email method, which requires the current password for verification. The failed login method and the locked fields have no public access at all. They are managed entirely through the authenticate method. Now let us walk through the how authenticate works. when someone calls authenticate with a raw password, the method first checks whether the account is locked. If it is, it returns an account locked result immediately without even checking the password. If the account is not locked, it hashes the provided password and compares it to the stored hash. If the password is wrong, it increments the failed logged attempts counter and checks whether the counter has reached 5. If it has, it sets the locked flag to true. Then it returns an invalid credentials result that includes how many attempts are remaining. If the password is correct, it resets the failed login attempts counter back to 0 and returns a success result. Now, notice what is happening here. The lockout policy, the attempt counting, and the reset on success, all of this lives inside the class. External code cannot call set locked with a false to unlock an account. External code cannot call set failed login attempts with 0 to reset the counter. The only way to interact with the authentication state is through the authenticate method, which enforces every rule internally. Now, the change email method follows the same principle. It does not just accept a new email and store it, it requires a current password first. This means email change cannot just happen without verification. The class protects itself. And here's something important for interviews as well. When you are building your class diagram in an LLD or OD interview, you should ask yourself for each field, should external code be able to read this? Should external code be able to change this? Under what conditions? If the answer of any of those requires a rule or a condition, that field needs a behavior method, not a setter. Now, interviewers pay attention to the ratio of behavior methods to getters and setters in your class design. If most of your methods are behaviors that enforces rules, that signals real understanding of encapsulation. If most of your methods are getters and setters, that signals a data bag. Now that we understand encapsulation, let us talk about the second pillar, which is abstraction. These two concepts work together, but they do hide different things. Encapsulation hides data, it protects the internal state of an object. Abstraction hides complexity. It protects calling code from needing to understand how something works internally. Now, a well-designed abstraction lets you say what you want without knowing how the work gets done. In Java, abstraction is expressed through interfaces and abstract classes. The interface defines the what, and the implementing class handles the how. Now, consider, as you can see in the slide, consider a message sender interface with these two methods: send, which takes the recipient and the content, and check delivery, which takes a message ID and returns a status. Any class that needs to send messages depends on this message sender interface, so it does not know whether the message goes out as an email, as an SMS, or a push notifications. It does not need to know that. Now, if you see on the screen, the second example is the order confirmation service. In that class, it shows how it's being implemented in action. It takes a message sender interface through its constructor. So when it needs to send an order confirmation, it calls the message sender.send with the customer contact and the confirmation message. This is it. The service works with email today. If the team switches to SMS tomorrow, the only change is providing a different implementation of the message sender. The order confirmation service class does not change at all. Now, this is what abstraction gives you: the freedom to change the how without touching the what. Now let us make this distinction between encapsulation and abstraction even more clear. Encapsulation hides the internal data and state. It is expressed through private fields and behavior methods. It protects the invariants and business rules. Abstraction hides implementation complexity. It is expressed through interfaces and abstract classes, and it protects the calling code from change. Now, both of them work together. A well-encapsulated class behind a clean interface gives you maximum flexibility. You can change the internal data and representation and the implementation approach without affecting any code outside the class. And here is the test interviewers apply for abstraction. Interviewers will generally ask you something like, okay, what if we need to swap that component? If swapping requires modifying existing classes that depend on it, your abstraction is leaking. If swapping requires only writing a new implementation class, your abstraction is clean. So what happens when abstraction fails? You get what is called an abstraction leak. This is when implementation details escape through the interface, forcing calling code to know things it should not be allowed to know. Now, abstraction leaks are subtle, and interviewers specifically probe for them in the interviews. The most common form is exposing internal data structures. As you can see in the slide, here, the open repository class in the first example stores orders in the hash map, and then it has a method called getOrderStore that returns that hash map directly. Think about what that means. Every piece of code that calls getOrderStore now knows that orders are stored in a map. It knows the key type is string. It knows the value type is order. The calling code now is tightly coupled to the specific storage implementation. Now, if you later switch from an in-memory hash map to a PostgreSQL database, for example, every single caller of the getOrderStore has to change. But the problem goes much more deeper than that. Since the method returns the actual map, not a copy, external code can call orderStore.clear and wipe all the data. It can call orderStore.put with an invalid order. The repository has lost control of its own data. Now, the fixed version hides the storage mechanism completely. The hash map is still there internally, but no external code knows about it. Instead, the class exposes three behavior methods. FindById, which returns an optional containing the order if it exists. FindByConsumer, which filters and returns a list. And Save, which stores an order. Now the calling code interacts only with these methods. It does not need to know whether orders are stored in a hash map, a tree map, an array list, or a database table. If you switch the storage implementation to a PostgreSQL tomorrow, you change only this one class. Every caller remains untouched. Now, here's a reliable test you can use both in interviews and in your own designs. If you change the internal implementation of a class, whether that means switching databases, changing data structures, or swapping libraries, would any code outside the class need to change? If the answer is yes, you have an abstraction leak. Mention this test during your LLD object-oriented design interview and apply it to your own design. Interviewers respond well to candidates who can articulate a clear principle and then can demonstrate it. Now let us ground abstraction in a real-world scenario that comes up pretty frequently in interviews. Consider a payment system that needs to support multiple providers, Stripe today, PayPal next month, and a region payment method provider, maybe the next quarter. Without abstraction, every class that processes payments would need to know the specific API details of each provider, the request format, the response structure, the error handling. Adding a new provider would mean modifying every one of those classes. Now, abstraction solves this by defining a clean contract. The payment processor interface has three methods: charge, which takes an amount and a payment method; refund, which takes a transaction ID and an amount; and check status, which takes a transaction ID. That is a contract. Every class that processes payments depends on this interface, never on any specific provider. Now, the Stripe payment processor class, as you can see in the slide here, implements that interface. Inside this charge method, it converts amount to cents, builds a Stripe-specific request object called the Stripe client, and maps the response back into a payment result. All of these Stripe-specific details, the conversion to cents, the Stripe charge request class, and the Stripe client call, are completely contained within this one class. Now, the order service depends on payment processor, not on Stripe payment processor directly. It calls processor.charge and gets back a payment result. It does not know or care which provider is behind that interface. Now, when the team adds PayPal support, they write a new PayPal payment processor class that implements the same payment processor interface. Zero changes to order service, zero changes to any other class that processes payments. The new provider plugs in through the interface. And here's something important for interviews. When you're designing class diagrams in your interviews, define your abstractions before your implementation. Draw the interfaces first, then draw the classes that implement them. This signals to the interviewer that you think in terms of contracts and dependencies, not just concrete classes. It also makes the extensibility of your design immediately visible on the whiteboard. Now let's pause and practice what we have covered so far. Here's the scenario. Let's say you're designing a notification preferences class for a system like, let's say, LinkedIn. Users can configure which notification types they would want, such as email, SMS, and push. They can also set quiet hours during which no notifications will be sent. Now let's say the interviewer asks you that, okay, show me your class designed for notification preferences. Now let's take a step back and let's think it through. Now let's compare two approaches for this. Now the weak answer approach would be that, okay, someone candidate would say that, okay, let's have three private fields, a set of strings for enabled channels, an int for quiet start hour, and an end for quiet end hour. And then every field has, let's say, they'll suggest that okay has a getter and setter, and that is essentially a data bag. External code here can set quiet start hour to 25 and quiet end hour to negative, let's say, 3. There's no validation, and the raw set is exposed, so callers can essentially add arbitrary strings like pigeon or as channel names. Essentially, every business rule, whether there is a valid hour, whether there is a valid channel, whether notification should be sent right now, all of that has to live in the calling code. The class holds data, but it does not protect it. Now, let's look at the stronger approach. The stronger approach looks fundamentally different. Instead of strings, it uses a set of notification channel, which is an enum. That means the valid channels are defined by the type system, not by whatever string someone decides to pass in. Instead of separate getters and setters for the start and end hours, there is a single set quiet hours method that validates both values. If either hours is below 0 or above 23, it throws an exception. Now, but the real strength is the should notify method. The calling code does not pull out the fields and make a decision. It calls should notify method with the channel and the current time, and the object answers yes or no. The decision logic is inside the class where it belongs. Now, this is the encapsulation abstraction actually working together. The internal implementation is hidden, the business rules are enforced, the calling code interacts through behavior, not through data access. Okay, now let us talk about inheritance. This is the object-oriented programming concept that engineers tend to reach for the first and overuse the most. Inheritance establishes an is a relationship. Let's say, for example, a savings account is a bank account. A manager is an employee. The subclass inherits all the fields and methods from the parent and can override behavior to specialize it. Now, inheritance is appropriate when 3 conditions are all true at the same time. First, the relationship is genuinely an is a relationship, not a has a relationship, not a uses a relationship. A real natural specialization is needed for this. Second, the subclass needs most or all of the parent's class behavior, not just 1 or 2 methods out of 20. Third, the parent class was designed for inheritance. It has clear extension points like abstract methods that subclasses are meant to implement. Now, as you can see on the slide here, the shape example shows all these 3 conditions being met. The shape class is abstract. It has a color field and a concrete method describe method that uses color and area together. The area method is abstract, meaning subclasses must provide it. Circle extends shape because a circle is genuinely a shape. It uses the inherited describe method. And shape was designed with the abstract area method as a clear extension point. But here is where things get difficult. Inheritance creates tight coupling between the parent and child classes. The subclass depends on the parent's implementation, not just its interface. If the parent changes how a method works internally, the subclass can break even if the parent's public interface stays the same. The subclass also inherits everything. You cannot selectively say that, okay, I want this method but not that one. It's all or nothing. And here's something to keep in mind for interviews. If you use inheritance in your answer, be prepared for the follow-up question. The interview will most likely ask you that, okay, what happens when requirements change? They probe inheritance decisions because they want to see if you understand the coupling risks. If you cannot articulate the trade-off, it looks like you chose inheritance by default rather than by design. Now this brings us to one of the real risks of inheritance, which is the fragile base case problem. This is when changes to a parent class break subclasses in a ways that are impossible to predict by looking at the parent class alone. The root cause is generally something called self-use. Self-use happens when one method in the base class calls another method in the same class. That seems pretty harmless. But if a subclass overrides one or both of those methods, the interaction between the base class and the subclass becomes unpredictable. The subclass author has to understand exactly how the base class implements every method internally. And that violates the principle of abstraction because the internal implementation of the base class should not matter to its subclasses. Now, this is not a theoretical problem. It shows up pretty often in real production code bases as well. It has come up in design discussions about standard libraries like Java's collection framework. And it appears in the interviews when an interviewer, let's say, asks you that, okay, what are the risks of this inheritance hierarchy? Now, being able to explain the fragile base case problem with a concrete example is one of the things that separates, candidates doing not so well in the interviews versus candidates who do well in the interviews. Now let us look at that exactly what that kind of example in the next slide. Now here's a fragile base case problem in action. We have, let's say, an event log class with two methods as shown in the slide. The add event method takes a single event and adds to the list. The add events method takes a list of events and loops through them, calling add event for each one. Notice that add events calls add event internally, that is self-use. Now we create, let's say, a counting event log that extends the event log class. Its job is to essentially keep, a running count of how many events have been added. The overridden add event method increments the count by 1 and then calls the super.add event. The overridden add events method increments the count by the size of the list and then calls super.add events. Now let us trace through what happens when you call add events with a list of 3 events. First, counting event log.add events runs. It adds 3 to the event count. The count is now 3. Then it calls the super.add events, which is the event log.add events. Event log.add events loop through the 3 events and then calls the add event for each one. But because the counting event log overrides the add event, the overridden inversion runs. Each call to the overridden add event adds 1 to the count, so the count goes from 3 to 4, then 5, and then 6. Now the final count is 6, not 3. Every event has gotten counted twice. Once in add events class and then once again is in add event, because the base class implementation calls add event internally. And here's the fragile part. This is not just a one-time bug. If the base class author later changes add events to use a direct add all call on the internal list instead of looping through add event, the counting subclass silently breaks in the opposite direction. Now events would only be counted in add events, not in add event, and single event additions through add event would not be counted at all. The subclass's correctness method depends on implementation detail of the base class that is not part of any public contract. However, the fix for that is composition. Instead of extending event log, the counting event log holds a reference to an event log instance as a delegate. Its add event method increments the count and then calls a delegate.add event. Its add events method increments the count by the list size and then calls delegate.add events. Now the counting logic is completely independent of how event log implements add events internally. Whether the base class loops through add event, uses add all, or does something else entirely, the counting wrapper is unaffected. The two classes interact only through the public interface, not through the inherent implementation details. So far we have covered encapsulation, abstraction, and inheritance. Now let us talk about polymorphism, which is the principle that ties everything together for extensible design. Now polymorphism means that the same method call can produce different behavior depending on the actual object it is being called on. In Java, there are 2 forms. The first is runtime polymorphism, which works through method overriding. The method that actually runs is determined at the runtime based on the real type of the object, not the declared type of the variable. This is the form that matters most for the interviews. Now consider a variable, let's say declared as payment processor, which is the interface type. At runtime, this variable holds a Stripe payment processor object. When you call processor.charge, the JVM looks at the actual object type and runs Stripe payments processor's charge method. If you reassign that same variable to hold a payment processor object, the same processor.charge calls now executes completely different code. Now, the calling code does not change. Only the behavior changes based on which implementation is behind the interface. The second form is compile time polymorphism, which works through method overloading. This is when you have multiple methods with the same name but different parameter list. The compiler check picks the right version based on the arguments you pass. The price calculator class on the slide here has just 2 calculation methods. One takes just an order, the other takes an order and a discount code. The compiler decides which one to call based on what arguments are provided. Now, why does runtime polymorphism matter more for design? Runtime polymorphism enables extensibility. It is the foundation of plugin architectures. When you design around interfaces and let different implementations provide different behavior at runtime, you get systems that can grow without being modified. Runtime polymorphism is what powers the strategy pattern, the factory pattern, the observer pattern. Compile time polymorphism is convenient for API usability, but does not change how your system is structured. Let's say when the interviewer asks you that, okay, design this system to be extensible, they're asking you to essentially use runtime polymorphism. They want to see that adding a new type means writing a new class, not modifying existing code. So polymorphism does not happen by accident. You have to design for it deliberately. And the design process follows a clear pattern as shown in the slide here. Step 1 is to identify what varies. In any system, some things stay constant and some things change. Let's say in a notification system, the act of sending a notification is constant, but the delivery channel varies. It could be an email, SMS, push, or something else entirely. Then step 2 is defining an interface for the thing specifically that varies. So the interface captures the contract. Every implementation must provide these methods, but each implementation does it differently. Then step 3 is writing one implementation per variant, which could be email channel, SMS channel, and push channel. Each one of them handles the delivery differently, but they all satisfy the same contract. Step 4 is writing the calling code so that it depends on the interface, not on any specific implementation. So for example, the notification service calls channel.send without knowing which channel it is, and it does not care as well. Now the diagram on the slide over here shows this exact structure. A notification service points to the notification channel interface. The interface has 3 implementations: email channel, SMS channel, and push channel. The service talks only to the interface. The implementations themselves are pretty interchangeable. And now here's why this is important and why this matters. Without polymorphism, adding a new channel like let's say WhatsApp means going into the notification service and adding another if or else switch branch. Every time a new channel is added, existing code then needs to be modified. However, with polymorphism, adding WhatsApp means writing just one new class, WhatsApp channel, that implements the notification channel interface. So that means 0 changes to the notification service and 0 changes to any existing channel class as well. And this is essentially open-close principle in action. The system is closed for modification, but it's open for extension. We will cover more of that principle, which is open-close principle in depth in section 3. But for now, recognize that the principle is built directly on top of polymorphism. The ability to identify what varies in a system and extract it into an interface is one of the strongest signals interviewers look for in an interview. It shows that you can design systems that grow cleanly rather than becoming more fragile with every new business requirement. Now let's build this out into a complete working implementation. This is a polymorphic notification system for a platform, let's say like Slack, and it shows a full pattern from interface to dispatch. As you can see on the slide here, the notification channel interface defines 2 methods. The send method takes a user ID and a message and delivers a notification. The support method takes a notification type and returns a boolean indicating whether this channel handles that type of notification. The email channel class implements this interface, so its send method looks up the user's email address from a user directory, then calls the email client to send the message. Its suppose method returns true for marketing and transactional notification types. Then if you look at the push channel class here, it also implements the interface. It sends method, it actually looks up the user's device token from the device registry, then it calls the push gateway. Its supports method returns true for transactional and alert types. Notice that each channel, knows its own delivery mechanism and its own supported types. That knowledge lives inside each implementation, not in the calling code. Now, as you can see on the slide, the notification dispatcher class ties it all together. It takes a list of notification channel instances through its constructor. When dispatch is called, it loops through every registered channel, checks whether that channel supports the given notification type, and if it does, it calls send. The dispatcher does not know about email, it does not know about push, it does not know about any specific channel. It only knows the notification channel interface. Now, adding WhatsApp to this system requires writing a single WhatsApp channel class that implements notification channel and registering it with the dispatcher. The notification dispatcher class is never modified. No existing channel classes are modified as well. And here is something that strengthens your interview answer. When you present a polymorphic design like this, explicitly state the extensibility property. You should say something like this in the interview that, okay, adding a new type of notification channel requires writing one new class. No existing classes are modified. When you say that statement in an interview, that will directly demonstrate, extensibility and signals design maturity. Interviewers actually specifically look for statements like that. Now, this exact pattern, an interface plus multiple implementations plus a dispatcher registry, appears in nearly like pretty much very common LLD OOD interviews. You should practice for notification systems, payment processing, file export, discount calculation, and any other scenario where behavior varies by type. Let us practice this with another scenario. So let's say you're designing a file export feature for a good document management system like, let's say, Google Docs. Users can export documents to PDF, docx, or HTML formats. Now let's say the interviewer asks you, okay, show me your class design for this export feature. Now let's take some time to think about it before we jump into the answer here. I'll show two approaches. One is essentially a weak answer approach, and then we'll shift to the stronger approach for the interviews. So weak answer would something look like this. Okay, let's say you put all the export logic into a single document exporter class with one export method. Inside that method, there will be an if-else chain. If the format string equals PDF, we call the PDF library. If it equals docx, we call the word library. And if it equals HTML, we call the HTML generator. Now let's think about what is wrong with this. Every time a new format is added, whether that is Markdown, EPUB, or plain text, you would have to open this class and add another branch. Then the class, it grows with every new format. It has to import every format library. Testing one format means constructing the entire class with all its dependencies. And if someone passes an unrecognized format string, the method silently does nothing because there is no matching branch. Now let's shift to the stronger answer, which uses polymorphism. So the document exporter is now an interface with two methods: export, which takes a document and returns bytes, and get format name, which returns a format string. Each format gets its own class. PDF exporter implements document exporter. It uses a PDF library internally to create a PDF document, add content, apply styles, and render to bytes. A map of string to document exporter route formats names to the right exporter. Adding Markdown support means writing a Markdown exporter class, so that will be zero changes to the existing code. Now the difference between these two answers in interview is pretty significant. The first answer shows procedural thinking. The second answer shows object-oriented thinking. And interviewers are actually looking for the second approach. Now we come to what I consider the single design trade-off that matters a lot in object-oriented design. This is a topic the interviewers test directly, and the one that separates candidates, who have essentially memorized principles from candidates from who actually truly understand object-oriented design. And we definitely want to be in the second group. Now, so a statement like, okay, favor composition over inheritance, I'm pretty sure you have heard a lot of times in your career. It is essentially a design principle with concrete technical reasons behind it. But now let's go through those reasons in this slide. Now, interface creates and is a relationship. The child class is a specialized version of the parent. It inherits all the fields, all the methods, and all coupling to the parent's internal implementation. Composition has a relationship. The class holds a reference to another object and delegates work to it. The composed object can be swapped, configured, or replaced without affecting the composing class. Now, let us compare them across several dimensions. So in terms of coupling, inheritance creates tight coupling because the child depends on the parent's internals. Composition creates loose coupling because the composing class depends only on an interface. Next, in terms of flexibility, inheritance is fixed at compile time. You choose the parent class once and it cannot change. Composition is swappable at runtime. You can inject different implementations through the constructor or a setter. Now, in terms of reuse granularity, inheritance is all or nothing. You inherit everything, including methods you may not need. Composition is selective. You compose only the pieces you actually would want. For testing, inheritance requires constructing the full parent hierarchy. Composition lets you mock each composed dependency independently. And for combining multiple behaviors, Java allows only single inheritance, so you can only have one parent class, but you can compose as many behaviors as you need. And for the fragile base class risk, inheritance has it, composition does not. Now, when you choose inheritance in an interview, the interviewer will likely ask you that, okay, why not composition here? So you should have a concrete reason ready. When you choose composition, stating your reasoning explicitly is something like, okay, I chose composition here because the relationship is a has-a relationship, and I want the flexibility to swap implementations at the runtime. And that's a pretty good answer to say that in the interview. Now let us make this concrete with a scenario that shows exactly where inheritance falls apart. Consider a notification system for a platform like, let's say, Slack. Now you have multiple channel types: email, SMS, and push. And you have multiple priority levels: urgent, normal, and digest. These are two independent dimensions of variation. So with inheritance, you start by creating a notification channel base class with email channel, SMS channel, and push channel as subclasses. Then you need to add priority. So you create urgent email channel, digest email channel, urgent SMS channel, digest SMS channel, urgent push channel, and then digest push channel. So that is essentially 6 leaf classes for just 2 priorities across 3 channels. Now let's say if you add a third priority level, like let's say scheduled, that adds 3 more classes, and a fourth channel like WhatsApp that adds 3 more. Now the class count grows as channel multiplied by priorities, so 4 channels and 3 priorities means 12 classes, 5 channels and 4 priorities means 20 classes. Essentially that is the channel explosion problem, and it is a direct consequence of inheritance forcing you to pick one hierarchy. Now composition actually solves that problem pretty cleanly. Instead of creating a class for every combination, you create 3 separate interfaces: delivery method for the channel dimension, priority handler for the priority dimension, and message formatter for formatting. Now the notification center class takes all 3 through its constructor and composes them together. Its sends method calls a formatter, then passes a formatted message to the priority handler, which schedules it through the delivery method. Now adding WhatsApp would mean writing just one delivery method implementation. Adding scheduled priority means writing one new priority handler implementation. The class count grows as channel plus priorities, not channels multiplied by priorities. So 4 channels and 3 priorities means 7 component classes, not 12. And here's something that is very effective in interviews. When your class diagram has 2 or more independent dimensions of variation, point it out explicitly. You should say something like, okay, I see 2 independent axes of variation here, channel type and priority level. Inheritance forces me to pick one hierarchy and duplicate the other across every subclass. Composition lets me vary each dimension independently. And that is a pretty strong statement to say in the interview, because that will show the design maturity and your strong understanding of object-oriented design. Now let us turn this into a decision framework you can apply during an actual interview. You should choose inheritance when all 3 of these conditions are true simultaneously. First, the relationship is a relationship. Let's say, for example, a savings account is a bank account. Second, the subclass uses most or all of the parent's behavior, not just 1 or 2 methods out of many. Third, the parent class was designed for extension with clear abstract methods or hooks that subclasses are meant to implement. Now, if any of these conditions is false, composition is a safer choice. You should choose composition when any of these conditions is true. The relationship is a has-a or a uses-a relationship. An order, let's say for example, would be an order has a payment processor, or you need to combine behaviors across multiple sources, or you would want to swap behavior at runtime, like switching between different pricing strategies, or you see 2 or more independent dimensions of variation, like the channel and priority example we just covered. And another example would be, let's say, or you want the composed object to be independently testable. Now let us also look at how common requirement patterns map to these approaches. When the requirements say, let's say, different types of X with a shared core of behavior, inheritance can work, but still cautiously. That is, true is a relationship with a common base. Now let's say when the requirements say that, okay, different types of X, but with each type has a fundamentally different behaviors, that is composition with an interface. That is a plug-in architecture. And then when the requirement says that, okay, X can do Y in multiple ways, that is composition with strategy pattern, which is swappable algorithms. And when the requirement says that, okay, X needs capabilities from both A and B, that has to be composition, because Java only allows the single inheritance. And then when the requirement says that, okay, X must work with different Z implementations, that is composition with dependency injection for loose coupling and testability. Now, stating your decision criteria out loud during interview shows the interviewer that you are making a deliberate trade-off, not just defaulting to whatever comes to mind first. Now let us address a question that comes up in almost every object-oriented design interview, which is to when to use an abstract class and when to use an interface. Both defined contracts and implementing classes must fulfill. The difference is in what they can provide beyond the contract. Now, an abstract class can hold state, meaning it can have instance fields. It can provide concrete method implementations alongside abstract ones. It can define constructors to enforce initialization logic, and it establishes an is-a relationship. So for example, as you can see in the slide here, the database repository abstract class, that's an example of that. It has a protected data source field that every subclass shares. It has a constructor that requires a data source to be provided. It has a concrete get connection method that subclasses can call, and it declares two abstract methods, find all and save, that each subclass must implement for its own entity type. Now, an interface on the other hand defines a pure contract with no state. Since Java 8 interfaces can have default methods which are concrete method implementations, but they still cannot hold instance fields. The key advantages of the interface is that a class can implement multiple interfaces simultaneously. Now, as you can see on the slide, the example shows a product class that implements both the cacheable interface and the auditable interface. Cacheable provides a get cache key and get time to live. Auditable provides get last modified by and get last modified at. A single class fulfills both contracts. That is impossible with abstract classes because Java allows only single inheritance. Now, the key difference that comes down to is this. Abstract classes can hold instant fields, interfaces cannot. Abstract classes have constructors, interfaces they do not. A class can extend only one abstract class but can implement many interfaces. Abstract classes expresses an is-a relationship, meaning a strong hierarchical bond. Interfaces expresses a can-do relationship, meaning a capability. Now, understanding these differences at a technical level is necessary, but it's not sufficient. Interviewers would want to see you apply them through a decision framework, so let's look at that next. Now, here's a decision framework. Choose an interface when you are defining a capability that multiple unrelated classes can have. Serializable, comparable, cacheable are all good examples. These are capabilities, not inheritance hierarchies. Also choose an interface when a class needs to conform to multiple contracts simultaneously because only interfaces support that in Java. Choose an interface when you want maximum flexibility for the implementing classes, meaning you do not want to force them into an inheritance hierarchy. And you should also, then the next reason is that the choosing interface when you are defining a contract for dependency injection. That is the most common case in LLD interviews. So your services depend on the interfaces and the implementations are injected through constructors. Now, you should choose an abstract class when subclasses they do share state. That means common fields like data source, a logger, or a configuration object that every subclass needs. Choosing an abstract class when you want to provide a partial implementation. That is a template method pattern where the abstract class implements the common steps and subclasses fill in the variable steps. You should also choose an abstract class when you need constructors to enforce initialization logic, like requiring a database connection to be provided before the object can function. And you should also choose an abstract class when the relationship is a genuine shared implementation hierarchy, like all database repositories needing a database connection. Now, the more common mistake in interviews is using an abstract class when an interface would be better. Candidates default to abstract classes because they want to share code between subclasses, but this forces a single inheritance hierarchy, which limits future flexibility. You can only extend one abstract class, so you are locking your subclasses into one hierarchy permanently. Now, since Java 8 interfaces can have default methods, which means interface can provide shared behavior without requiring an abstract class. This blurs the lines between the two, but the rule still remains clear. If you need shared state, meaning actual instance fields, use an abstract class. If you only need shared behavior, meaning methods, an interface with default methods is usually sufficient. Now the decision shortcut is pretty simple. Do you need shared fields? Okay, then use abstract class. Everything else, you should use interface. Now in an LLD or OOD interview, default interfaces for defining contracts between your classes. Only introduce an abstract class when you can point to a specific shared state that subclasses need to inherit. This shows the interviewer that you are not creating unnecessary coupling. And this is something you should write down for your interview prep. These are the 5 decision points that interviewers evaluate more frequently. Note these down because they form a checklist essentially you can apply to every class you design in an LLD interview. Decision number 1, the encapsulation check. For every field in your class, you should ask, okay, should external code be able to change this directly? If the answer involves a condition or a rule, like let's say only if the current password is verified or only if the value is between 0 and 23, then that field should not have a setter. It should have a default behavior method that enforces that business rule. Decision 2 is the abstraction check. For every dependency your class has, you should ask that, okay, if I swapped the implementation, would the calling code need to change? If the answer is yes, introduce an interface. The calling code should depend on the interface, not on the concrete class. Decision 3 is inheritance versus composition. You should always default to composition. Use inheritance only when a relationship is a relationship and the subclasses uses most of the parent's behavior and the parent was designed for extension. All 3 conditions must be true. If even one of them is false, you should default to composition. Decision 3 is interface versus abstract class. So you should always default to interfaces. Use abstract classes only when subclasses share state, meaning actual fields, not just behavior. Then decision 5 is the polymorphism check. For every if-else or if-switch statement on the type in your code, you should ask that, okay, could this be replaced with polymorphic dispatch? And if a method behaves differently based on the type of an object, that behavior belongs in the object itself, not in the caller. Now, the quick reference table here on the slide maps common design smells to their fixes. Getter and setters on every field mean you should replace them with the behavior methods. An if-else chain on an object type means you should extract an interface and use polymorphism. A class that inherits only uses 1 or 2 methods from the parent means you should switch to composition. An abstract class with no shared fields means it should be an interface. And calling code that knows the implementation details mean you need to introduce an abstraction layer. And these are the 5 checks that you should definitely keep in your interview prep for the LLD, OOD, object-oriented design interviews. Now let us put everything we have learned in this section into practice with the full scenario. Let's say you're designing a ride-sharing system like Uber. The system supports multiple vehicle types, sedan, SUV, luxury, and also supports multiple pricing strategies, which are flat rate, surge pricing, subscription discount. Let's say now the interviewer asks you that, okay, walk me through your class design for this problem. Now let's take a step back, let's think about it before we jump into the answer here. Now the critical observation here is that the vehicle type and pricing strategy are 2 independent dimensions of variation. If you heard 2 independent dimensions of variation and immediately thought composition, that is the right instinct. This is exactly that composition signal we discussed in the earlier slides. Now a strong answer separates these into 2 interface hierarchies. One interface for vehicle type, one interface for pricing strategy. The right class composes them together, so you can create any combination, a sedan with a surge pricing, or an SUV with a subscription discount, or a luxury vehicle with a flat rate. Each combination is just a configuration, not a new class. However, a weak answer would create, an inheritance tree like subclasses, like classes like surge pricing, sedan ride, or a flat rate luxury ride. That leads to the class explosion problem we saw earlier in the few slides ago. So that would be 3 vehicle types and 3 pricing strategies means 9 classes. And if you add a 4th vehicle type, you would need 3 more. So that is not ideal. Now let us walk through the common OOP mistakes that show up in LLD interviews because they map directly to what we have covered. Using getter and setters in every field exposes internal state and removes the invariant protection. The stronger approach is behavior methods that enforces those business rules. Then, using inheritance purely for code reuse creates coupling without a genuine is-a relationship. The stronger approach is composition with delegation. Then, putting all logic in one massive class violates the encapsulation and makes testing impractical. The stronger approach is separate classes with focused responsibilities. Using if-else chains on type strings is fragile, not extensible, and misses the opportunity for polymorphism. The stronger approach is an interface with implementations per type. Using an abstract class where interface would work forces single inheritance and it limits the flexibility. The stronger approach is an interface with default methods if shared behavior is needed. Now, exposing internal connections allows callers to modify states without going through validation. The stronger approach is returning unmodifiable copies or exposing behavior methods instead. Now, each stronger approach in this table is what earns a strong higher signal in the interviewer feedback, and these are the patterns interviewers, they are trained to look for in object-oriented design interviews. Now, here is the reference card and the summary for this entire section. This slide is designed to be essentially, you should go through, reference it quickly before the interviews, the object-oriented interviews, and keep in your notes. Now, let us walk through what we have covered. Encapsulation means controlling access to state through behavior methods, not through getters and setters. The class owns the data and enforces the rules. Abstraction means hiding implementation complexity behind clean interfaces. The calling code says what it wants, the implementation decides how. The abstraction leaks happen when implementation details escape through the interface, forcing callers to know things that they should not need to know. Inheritance creates an is-a relationship with full coupling to the parent's class. It works when this relationship is genuine, the subclass uses most of the parent's behavior, and the parent would design for extension. The fragile base class problem is what happens when a subclass breaks because the parent's internal implementation changes. Runtime polymorphism gives you the same method call producing different behavior based on the actual object type. Compile time polymorphism is method overloading resolved by the compiler. Composition over inheritance means has-a with a loose coupling should be preferred over the is-a approach with the tight coupling in most cases. Abstract classes provide shared state plus partial implementation for a genuine hierarchy. Interfaces provide a pure contract with multiple implementation and maximum flexibility. Now, the common interview mistakes table here maps weak answers to strong answers, so you know what approach to take. So a weak answer would be that someone says that I use getter and setters to encapsulate data. That should become that instead you should say that I expose behavior methods that enforces the business rules. Another mistake or a weak answer would be that I used inheritance because the child reuses parent code. Instead, you should say that in the interview that I use composition because the relationship is has a relationship and I need runtime flexibility. Very next common interview mistake is that people saying that I use an abstract class to define the contract. Instead, you should say that I use an interface because there is no shared state. And implementers, they may need multiple contracts, so you should go with interfaces. And the fourth common interview mistake is that people sometimes say that I added a switch statement for each new type. Instead, you should say go with the approach that and say that in an interview that I use polymorphisms, so adding a new type is a new class, not a code change. Now, the key tests to remember are these. For encapsulation, ask, can external codes violate an invariant? For abstraction, ask, would swapping the implementation require caller changes? For inheritance, ask, is this truly a is-a relationship and does the child use most of the parent? But for polymorphism, ask if there's an if-else or on the type. For inheritance, for interface versus abstract class, ask that, is there a shared state? And now this is how the section connects to what comes next. In section 1, we covered the mental model and evaluation rubric. This section covered the class design clarity and correct use of object-oriented programming criteria from that rubric. In section 3, we'll cover solid principles which build directly on top of object-oriented programming. Single responsibility defines encapsulation. Open-close formalizes polymorphism for extensibility. Liskov substitution, constrains inheritance. The inheritance segregation defines abstraction. And dependency inversion enforces composition over concrete dependencies. And then in sections 4 through 6, we'll cover design patterns. So every design pattern is built on the OOP primitives. Factory uses polymorphism. Strategy design pattern uses composition. Observer design pattern uses interfaces. So understanding object-oriented programming deeply makes every pattern feel intuitive rather than just like trying to learn it from scratch. So now in the next section, let's move to learning more about solid principles and the design patterns. So in section 2, we build the foundation: encapsulation, inheritance, polymorphism, and abstraction. Those 4 pillars give us the mechanics of object-oriented programming, but mechanics alone do not tell us how to use them well in production. And this is what exactly this section is about. Solid principles are essentially a set of 5 design principles that guide how you structure classes and how those classes relate to each other. These 5 principles are single responsibility principle, open close principle, Liskov substitution principle, interface segregation, and dependency inversion principle. Each one of them addresses a specific kind of design problem that shows up repeatedly in real code bases as well as the interviews. Now here's what matters in the for the interviews. So solid is not just tested on theory. So no interviewer is essentially going to ask you that okay, recite the definition of open close principle. However, the interviewer is actually there to evaluate whether you instinctively apply these principles when you design your classes and whether you can spot violations when they probe your design with follow-up questions. So each solid principle connects directly to the object-oriented programming foundations we had just covered in the previous section. So SRP refines how you think about encapsulation. Open close principle formalizes polymorphism for extensibility. LSP constrains where inheritance is appropriate. And ISP defines how you design your abstractions. And then the dependency inversion principle enforces composition over concrete dependencies. So if object-oriented programming gives you the building blocks, solid gives you the rules for assembling them correctly. Now let me walk you through where these principles appear during an actual interview. So when an interviewer, let's say, asks you that okay, how would you able to add a new feature, they are testing for open close principle. Let's say now when their interviewer is asking you, okay, this class is doing too much, then they're testing you on single responsibility principle. If the interviewer asks you for, okay, what if we swap this implementation, then they're testing you on dependency inversion principle, DIP. And when they question whether a subclass belongs in hierarchy, that is LSP. And when they point out that the interface is too large, for example, so that would be interface segregation principle, ISP. And also during a design review or code walkthrough, they're testing for all of these 5 at once. Now let us start with the principle that gets tested more often than any other principle in object-oriented design interviews, which is single responsibility principle, or SRP. Now SRP states that a class should have only one reason to change. Now that sounds pretty simple, but the one responsibility part is kind of vague, and this is where most people kind of get it wrong. So mostly folks think that SRP means a class should only do one thing. But that is not precise enough. The real definition is about change drivers. A class should be affected by changes from exactly one source. So what is a change driver? A change driver is a stakeholder, a business domain, or a technical concern that could independently require modification to the class. If two completely unrelated changes both require editing the same class, that class has more than one responsibility. Now let us make this concrete. If you look at the class, the slide over here, now think about an invoice service class, for example, that calculates totals, formats the PDF output, and sends emails. 3 different change drivers affect the single class. The finance team might change the tax calculation rules, the design team might change the PDF invoice layout, and the infrastructure team might switch from, let's say, SMTP to a third-party email API. Now, each of these changes come from a different stakeholder and a different domain. Yet all 3 requires editing the same invoice service class. Now let's think about this. Why is that a problem? Because the change requested by the design team to update the PDF layout could accidentally break the tax calculation logic. Maybe the developer modifies the wrong method, or a merge conflict introduces a subtle bug. SRP violations increase the blast radius of every change. A change that should be isolated to one domain now ripples into unrelated domains because the class bundles them together. And here's something important for interviews. When an interviewer asks you that, okay, does this class have a single responsibility? Do not answer with that, okay, it does one thing. Instead, identify the distinct change drivers. Say something like, okay, this class would need to change if the tax rules change, or if the PDF format changes, or if the email provider changes. Now that is 3 separate reasons to change, so that that essentially violates SRP. When you frame it like that, counting change drivers is what separates a not ideal answer interview to a very strong one. So you should go with that approach. Now SRP is like one of the most commonly tested solid principle. Interviewers often present class with 5 or 6 methods spanning different domains, and then they ask you to refactor it. Knowing how to identify and count change drivers is a skill that unlocks those questions. Now let us look at a realistic example of an SRP violation. This is a kind of code you'll see in production code bases and also in interview questions. Now let's say we have a user service class that handles 4 things: authentication, profile management, email notifications, and audit logging. The class takes 3 dependencies through its constructor: a user repository, an email client, and an audit logger. Now the authenticate method looks up the user by email, verifies the password hash, logs the result to the audit logger, and returns a boolean. The update profile method finds the user, updates the name and bio, saves to the repository, sends a confirmation email, and logs the event. The reset password method generates a temporary password, saves it, and emails it to the user and logs the reset. Now let's look at the change drivers here. There are 4 distinct ones packed into a single class. First, authentication policy. If you need to add 2-factor authentication, you're editing the authenticate and reset password methods. Second, profile business rules. If you need to add profile, picture uploads, or bio length limits, you are editing update profile. Third, notification requirements. If you need to switch from email to SMS or add templates, you're editing update profile and reset password. Fourth, audit compliance. If you need to change the log format or add a retention policy, you're editing all 3 methods. Now a change to the email template system could introduce a bug in authentication if a careless merge modifies the shared state. Every method in this class is affected by unrelated changes, and that is exactly the problem SRP is designed to prevent. Now if an interviewer presents you with a class like this and then they ask you that, okay, what is wrong with this design? The answer is SRP violation. You identify the change drivers, you count them, and then you explain why bundling them together creates risk. Now the next slide will show exactly what the refactored version should look like. So now how do we fix the user service? Each responsibility gets its own class with its own single chain driver. The authentication service class takes a user repository and an audit service. Its authenticate method looks up the user by email, verifies the password, records the audit event, and then returns an auth result. Notice that the auth result is a proper result object now, not just a boolean. It carries information about where the authentication has succeeded, and if it has failed, then why. That is small but meaningful improvement. Now, the profile service class over here takes a user repository and a notification service. Its update profile method finds the user, applies the changes, saves them, and sends the profile update confirmation. The only reason this class would change is that if the profile business rules change. Now, the next example is the profile reset service class takes a user repository, a notification service, and an audit service. Its reset password method generates a temporary password, updates the user, sends a reset notification, and records the audit event. A change to how password reset work affects only this class. Now let's think about what we have gained. A change to the authentication policy affects only the authentication service. A change to the notification delivery affects only the notification service. A change to the profile rules affects only the profile service. So the blast radius for every change is now contained to a single class. No more worrying about the updating an email template that will break the login flow. Now, for interviews, presenting this refactored version demonstrates that you can decompose responsibilities, not just identify violations. Interviewers want to see both the diagnosis and the treatment. Spotting the problem is step 1. Showing a clean refactoring is what earns a strong signal. Now this single responsibility principle connects to something much more larger. The same principle that guides how you split classes and also guides you how to split services in a distributed system. Think about the refactored user service from the previous slide. We ended up with an authentication service, a profile service, a notification service, and an audit service. Each class has one chain driver. Each class communicates with others through interfaces. Now map that to the service level. The authentication service class becomes an authentication microservice. The profile service class becomes a user profile microservice. The notification service becomes a notification microservice. And the audit service becomes an audit and logging microservice. Each service is now independently deployable, independently testable, and owned by a separate team. Each service changes for exactly one reason, just like the classes. Now, this is not a coincidence. SRP and microservice boundaries are the same concept applied just at different scales. At the class level, classes communicate through interfaces. At the service level, services communicate through APIs. The principle itself is identical, the mechanism changes. But now here's where the analogy kind of breaks down and has its own limits, and it's worth understanding as well. The cost of splitting is different at each scale. Splitting a class into 3 classes adds minimal overhead. You've got a few more files, a few more constructors, but the runtime cost is close to zero. Now, however, splitting a monolith into 3 different services adds network latency, distributed transaction complexity, deployment infrastructure, and operational monitoring. Each service boundary introduces real operational cost. And this is why single responsibility principle does not mean just like split everything. Both at the class level and at the service level, the question is whether the cost of coupling, meaning shared chain drivers and cascading modifications, exceeds the cost of separation, meaning the additional coordination and infrastructure. When the coupling costs are high, you split. When the separation costs are high, you keep things together. Now, making this connection between class level SRP and service level decomposition shows the interviewer that you think across abstraction levels. That ability to reason at multiple scales is a signal of a senior level design thinking. Now that we understand single responsibility principle, let us move to the second solid principle, which is the open close principle, or as we call it also OCP. So open close principle states that a class should be open for extension but closed for modification. So in practical terms, this means that you should be able to add a new behavior to a system without changing the existing tested code. Now, that does not mean you never modify existing classes. That would be pretty unrealistic. What it means is that you design your classes so that the most likely type of change, like adding a new variant, supporting a new format, handling a new case, can be done by writing new code rather than editing old code. Now, why does this matter? Every time you modify an existing class, you risk breaking something that has already been working. If adding a new discount type requires editing the pricing calculator class, and that class also handles tax calculation and currency conversion, a bug in the new discount logic could break tax calculations. Now, OCP minimizes this risk by ensuring new behavior is added through new classes, not by editing existing ones. OCP is actually the formal principle behind the polymorphic design we covered in section 2. So when you define an interface and add new implementations, you are following OCP. The interface is closed, its contract does not change. The system is open, so new implementations can be added freely. Now let's think about it visually. You have an order service that depends on a discount strategy interface. Behind that interface, you have a flat discount, percentage discount, and season discount. Adding a new discount type means creating a new class that implements the discount strategy interface. The order service never changes, so no existing discount classes changes. The extension point is represented by that interface and is where the new behavior enters the system. Now, the OCP is the second most tested solid principle behind after SRP. So interview is tested by asking, okay, how would you add a new type of, let's say X? If your answer involves modifying existing code, you have essentially violated OCP. However, if your answer is that, okay, I will write a new class that implements this interface, you have demonstrated open close principle. Now let us look at OCP in action with a concrete before and after example. Before OCP, we have a pride calculator class with a calculate discount method that takes an order and a discount type string. Inside that method, there is a switch statement. If the discount type is flat, return a flat $10 discount. If it is percentage, multiply the subtotal by 0.15. If it is buy one, get one, return the cheapest item price, and the default returns to 0. Now, every new discount type requires adding a new case to the switch statement. If the marketing team creates promotion frequently, this class is being edited constantly. And every edit risks breaking the existing discount logic. The flat case worked fine for months, but then when someone let's add seasonal and accidentally misplaces the break statement, suddenly flat discounts are broken too. Now let us look at the OCP compliant version. We define a discount strategy interface with two methods, calculate discount, which takes an order and returns the discount amount, and is applicable, which takes an order and returns where this discount applies. Now each discount type becomes its own class. The flat discount class takes the discount amount through its constructor. Its calculate discount method returns that amount. Its is applicable method checks where the order subtotal exceeds $50. Each class is self-contained, encapsulating both the logic and the applicability condition. Now the pricing calculator class now takes a list of discount strategy objects through its constructor. Calculate best discount method streams through the available discounts, filters for applicable ones, maps each to its discount amount, and returns the maximum. The price calculator class is closed for modification. Adding a, let's say, seasonal 20% off discount means writing a seasonal discount class and registering it. The price calculator class is never edited. Now, this before and after transformation is the exact pattern interviewers expect when they ask, okay, how do you make this extensible? Show the switch statement first and then explain why it violates the open-close principle and then show the interface-based solution. Now the discount example from the previous slide is actually a design pattern in disguise. It is a strategy pattern. The strategy pattern is the most direct implementation of open-close principle. You define a family of algorithms behind an interface and the calling code works with any of them interchangeably. The pricing calculator is the context. It holds a reference to the strategy interface and delegates the discount calculation to whatever implementations are provided. Each concrete strategy, flat discount, percentage discount, seasonal discount, loyalty discount, encapsulates one algorithm. Now we'll cover the strategy pattern in full depth in section 6, which covers the behavioral design patterns, but recognizing these connections now matters. Open-close principle tells you why to design this way. A strategy pattern tells you how. Now, the same open-close principle plus strategy structure applies to any requirement that says that, okay, support multiple types of X. Multiple discount types map to a discount strategy interface with implementation of flat, percentage, seasonal, and loyalty. Multiple payment methods map to a payment processor interface with Stripe, PayPal, and bank transfer. Multiple export formats map to a document exporter interface with PDF, DocX, HTML, and CSV. And multiple notification channels map to a notification channel interface with email, SMS, push, and webhook. And similarly, multiple compression algorithms map to a compression strategy interface with gzip, snappy, LZ4, and ZCD. Now, every one of this is a place where open-close principle prevents you from writing a growing switch statement. And here's something important for interviews as well. When you hear a statement like, okay, support multiple types of X in an object-oriented interview, your first instinct should be to define an interface for X. Say this out loud in the interviewer so that they understand exactly what you think. So you can say a statement like, okay, since we need multiple types of X, I will define an interface so we can add new types without modifying existing code. This demonstrates open-close principle thinking without needing to name the principle explicitly. The interviewer hears the reasoning and recognizes the principle. Now, the connection between OCP and strategy is one of the highest value insights for object-oriented design interviews. Interviewers expect you to reach for this pattern whenever you hear multiple types of. Now, let us put the single responsibility principle and open-close principle together with a practice scenario. Now, let's say you're designing an order processing system for a platform like Shopify. The order processor class currently handles order validation, inventory checking, payment processing, shipping label generation, and sending confirmation emails. Now, let's say the interviewer asks you that, okay, what is wrong with this design and how would you fix it? Now, let's pause for a minute and let's think about it deeply before jumping. We can jump to a solution. Now, we'll first start with the weaker answer and then we'll go to a stronger answer. So weaker answer, which is not an ideal answer, will sound something like this. The class is too big, I would split into smaller classes. If a candidate says something like that, that answer identifies the symptom but not the principle. It does not explain why the class should be split or how to design where the boundaries go. An interviewer hearing this does not know whether you understand single responsibility principle or you just notice that the class is too long. Now here's what a strong answer sounds like. You should say something like this in the interview. So essentially you should say that, okay, this class violates single responsibility principle because it has 5 distinct chain drivers: validation rules, inventory management, payment processing, shipping integration, and notification delivery. A change to the shipping provider should not require editing the same class that handles payment processing. Just like that, you should also continue that, okay, I would refactor into 5 classes, each behind an interface, which will be order validator, inventory service, payment processor, shipping service, and notification service. The order processor becomes an orchestrator that delegates to each of these services through its interface. And then the strong answer connects to the open close principle. So then you should say something like, okay, this also enables open close principle because when we add a new payment provider, we write a new payment processor implementation. When we add a new notification channel, we write a new notification service implementation. The orchestrator itself never changes. Now notice that what makes the strong answer strong. It names the principles. It identifies the specific change drivers and explain how the refactor design enable the future extension. That combination of diagnosis, treatment, and forward thinking is what earns the strong interview segment. Okay, now let us move to the third solid principle, and which is actually a very least intuitive one, which is the Liskov substitution principle, or LSP. Now LSP states that if the class B is a subtype of class A, you should be able to replace A with B without the program's behavior being incorrect. Now this is not about type compatibility. It's not about whether the code compiles. It is about behavioral compatibility. Will the program work correctly at runtime when the substitution happens? Now, to understand what behavioral compatibility means, a subtype must honor 4 constraints from the parent type. First is that the preconditions cannot be strengthened. If the parent accepts any positive number, the subtype cannot restrict to only even numbers. The subtype must accept at least everything what the parent accepts. Second is the post conditions cannot be weakened. If the parent guarantees a null return value, the subtype cannot return null. The subtype must deliver at least what the parent promises. Third, invariance must be preserved. If the parent guarantees that the balance is always greater than or equal to 0, the subtype must maintain that guarantee. Fourth, there should be no unexpected side effects. So if the parent's save method saves to the database, the subtype save method should not also send an email as a surprise. The caller did not ask for that, and the parent's contract did not promise it. Now, when any of these constraints is violated, code that works correctly with the parent type will break when given the subtype. And the dangerous part is that the calling code has no way to know it's broken because the type system says the substitution is valid. Now the compiler is satisfied, the code review looks clean, but the bug is invisible until runtime. Now LSP is the least intuitive solid principle, and when an interviewer brings it up, they're testing whether you understand the difference between type level compatibility and behavior level compatibility. You should focus your answer on the behavioral contract, not on the type system. LSP violations are tested through concrete examples, and knowing at least 2 examples well is pretty important. The next 2 slides cover the 2 most common ones. Now, this is the most famous LSP example and is worth understanding deeply because it comes up pretty frequently in interviews. Mathematically, a square is a rectangle. Every square has 4 right angles and 4 sides and satisfies every property of a rectangle class. Now, so it seems natural to make the square class extend the rectangle class, but in object-oriented design, that creates a behavior violation. Now, the rectangle class has 2 fields, width and height. It has setWidth and setHeight methods that set each field independently, and it has an area method that returns width multiplied by the height. Now, the square class extends the rectangle because the square must have equal sides. The setWidth method sets both width and height to the provided width value. The setHeight method sets both width and height to the provided height value. This maintains the square's invariant that all sides are equal. Now, let's look at where the substitution breaks. There is a method called resize and verify that takes a rectangle parameter. It sets the width to 5 and sets the height to 10 and then asserts that the area is equal to 50. This works correctly for any rectangle. Set width to 5, set height to 10 and the area is 50. But if you pass the square to this method and then you'll see that something unexpected happens. When set height is called with 10, it also sets the width to 10 because the square overrides the set height to keep both dimensions equal. So the area now becomes 100, not 50. The assertion now fails and the program's behavior is incorrect even though the type system accepted square as a rectangle. So now why does this happen? Rectangle has an implicit post condition setting the height that does not change the width. Square violates that post condition. The calling code relies on that post condition. It expects the width to remain 5 after setting the height, so the substitution breaks. Now the fix is pretty straightforward. Make the rectangle and square separate classes that both implement a shape interface. Neither extends the other. The is-a relationship from mathematics does not translate to a valid is-a relationship in object-oriented programming. The reason is that the behavior contracts differ. Now the mathematical is a relationship is about properties, and object-oriented programming is a relationship is about behavioral compatibility. They are not the same thing. Now the rectangle square problem is useful for understanding the concept, but can feel pretty academic. Let us look at an LSP violation that appears in real production systems and also in interviews. Now let's say we have a repository interface with 4 methods: find by ID, find all, save, and delete. There is a standard repository contract. Any code that accepts a repository reasonably expects all 4 operations to work. Now let's say someone creates a read-only repository that implements this interface. The find by ID and find all method work fine. They query the data source and return the results. But the save method throws an unsupported operation exception with the message that okay, this repository is read only. The delete method does the same. Now, if you think about it, why does this violate LSP? Any code that accepts a repository of T reasonably expects that save and delete would work. The read-only repository compiles fine and passes the type checks, but it throws exceptions for operations that the interface promises to support. If you have a service that loops through a list of repositories and calls save on each one, it will crash at runtime when it hits the read-only instance. The type system said the substitution was valid. It was not. Now the fix for that is here is the interface segregation principle. You split the responsibility interface into two: a readable repository interface with find by ID and find all, a writable repository interface that extends the readable repository and adds save and delete. Now the read-only repository implements the readable repository and generally supports every method it declares. Code that needs to write uses, writable repository. Code that only needs to read uses readable repository. So there are no surprises, no exceptions, and no LSP violations. Now notice something interesting here. Fixing the LSP violation naturally led us to the interface segregation principle. The principle reinforces each other. An LSP violation is often a signal that interface is too broad, and splitting it resolves both problems at once. Now when you see a subclass that throws unsupported operation exception for a parents method in an interview, flag it as an LSP violation and suggest splitting the interface. That two-step response, identifying the violation and proposing the fix, demonstrates the depth. Now LSP violations are particularly dangerous because they pass all the compile time checks. The type system saves the substitution, is valid. The code compiles. The test that uses the parent types pass. The code review looks clean. The bug, however, only appears at runtime, often in a code path that was not tested with a specific subtype. Now let me walk you through how this plays out in a real scenario. Let's say a developer writes code, that uses a repository interface. They test it with the writable repository and everything works. Later, a new term adds a read-only repository for their analytics pipeline. That read-only repository gets injected into the existing service. The service calls save on the read-only repository, and then you get an unsupported operation exception in production, let's say at 2 a.m. Now, each developer's code is correct in isolation. The developer who wrote the original service never anticipated that the repository might not support save. The developer who created the read-only repository never tested in any context where the save is called. Now the bug exists in the gap between the interface contract promises and what the implementation actually does. Now there are 3 warning signs or LSP violations to watch out for. The first is when your subclass overrides a method to throw an exception. The second is when a subclass overrides a method to do nothing with an empty body. The third is when the calling code uses instance of checks before calling a method on the interface type. Now the third sign is particularly telling. If you see code that says, if repo is instance of writable repository before calling save, it means the interface hierarchy is wrong. The type system should prevent invalid calls. Programmers should not need to manually check types before using an interface. When you see instance of checks guarding method calls, that is the type system failing to express the actual contract. Now being able to explain why LSP violations are dangerous, not just define what LSP is, separate candidates who understand solid principles deeply from those who might not do that well in the interviews. So let's practice with another interview scenario here. Let's say you're reviewing a class hierarchy for a file storage system. The base class is file storage with 3 methods: upload, download, and delete. Let's say a teammate has created archive storage that extends file storage, but the delete method throws an unsupported operation exception because the archived files must be retained for compliance. Now let's say the interviewer asks you that, okay, is this a good design and what would you change? Now let's pause for a minute and let's just think about it before diving into the solution. So we'll first start with the weak answer, which is not an ideal answer, and then we'll move to a stronger answer, which is ideally, we should say in the interview. So here's what a weak answer would, let's say the candidate says that, okay, it is fine because archive files should not be deleted. The exception tells the callers not to delete. Now this answer actually entirely misses the LSP violation completely because the calling code does not know it's working with archive storage. A batch cleanup job that calls the delete on the file storage instances will essentially crash on the archive step. However, this is what a strong answer now sounds like. Let's say candidate says that, okay, this violates the Liskov substitution principle because any code that accepts file storage expects delete to work. Archive storage breaks that contract by throwing an exception. The strong answer continues with the fix, which is that, okay, you should actually say that as well, that, okay, you split the interface. Let's say a readable storage interface with a download, a deletable storage interface that extends the readable storage and adds upload and delete. So now archive storage implements only readable storage. Batch cleanup jobs accept the deletable storage, so they can never be passed in archive storage by mistake. The type system prevents the bug instead of relying on the runtime exceptions. Now notice the structure of the stronger answer. It identifies the violation, names the principle, and then explains why it's a problem in practice. And after that, it proposes a concrete fix that uses the time system to prevent the bug. That is a pattern to follow. And this leads us directly into the fourth solid principle, which is the interface segregation principle, or ISP. ISP states that no class should be forced to implement methods it does not use. Also, for example, a quote-unquote file interface is one that bundles many capabilities into a single contract, forcing implementers to provide methods that are irrelevant to the purpose. Now, ISP is pretty closely related to LSP, and we have already seen why. When a class is forced to implement methods it does not need, the most common response is to throw unsupported operation exception or leave the method body empty. Both of those are LSP violations, so ISP prevents LSP violations by ensuring that the interfaces are small enough that every implementer can generally fulfill the entire contract. Now, the fat interfaces create a false promise. They tell calling code that, okay, any object of this type supports all of these operations. So when an implementer cannot actually support all the operations, the calling code has been deceived. It calls a method expecting it to work and gets an exception instead. Now, fat interfaces also create an ongoing maintenance cost. If you add a method to a 15 method interface, every implementing class must be updated, even the ones that have nothing to do with the new method. The interface becomes a tax on every implementer, growing heavier and heavier over time. Now, the goal of the ISP is to design interfaces that are focused on a single capability or a closely related group of capabilities. Each interface should represent a role that an implementer plays, not a collection of everything the system might ever need. Now, the ISP violations show up as large interfaces with 10 or more methods where most implementers only care about, let's say, 2 or 3 of those methods. When you spot this pattern in an interview, suggest splitting the interface by capability. Now let's look at the canonical ISP example. Now consider an office equipment management system. The team defines a single interface for all the machines called office machine. It has 5 methods: print, scan, fax, staple, and copy. So now let's look at what happens when you implement a basic printer. The basic printer generally supports one method, which is print. It sends the document content to the printer driver. The other 4 methods, scan, fax, staple, and copy, all throw unsupported operation exception. 4 of the 5 methods are dead code that exists only to satisfy the interface. Now this is both the ISP violation and also an LSP violation at the same time. The ISP violation is that the basic printer is now forced to implement methods that it does not support. The LSP violation is that calling code expecting an office machine will get exceptions on legitimate method calls. If a service calls scan on what it believes to be a fully capable office machine and it receives the basic printer, then it crashes. Now, the impact actually gets worse over time for the codebase. When a new capability is added to the office machine interface, say email document with a document and a recipient, every implementer must be updated. The basic printer adds yet another method that throws unsupported operation exception. The interface becomes a growing tax on every implementer, requiring changes for capabilities that will never support. Now, the machine interface is the canonical ISP example. You should know it well, but also be ready to show the refactored version with focus interfaces, which is what we will cover next. Now, the fix is to split the fat, bigger office machine interface into focus interfaces, each representing a single capability. So now we define 4 interfaces. The printer interface has one method print, the scanner interface has one method scan, the fax machine interface has one method fax, and similarly the copier interface has one method copy. Now let's look at the implementations here. The basic printer class implements only the printer interface. It has one method print and that method generally works. No exceptions, no empty bodies, and no dead code. Then if we look at the multifunction device class that implements the 3 interfaces, which is printer, scanner, and copier, it provides real implementations for all 3 capabilities. Its copy method even composes the other 2, scanning the document first and then printing it required the number of times. Every method on every class does exactly what it says. Now let's look at the calling code and how that changes. The print service class depends only on the printer interface. It accepts a basic printer, a multifunction device, or any future class that can print. The document archiver class depends only on the scanner interface. Each service declares exactly what capability it needs and nothing more. Now here's a practical guideline for interviews. When you define interfaces in your object-oriented design answer, aim for 2 to 4 methods per interface. If you find yourself defining an interface with, let's say, 8 or more methods, you should ask yourself, okay, are these all part of the same capability or am I bundling unrelated operations? If they are unrelated, split the interface. Now ISP is tested by asking you to design interfaces for a system with different device types, user roles, or service tiers. The interviewer wants to see focused interfaces that represent individual capabilities, not a single interface that tries to describe everything. Okay, now let us cover the 5th and final solid principle, which is the dependency inversion principle, or DIP. Now DIP has 2 parts. First, high-level modules that should not depend on the low-level modules. Both should depend on abstractions. Second, abstraction should not depend on the details. Details should depend on the abstractions. Essentially, in simpler terms, your business logic should never directly reference a specific technology, library, or infrastructure component. Instead, define an interface that represents what you need and let the concrete implementation satisfy that interface. Now let me show you what this looks like without DIP. Let's say we have an order service class that directly depends on 3 concrete infrastructure classes: Stripe payment client, SendGrid email client. The constructor creates all 3 using the new keyword, handwriting the connection strings and the API keys right there in the business logic. Now this creates several problems. The order service is permanently tied to Stripe. Switching to PayPal requires editing the order service class. Writing a unit service for order service requires a live Stripe account and a running PostgreSQL database. The business logic processing orders now is entangled with infrastructure details, payment gateways, email providers, and database drivers. Now let's look at the DIP compliant version. The order service class depends on 3 interfaces: payment processor, notification sender, and order repository. The dependencies are received through the constructor, not created internally. The order service does not know or care whether the payments go through the Stripe or PayPal, whether the notifications go through SendGrid or Twilio, or whether the orders are stored in PostgreSQL or MongoDB. The concrete implementations are injected from outside. Now, DIP is tested every time an interviewer looks at your class diagram's dependency arrows. If arrow points from business logic classes toward the infrastructure classes, you have violated DIP. The arrow should point toward abstractions, so both the business logic and the infrastructure depend on the interfaces. The interfaces own the dependency direction. Now let us work through a complete DIP compliant design for an order processing system. Let's start with abstractions. The payment processor interface has two methods: charge, which takes a customer ID and an amount and returns a payment result, and refund, which takes a transaction ID and also returns a payment result. The order repository interface has three methods: save, find by ID, and find by customer. These interfaces define what the business logic needs without specifying how it's done. Now let's look at the business logic here. The order service class takes a payment processor and an order repository through its constructor. The place order method calculates the total, calls the charge on the payment processor, checks whether the payment succeeded, and if it did, it creates an order and saves it through the repository. Now if the payment failed, it returns a failure result with the error message. The code has zero knowledge of Stripe, PostgreSQL, or any infrastructure detail. It works entirely through the abstractions. Now, if we look at the infrastructure layer here, this is where the concrete details live. The Stripe payment processor class implements the payment processor interface. It wraps the Stripe SDK, calls create charge, and translates the Stripe-centric specific response into a payment result. The Stripe's specific types, Stripe charge, Stripe client, are all contained entirely within this class. They never leak to the business logic. Now let's look at the dependency direction here. The order service depends on the payment processor interface. The Stripe payment processor also depends on the payment processor interface by implementing it. Both the high-level module and the low-level module point toward the abstraction. The abstraction owns the dependency direction. Now, drawing this diagram in an object-oriented interview, design interview with dependency arrows pointing toward the interfaces rather than toward the concrete classes is actually one of the clearest signals of design maturity, and this definitely you should do in your interviews. Now, dependency inversion principle, which is DIPs, its most immediate practical benefit is testability. When business logic depends on interfaces, you can substitute test implementations without needing real databases, real payment APIs, or even real CMS servers. Now let us look at how you test the order service. In the test setup here, you create a fake payment processor and an in-memory order repository. So you inject both into the order service constructor. No network connections are needed, no databases, and no API keys. Now to test a successful order now, you tell the fake payment processor to return a success result for the next call. You create a list of order items and call the place order. Then you assert that the result is successful and that the order was actually saved in the in-memory repository. Now to test a payment failure, you tell the payment, fake payment processor to return a failure result with, let's say, a message like card declined. You call the place order again and assert that the result is not successful and that nothing was saved. Now notice how easy it is to test the failure path. Without DIP, testing a declined card would require either a real declined card from Stripe or complex mocking or HTTP responses. With DIP, it's literally a single line, set next result with a failure. Now, the difference is pretty significant across every dimension. Without DIP, tests need a running PostgreSQL instance. With DIP, tests use an in-memory order repository. Without DIP, tests need a valid Stripe API keys. With DIP, tests use a fake payment processor. Now, without DIP, tests, they will take seconds because of network calls. With DIP, test takes like milliseconds because everything runs in memory. And similarly, without DIP, tests are flaky because sometimes due to network timeouts. With DIP, tests are deterministic and repeatable. So when an interviewer asks you that, okay, how would you test this? They're often indirectly testing, DIP. If your answer requires setting up real infrastructure for a unit test, your design has DIP violations. If your answer is something like, okay, I would inject a mock implementation of this interface, you have demonstrated both DIP compliance and practical testing knowledge. That question, which is, the interviewer just asks you that, okay, how would you test this, is one of the most common follow-up questions in object-oriented design interviews, and DIP compliant designs have an immediate clean answer. Now, there's something you should write down for interviews. These are the 5 solid principles distilled to the essential test for violation. Note this down and you should, recap this before your interviews. So for single responsibility principle, one thing you should remember is that, okay, like the one-line test would be for this principle would be like, how many reasons does this class have to change? If there's more than one, you split it, so you count the chain drivers. For OCP, the one-line test would be like, okay, to add a new type of X, do I modify existing code or add a new class? If you're modifying existing class code or class, you extract an interface. For LSP, the one-line test would be like, okay, can I substitute a subtype without the program breaking? If not, the hierarchy is wrong. For ISP, the one-line test would be like, okay, does any implementer throw unsupported operation exception or leave methods empty? If yes, then split the interface. For DIP, the one-line test would be like, okay, does my business logic class import a concrete infrastructure class? If yes, then you introduce an abstraction. Now, each of these is a one-line diagnostic test. In an interview, when you look at a class or a hierarchy, run through these 5 questions. They will surface most of the design problems. Now, let us connect these to the code smells that you will encounter. So, class with 10 or more methods across different domains likely violates SRP. You split it into focused service classes. A switch or if-else statement on type to decide behavior likely violates OCP. So you extract an interface with one implementation per type. Then a subclass that overrides a method to throw an exception likely violates both LSP and ISP. So for that, you split the interface and adjust the hierarchy. Then a subclass that overrides a method with an empty body likely violates LSP. For that, you remove the inheritance and use the composition instance. Then an interface with 8 or more methods likely violates ISP. You split it into focus, role-based interfaces. So for that, a constructor that creates its own dependencies with new keyword likely violates DIP. So for that, you accept the dependencies through the constructor parameters. Then a business class that imports a database driver or HTTP client likely violates DIP. So for that, you depend on an interface and inject the implementation. Now, if you recognize these 7 code smells during the object-oriented design interview and name the corresponding solid principal violation, you will essentially demonstrate the pattern recognition that interviewers associate with senior level candidates. Practice scanning code for these code smells that we just covered until the recognition kind of becomes automatic for you. Now, this slide gives you a complete mapping from the most common code smells to the solid principle they violate, along with the specific refactoring pattern for each one of them. In an interview, recognizing the smell and naming the fix quickly is what earns a strong hire signal. The first smell, code smell as we would call it, is the God class, which violates this SRP. This is a class with, let's say, 15 or more methods spanning authentication, data access, business logic, and let's say formatting. The refactoring is to identify the chain drivers and extract each one into its own class with the focus interface. The second code smell, as they call it, is the divergent change, which also violates the SRP. This is when you find yourself editing the same class for completely unrelated feature requests. Let's say if someone says that, okay, we need to change the tax calculation, and the other person says that, okay, we need to change the email template. If both the requests from your coworkers both point to the same file, the refactoring, that is the code smell. The refactoring for that is to split the class along, change boundaries. The third code smell is shotgun surgery, which is SRP inverted. A single logical change requires editing 10 or more files, so that means a single responsibility is carried across too many classes instead of being concentrated into few. The refactoring for that is to consolidate the related logic into one class or one module. The fourth code smell is a switch statement on type which violates the OCP. This is a switch or if-else chain that selects behavior based on type string or enum and grows every time a new type is added. The refactoring is to replace it with an interface and polymorphic dispatch. The fifth code smell is the refused bequest, which violates the LSP. A subclass inherits the methods from the parent but overrides them to do nothing or throw exceptions. The subclass is refusing its inheritance, and the refactoring is to break the hierarchy and use composition or split the interface. The sixth code smell is, as we call it, the pair interface, which is violating the ISP. An interface with 10 or more methods where most implementers only use 3-4 of them. The refactoring is to split the interface into smaller role-based interfaces that represent the individual capabilities. The seventh smell is the dependency magnet, which violates the DIB, a class whose constructor creates its own dependencies using the new keyword with concrete classes. This hardwires a class to specific implementations and makes testing impossible without real infrastructure. The refactoring is to accept the dependencies as constructor parameters typed to interfaces. Now, having this meld to principal mapping internalized, lets you answer questions that, okay, how would you improve, when, like, for example, an interviewer asking in the interview that, okay, how would you improve this object-oriented design? So for them, you need to look at these, try to find these code smells in the problem that has been given to the interview. And then you would need to, work your way through and try to suggest the refactoring that we just covered. Now, let us cover the one more complete end-to-end scenario which tests all the 5 principles together. Let's say you're designing a reporting system for an analytics platform like Mixpanel. The system needs to generate reports in multiple formats like PDF, CSV, and Excel. It needs to pull data from multiple sources like PostgreSQL, Elasticsearch, and Redis Cache. And then it needs to deliver reports through multiple channels: email, Slack, webhook, and S3 upload. Now let's say the interviewer asks you in the interview that, okay, walk me through your class design. So how we'll get started and how we'll approach this problem. Now let's pause for a minute and let's think through it before we jump through a solution. Now here's what the interviewer is evaluating. There are 3 independent dimensions of variation: format, data source, and delivery channel. That means 3 interface hierarchies composed together. A single report generator class that handles all 3 violates the SRP because it has 3 chain drivers. OCP because it adds adding a new format requires modifying the class, and then it violates the DIP as well because it directly depends on the PostgreSQL driver, the Elasticsearch client, and the SMTP library. Now let us go through the common solid principle mistakes that show up in the object-oriented design interviews. The first is having one class handle validation, persistence, and notification. That violates SRP. The stronger approach is to have separate classes per responsibility composed by an orchestrator. The second is adding new behavior with if-else branches. That violates the open-close principle. So for that, the stronger approach would be to define an interface and write a new implementation class for each new behavior. The third is having a subclass throw unsupported operation exception, so that violates both LSP and ISP. The stronger approach is to split the interface so the subclass only implements method it generally supports. The fourth is creating a 12-method interface where most implementers leave half the methods empty, so that violates ISP. The stronger approach again would be to split into 3 or 4 more focused interfaces organized by the capability. The fifth very common mistake is having a business logic class create let's say a new Postgres connection directly. That violates the DIP because the stronger approach is to accept a database connection interface through the constructor instead. And the sixth, and this is pretty subtle, is saying that, okay, I use solid principles, but without explaining which principle or why. This gives the interviewer nothing to evaluate, so the stronger approach is to name the specific principle and the specific problem it solves. And here's something important about how to present solid in an interview. Do not just name solid principles unprompted unless the interviewer asks about design principles. Instead, apply them silently through your design decisions. If the interviewer probes and asks you, okay, why did you use an interface here? Then you should definitely name the principle. Saying that, okay, I'm applying OCP here before anyone asks can come across kind of rehearsed, but at the same time, you will still need to say it with the balanced, way, because you need to show that you are applying design principles. So the interviewer recognizes the principle from your reasoning as well. So make sure you also do use the principle in addition to saying that you're using it, but it should be part of your design choices. Now here's a reference card for this entire section. So this slide is essentially designed to be screenshotted and remembered and quickly revised before your interviews. Now let me walk you through the one-line summary for each principle. So SRP, essentially a class should only have one reason to change, meaning one change driver. OCP, adding a new behavior by adding new classes, not modifying existing classes. LSP, subtypes must honor the behavioral contract of the parent type. ISP, no class should be forced to implement methods it does not use. DIP, business logic depends on interfaces, not concrete implementations. And here are the key combinations. SRP at the class level maps directly to service level decomposition in microservices. OCP combined with strategy gives you the multiple types of X pattern, meaning interface plus implementations. LSP combined with ISP means the exception throwing override signal both violations simultaneously, and DIP combined with testability means that the interface dependencies enable the mock-based unit testing. Now let us go through the common mistakes, interview mistakes, and the stronger alternatives. If you say that, okay, this class has a single responsibility because it handles, let's say, users, the stronger version of saying that is that, okay, this class has 3 change drivers: authentication policy, profile rules, and notification delivery. Each should be a separate class. Let's say then if someone says that, okay, I will add a case to switch for the new type. For that, the stronger version would be, okay, I'll write a new class implementing the interface, so no existing code or the class would be need to change. Now let's say someone says that, okay, square extends the rectangle because the square is a rectangle class. However, the stronger version of that would be that, okay, the behavioral contracts differ. Setting height on a square changes width. They should be sibling implementations of a shape interface. Now let's say someone says that, okay, this interface has 12 methods because the system needs all of them. The stronger version of that would be that, okay, not every implementer needs to all 12. So, we'll split into focused interfaces by capability. Now let's say if someone says that, okay, I use the new Stripe client in my order service, instead you should do that, okay, the order service would accept a payment processor interface and Stripe will be injected from outside. For quick violation detection in an interview, here are the 5 key tests. For SRP, count the distinct chain drivers. For OCB, check if adding a new type requires editing existing code. For LSP, check if any subtype throws exceptions or has empty overrides. For ISP, check if any implementer leaves the method unimplemented. For DIP, check if the business logic imports concrete infrastructure classes. Now this section connects directly to what comes next. Section 4 on creational design patterns build on these principles. Factory method is OCP applied to object creation. Builder isolates the construction from representation, which is SRP for construction. And then section 5 on structural patterns, it continues this trend. Adapter pattern enables a DIP by wrapping incompatible interfaces. Decorator pattern enables OCP by adding behavior without modification. And facade design pattern applies this SRP to subsystem access. Similarly, section 6 on behavioral patterns complete the picture. So strategy is the direct implementation of OCP. Observer decouples the event producers from consumers through DIP, and chain of responsibility applies the SRP to request processing. And finally, section 7 on pattern selection ties it all together. So where the solid violation detection tests from this section become the signal to pattern mapping that guides which pattern to apply. Now let's move to the next section, section 4. So in a small code base, creating objects is pretty simple. You call a constructor wherever you need an object and everything just works fine. But as the code base grows, something starts to go wrong. Object creation logic gets scattered across dozens of classes, configuration details gets duplicated, and the code that uses an object becomes tightly coupled to a specific class being created. Now changing how an object is constructed means editing every class that creates it. So creational design patterns actually solve this problem. They control how and where the objects get created so that the rest of your code can depend on abstractions rather than concrete classes. If that sounds familiar, it should. This is the dependency inversion principle from section 3 applied specifically to construction. So in this section, we'll cover 4 creational patterns. First, factory method, which decouples object creation from usage. Second, abstract factory, which creates families of related objects that need to stay consistent with each other. Third, builder pattern, which constructs complex objects step by step when you have many parameters. And fourth, Singleton pattern, where we'll talk about when it's generally appropriate and why it gets sometimes overused more often, which we should avoid as well. Now, where do these design patterns show up in interviews? Let's talk about that for a bit. There are specific signals in the requirements that tell you which creation pattern to reach for. Let's say when the interviewer tells you that, okay, support multiple types of X, that is a factory method signal. Let's say if the interviewer tells you that, okay, these objects must be created together consistently, that points to abstract factory. When you see a class with 8 or more constructor parameters, that is the signal for build a design pattern. And let's say when the requirements by the interviewer says that, okay, we need exactly one instance of X, that is Singleton, but you should also approach it cautiously. And let's say when the interviewer asks you that, okay, how would you add a new type without changing existing code, that is signal for factory design pattern, because it applies the open close principle to object creation. Now, let us start with the pattern you will use most often in interviews, which is the factory design pattern. Now, the factory design pattern, does something pretty straightforward, but still pretty powerful as well. It moves the object creation out of the calling code and into the dedicated method or class. The calling code asks for an object through the factory and receives it through an interface without ever knowing which concrete class was instantiated. Now, let's talk about why does it matter. Think about what happens when the creation logic is spread across the code base. Say you have a notification system, and let's say 15 different classes each call the constructor for the email notification class directly. Now the product team says, let's say that, okay, we need to support push notifications. You have to now go into all the 15 classes and change them. That is 15 files to edit, 15 places where a mistake can happen, and 15 pull requests to review. So now the factory design pattern actually centralizes this decision into one place. The notification service, which is the calling code, never calls the constructor for the email channel directly. Instead, it asks the notification factory for a channel. The factory decides which concrete class to instantiate based on the configuration, user preferences, or business rules. The notification service works entirely with the notification channel interface and has zero knowledge of the concrete implementations behind it. Now, this is a pattern that comes up most frequently among creational patterns in object-oriented design interviews. So interviewers, they use it to evaluate whether you understand the open-close principle applied to object creation. The key idea is that adding a new type means updating the factory, not every class that uses the type. Now, let us look at what happens when you do not use this pattern in the next slide. Now, here's what happens when creation logic lives directly inside the calling code. Now, let's say, for example, if you see on the slide, you have a notification service class and its send notification method has a series of if-else blocks. Now, if the channel type is email, it creates an email client with an SMTP host and port, looks up the user's email address and sends a message. If the channel type is SMS, it creates an SMS gateway with an API key, looks up the phone number and sends a text. If the channel type is push, then it creates a push service with the Firebase key and looks up the device token and sends a push notification. Now, this code has several concrete problems. First, adding a WhatsApp channel, let's say, requires editing this class. That is an open-close principle violation. The class is not closed for modification. Second, the notification service now knows about SMTP ports, API keys, and Firebase configuration. That is a single responsibility principle violation, because the business logic is now mixed with the infrastructure details. Third, you cannot test the notification logic without connecting to real email, SMS, and push services. That is a dependency inversion principle violation. The class depends on concrete implementations rather than abstractions. Fourth, if other classes in the code base also send notifications, they all duplicate this same switch logic. One change to how the email is sent means editing multiple files, and that is a shotgun surgery problem. So this code violates three solid principles at the same time. The factory method fixes all of them in a single refactoring step. So let's see how we do that. And by the way, here's something worth noting for interviewers as well. Interviewers often present code exactly like this and ask that, okay, how would you improve? Now, being able to identify the specific solid violations and propose factory method is a pretty strong response, just exactly what we did in this slide. So now let us refactor that code. The first step is to define an interface. The notification channel interface has a single method send, which takes a user ID and a message. And that is it. Every channel, whether it's email, SMS, or push, implements the same interface. Now the email channel class implements the notification channel. It takes an email client through its constructor, and its sends method looks up the user's email address and sends through the email client. The SMS channel class does the same thing with an SMS gateway. Each concrete class encapsulates its own infrastructure details, The email channel knows about SMTP, the SMS channel knows about SMS gateways, but nothing outside those classes needs to know those details. Now next is the factory. The notification channel factory class holds a map from channel type strings to notification channel instances. Its create method takes the channel type, looks it up in the map, and returns the corresponding channel. If the type is not found, it throws an unsupported channel exception. And here's the result. The notification service class now takes a notification channel factory through its constructor. Its send notification method is 3 lines of code. It asks the factory for a channel, then calls a send on that channel. The notification service knows nothing about email servers, SMS gateways, or push note services. It works entirely through the notification channel interface. Now, adding WhatsApp now means writing a WhatsApp channel class which that implements the notification channel and registering it in the factory's map. 0 changes would be needed to notification service, 0 changes would be needed to the factory class itself, and similarly 0 changes to any existing channel implementation. Now here's one practical note for the interviews. The factory does not always need to be a separate class. A static factory method on the interface itself works for simple cases. What the interviewer is looking for and evaluating is whether the creation logic is centralized and the calling code is decoupled from the concrete types. Now the strongest way to demonstrate this in an interview is to show the before and after. Show the switch statement and then show the factory. That makes it clear that you understand why the pattern exists, not just how to implement it, which is super useful to show and demonstrate in front of the interviewer. Now let us see how the complete factory-based notification system gets wired together at application startup. This is a path that connects the factory to the actual infrastructure. Now the notification module class has a static create method that takes an app config object. Inside this method, we build a map of channel type strings to notification channel instances. The email key, maps to a new email channel, which gets an email client configured with the SMTP host and port from the application config. The SMS key maps to a new SMS channel with an SMS gateway configured with the SMS API key. Similarly, the push key maps to a new push channel with a push service configured with the Firebase key. And then we create the notification channel factory with this map and finally create the notification service with the factory. As you can see, all the infrastructure knowledge, the SMTP host, the API keys, the Firebase configuration, they all live in the one module. The notification service and the factory know nothing about those details. Now, what happens when the product team asks for, let's say, WhatsApp support? Step 1, we write a new WhatsApp channel class that implements the notification channel. It takes a WhatsApp client through its constructor and it sends a method. It sends method looks up the phone number and sends through the WhatsApp client. Step 2, we add one line to the configuration module. We register the WhatsApp key with the new WhatsApp channel instance configured with the WhatsApp API key from the app config. So that's it. Those are the 2 changes total. One new class file and one new line in the configuration module. The notification server itself is untouched. The notification channel factory is untouched. And every existing channel implementation is also untouched. Now walking through this add a new type scenario step by step is one of the strongest moves you can make in an interview to demonstrate the open-close principle compliance. Count the files unchanged and state it explicitly in front of the interviewer. Okay, one new file and one new line in configuration. 0 change in existing code. And that precision exactly is a very strong higher signal in front of the interviewer. So now that we understand factory method, let's talk about what happens when you need to create not just one object, but a set of related objects that must work together. Now, the abstract factory pattern creates families of related objects that need to be used together consistently. While factory method creates one type of object, abstract factory creates a coordinated group. Now here's a concrete example. Consider a UI component library that supports multiple themes. You have a material theme and a fluent theme. Each theme defines its own version of buttons, text fields, and dropdowns. A material theme produces material style components. A fluent theme produces fluid style components. And here's the key constraint. Mixing a material button with a fluid dropdown looks broken. The components within a theme must be created together. Now here's the structure looks like. We define a UI component factory interface with 3 methods. create button, create text field, and create dropdown. Then the Material UI Factory class implements this interface, and each of its creation methods return the material version of the component. The Fluent UI Factory class does the same thing but returns the Fluent versions. Now the calling code, in this case a form renderer class, takes a UI component factory through its constructor. When it builds a login form, it calls the component factory.create button for the submit button, component factory.create text field for the email and password fields. The form renderer does not know which theme is active. It creates components through the factory, and the factory guarantees that all components belong to the same theme. Switching from Material to Fluent means injecting a different factory. Zero changes to the form renderer. Now, the abstract factory shows up less frequently in interviews than let's say the factory method, but when it does, it appears in questions involving themes, platform-specific rendering, or environment-specific configurations like development versus staging versus production. Now let us look at the complete object hierarchy for the UI component system, because understanding the structure helps you draw it quickly in an interview. Now as you can see at the top, we have the UI component factory interface. Below it has two concrete factories, Material UI Factory and Fluent UI Factory. Then we have separate interface hierarchies for each component type. The button interface has Material button and Fluent button implementations. The text field interface has Material text field and Fluent text field implementations. Each factory creates components exclusively from its own family. The Material UI factory creates the Material button and Material text field. The Fluent UI factory creates the Fluent button and Fluent text field. Now, the calling code depends only on the interfaces, UI component factory, button, and text field. It never references any concrete class, and this is what makes the pattern work. Now, here's a question that comes up pretty often. When do you use factory method versus abstract factory? Let us be more precise about the difference. So factory method creates one type of object. It has one creation method. It solves the problems of, which concrete class should I instantiate? Abstract factory creates a family of related objects. It has multiple creation methods. It solves the problem of essentially, which family of classes should I use together? Factory method guarantees you get the correct single object. Abstract factory guarantees that all objects come from the same family. And the complexity of abstract factory is much higher because of the multiple interfaces and implementations involved. So the decision rule is this. Use abstract factory when objects must be created as a consistent group, and mixing objects from different groups would produce incorrect behavior. If each object can be created independently without consistency concerns, use the individual factory methods instead. Now here's a practical guideline for interviews. Do not reach for abstract factory unless you clearly see the family of related object signal. Using abstract factory for a single object type adds complexity without benefit, and interviewers will recognize that as over-engineering. The question to ask yourself is that, do these objects need to be consistent with each other? If the answer is no, factory method is sufficient. Now let us work through a practice scenario. So let's say you're designing a document generation system for a platform like, let's say, DocuSign. Now the system creates documents in multiple formats, which is PDF, Word, and HTML. Now each format requires a header renderer, a body renderer, and a footer renderer that is specific to that format. Now let's say the interviewer asks you that, how would you structure the creation of these renderers? Now let's pause for a bit and let's think through it before we dive into the solution. So I'll first cover the weaker version of the answer that is not ideal to give in the interviews, and then we'll switch to what a strong answer would look like. So a weak answer would sound something like, let's say a candidate says that, I would use a factory method that takes a format string and returns a renderer. Now this answer misses the core problem. There are 3 renderers per format, header, body, and footer, and they must be consistent. A PDF header renderer must be paired with a PDF body renderer and a PDF footer renderer. A single factory method returns one object, not a coordinated set. If you use 3 independent factory methods, there is nothing preventing someone from mixing a PDF renderer, header renderer with the HTML body renderer, and that combination would produce broken output. Now let's see what a strong answer version would look like. So essentially a stronger answer version would recognize that the family of related objects is a signal. So since each format requires a consistent family of renders, header, body, and footer, I would use Abstract Factory. A document render factory interface defines three methods: create header render, create body render, and create footer render. The PDF render factory class implements this interface and creates all three PDF specific renders. The HTML render factory creates all three HTML specific renders. And the document generation service depends on the document render factory interface. Switching formats now means injecting a different factory, so the service never mixes renders from different formats because the factory guarantees the consistency. Now, notice what makes a strong answer strong. It identifies the signal, that is, family of related objects. It names the correct pattern, and it explains why factory method alone would not be sufficient for this particular problem. Now let us move to a different kind of creation problem. So far with factory method and abstract factory, the question has been, okay, which type of build object should I create? Now with builder pattern, the question is different. How do I construct an object that has many parameters, most of which are optional? Now, the builder pattern separates the construction of a complex object from its representation. It is the right pattern when the valid combinations of parameters are too numerous to handle with construction overloading. So now, when is the builder pattern appropriate? So when an object has more than 4 or 5 constructor parameters, many of which are optional, and the order in which you specify them does not matter, that is when you use builder. The classic example is any configuration object, query object, or request object with a mix of required and optional fields. Now let us look at a concrete example. Let's say there is a search query class with 7 fields: the search term, the maximum number of results, the sort order, a list of filters, a from date, a to date, and whether to include the archive results. Of these, only the search term is required. Everything else is optional with sensible defaults. Now, the builder is implemented as a static inner class. The builder constructor takes only the required parameter, the search term. Then each optional parameter has its own method that sets the value and returns the builder itself, enabling the method chaining. The max results method sets the max results and returns the builder. The sort order method sets the sort order and returns the builder. The add filter method adds filter to the list and returns the builder, and so on. Finally, the build method, creates the search query by passing the builder to the private constructor. Now, the usage code over here, it reads like a specification. You create a new search query.builder with a search term, let's say system design, and then chain calls: max results 50, sort order date, add filter as category, engineering, date range from January 2025 to let's say now, and included archive as true, and finally build. Each method call is self-documenting, so the reader knows exactly what each parameter means without checking the parameter positions. And if you do not need a particular option, you simply just do not call that method. Now, builder shows up in interviews when you design objects with many configuration options. What the interview evaluates is whether you recognize the too many constructor parameters signal and reach for builder instead of telescoping constructors. And that brings us to the question: what exactly are telescoping constructors and why are they a problem? Now, the telescoping constructor is a problem that builder solves. It happens when a class needs to support many combinations of optional parameters and the developer creates multiple constructor overloads to handle them. Here's what it looks like with our search query class. The first constructor takes just the search term and delegates to the next one with a default max results of 20. The second takes the search term and max results, then delegates to the next one with a default sort order of relevance. The third takes 3 parameters and delegates to the fourth. This continues until you reach the final constructor with all 7 parameters. Now there are specific problems with this approach. First, parameter position confusion. When you see a call like new search query with arguments design, 50, sort order.date, a filters list, null, null, true, you have to remember that true is the 7th parameter and it means include archive. There is nothing in the code itself that tells you what that true means. Second, as you can see, you cannot skip optional parameters. If you want to set include archive to true, but you do not need a date range, you still have to pass null and null as placeholders for the from date and the to date. And the third reason is every new optional parameter requires a new constructor overload. the number of constructor grows linearly with the parameter count. And fourth reason why this is harmful is that the code at the call side is unreadable. A constructor call with 5 null values gives no indication of what each null represents. Now, with 7 parameters, there are 127 possible combinations or optional values. Telescoping constructors cannot handle this without an explosion of overloads. Builder handles all 127 combinations with a single clean API. Now, recognizing this anti-pattern and proposing Builder as a solution demonstrate that you understand when patterns solve real problems rather than just adding unnecessary abstraction. Here is a Builder that goes a step further. It enforces validation rules during construction, which connects it back to encapsulation from section 2. The idea is that an invalid object can never exist. The user profile class has 9 fields: user ID, display name, email, bio, avatar URL, preferred language, time zone, email notifications enabled, and profile public. 3 of these are required, which are user ID, display name, and email. The rest are optional with sensible defaults. Bio defaults to an empty string, preferred language defaults to English, time zone defaults to UTC, and email notifications default to enable, and profile visibility defaults to public. Now the builder constructor takes the 3 required parameters and validates them immediately. If the user ID is null or blank, it throws an illegal argument exception with the message user ID is required. If the email is null or does not contain an, let's say, @ symbol, it throws an illegal argument exception with valid email is required message. The optional methods, they also validate the inputs. So the bio method checks the bio does not exceed 500 characters. Now the usage is pretty clean. You create a new user profile.builder with the user ID, display name, and email. Then you change the optional methods bio, time zone, email notifications, and then you call build. And if you try to create a user profile without a user ID, the builder stops you at the constructor. If you try to set a bio longer than the 500 characters, the bio method stops you right there. The result is that every user profile object that exists in the system is guaranteed to be valid. Required parameters are enforced by the type system through the builder constructor. Optional parameters have sensible defaults, and the validation happens during the constructor, not. Now, here is a practical tip for the object-oriented design interviews. When you use builder in your class design, you put required parameters in the builder constructor and optional parameters as chain methods with defaults. This shows the interviewer that you understand the distinction between mandatory and optional fields and that you are using the type system to enforce it. So now builder pattern, it adds a real amount of boilerplate code. You need an inner class, chained setter methods, a build method, and a private constructor on the outer class. This cost is justified only when the object is genuinely complex. So let us be more specific about when to use it and when not to use it. Now, builder is pretty essential in typically 4 situations. First, when the object has 5 or more parameters with many optional combinations. Second, when there are validation rules that span multiple fields, for example, an end date that must come after a start date. Third, when the object should be immutable once constructed, meaning all fields are finals with no setters. And fourth, when the same construction process needs to create different representations. Now, builder is overkill in 3 situations. First, when the object has 2 or 3 parameters that are all required. Second, when there are no optional fields with or variant configurations. Third, when a simple constructor is already clear and readable. Now, the decision comes down to the parameter count and the presence of optional fields. For 1 to 3 parameters with no optional fields, use a simple constructor. For 3 to 4 parameters with 1 or 2 optional fields, constructor overloading can work if it is clear, but builder is also reasonable. For 5 or more parameters with 2 or more optional fields, builder is the right choice. And regardless of parameter count, if you need cross-field validation or immutability guarantees, builder earns its place. Now, a common mistake in interviews is using builder for a class with 2 required fields and no optional fields. That adds 30 or more lines of boilerplate code for pretty much zero benefit. The interviewer will recognize that essentially as over-engineering. Now, knowing when not to use a pattern is as valuable as knowing how to use it. If an interviewer asks you that, okay, would you use builder here for a simple 2-field class The correct answer is no. A simple constructor is sufficient there. Now let us work through another practice scenario. Let's say you're designing an HTTP request class for an HTTP client library. An HTTP request has a URL which is required, an HTTP method which is required, headers which are optional and they can be 0 or more of them, a request body which is optional, a timeout in milliseconds which is optional with a default of 30,000, and a retry count which is optional but with a default of 3. Now let's pause the video for a bit and let's think through this problem before we dive into the solution. I'll first give the weaker version of the answer and then I'll move to the stronger version of the answer, which you should say, go through in the interview. So here's the weaker version of answer, what it looks like. A constructor that essentially take all 6 parameters. The problem is that the URL and method are required, but the headers, body, timeout, and retry count are optional. A caller who just wants to make a simple GET request still has to write something like a new GET request, http api.example.com, get null 30,000 and 3. Essentially, that call is pretty unreadable. And you cannot tell what null and 30,003 mean without checking the constructor's signature. Now, here's what a strong answer looks like. It uses a builder pattern. So the builder constructor, takes the 2 required parameters, URL and HTTP method. Headers are added one at a time with add header method. The body is set with the body method. The timeout is set with timeout ms method, and retry counts default to 3, so it does not need to be specified for most requests. And then the build method can just enforce the validation rules, like ensuring that a post request has a body while a get request does not. Now the resulting code reads pretty clearly. You create a new http request.builder with the URL and http.method.get, chain the add header calls for authorization and content type, set the body, set a custom timeout of 5000 milliseconds, and call build. Every parameter is named, nothing is ambiguous now. So a Singleton pattern ensures that a class has exactly one instance and provides a global point of access to it. It is simple to implement, and which makes it tempting to reach for, but it comes with real trade-offs that are worth understanding clearly. Now let us start with when Singleton is generally appropriate. Singleton makes sense when creating multiple instances would cause correctness or resource problems. Connection pools are a good example. So if you create multiple pools to the same database, each pool opens its own set of connections, which wastes connections and can bypass the pool size limit you configured. Configuration registries are another example. Application configuration that is loaded once from a file or environment variable should not be repassed by every class that needs a setting. Then hardware interface controllers like a printer spooler that maps to a single physical resource are a third example. In each of these cases, the exactly one instance constraint is a correctness requirement. Now, when do the Singleton pattern gets overused? Developers often reach for Singleton when they want a class to be easily accessible from anywhere in the codebase. But that is using Singleton as a replacement for dependency injection, and it creates specific problems. First, hidden dependencies. A class that calls, let's say, database pool.getInstance inside its methods has a dependency on database pool that does not appear in its constructor. Anyone reading the constructor signature has no idea this class uses a database pool. Second, tight coupling. Every class that uses a singleton is coupled to the concrete implementation, which violates the dependency inversion principle. Third, testing difficulty. You cannot substitute a mock in unit test because the singleton controls its own lifecycle. Fourth, shared mutable state. Global state exists from multiple threads create concurrency bugs that are difficult to reproduce and debug. Now here's a practical rule of thumb. If the reason for using singleton is, I need easy access to this object, the real solution is dependency injection. If the reason is, let's say creating 2 instances would cause a bug, singleton may be appropriate. Now in interviews, singleton is often used to test whether you understand its trade-offs. Saying that, I would use singleton for a database connection pool is a reasonable answer. Saying that, I would use a singleton for the user service signals a gap in understanding because the user service has no correctness reason to be limited to a single instance. Now let us look at the implementation details, starting with the naive approach and why it breaks in multi-threaded environment. So the naive implementation, which is not so good, essentially has a private static field for the instance initialized to null. The getInstance method checks if the instance is null. If it is, the method creates a new instance and assigns it. Then it returns the instance. This looks correct in a single thread program, but it fails with multiple threads. If two threads call getInstance at the same time when instance is null, both threads pass the null check and both threads create a new instance. Then the second instance assignment overrides the first. So any thread holding a reference to the first instance now has a stale object that may be in an inconsistent state. Now there are essentially four common approaches to solve this. First, the synchronize method approach. You add the synchronize keyword to the getInstance method. That is simple and correct, but every call to getInstance pays the synchronization cost even after the instance has already been created. Second, double check blocking. You check if the instance is null, then synchronize, then check null again, then create. This works correctly only if the instance field is declared volatile. Third, eager initialization. You assign the instance directly in the field declaration private static final connection pool instance equals new connection pool. This is simple and thread safe, but the instance is created when the class loads, even if it is never used. Fourth, the enum approach. You declare the singleton as an enum with a single value call instance. This is the approach recommended by Joshua Block. So the JVM guarantees that the enum values instantiate exactly once in a thread-safe manner, and they are immune to reflection-based attacks that can bypass private constructors. So the enum approach in Java is worth knowing for interviews. The connection pool enum has a single value instance. Its constructor initializes the connection list. The acquire and release methods are synchronized to handle concurrent access to the pool. But regardless of which thread safety approach you choose, there is a fundamental problem that remains. Singleton makes unit testing difficult. A test that calls connection pool.getInstance cannot substitute a mock. The test either needs a real connection pool, which makes it slow and fragile, or it must use reflection to reset the static field between tests, which is brittle. This is the fundamental tension with Singleton. It trades testability for global access. Now, if you use Singleton in your interview answer, mention the thread safety consideration and the testing trade-off proactively. This shows the interviewer that you understand the cost of the pattern, not just the mechanics. So if Singleton has these testing and coupling problems, what is the alternative when you genuinely need a single instance of the class? The answer is dependency injection. So let us compare the two approaches side by side. In the Singleton approach, the order service class calls connection pool.getInstance directly inside this place order method. It gets the connection, executes the SQL statement, and releases the connection. However, the problem is that the order service has a hidden dependency on connection pool. Nothing in the constructor tells you this class uses a connection pool, and there is no way to substitute a different pool for testing. Now, in the dependency injection approach, the order service class takes a connection pool through its constructor and stores it as a field. The place order method uses this as an injected pool. The code inside the method is nearly identical, but the way the pool is provided is fundamentally different. The wiring happens at the application startup in what called the composition route. The main method creates a single connection pool instance, creates an order repository with the pool, creates a payment processor, creates an order service with the pool, and starts the web server. The connection pool is created once, which means it's effectively a singleton in behavior. But it is passed explicitly through constructors. Every class declares the dependencies visibly. Test can now inject a fake connection pool. There is no global state and there is no hidden coupling. Now, there are cases where Singleton remains pragmatic. So if the class is generally infrastructure level, like a logging framework or a metrics collector, and injecting it through 50 or more constructors would add noise without real benefit, Singleton is a reasonable choice. But for business logic dependencies, dependency injection is a stronger approach. Now, here's a phrasing that works well in interviews. If the interviewer asks you that, okay, should this be a singleton, you can say that, okay, I would create one instance at startup and inject it through constructors. This gives you the same single instance behavior with the added benefit of testability. That response demonstrates that you understand the trade-off and that you are choosing the approach that gives you more flexibility. Now, this is something you would want to write down just for your notes for your interview prep. These are the signals in a requirement description that tells you which creational design pattern to reach for. So when the requirements say that, okay, create objects of different types based on configuration or input, the pattern is factory method. The reason is that factory method decouples the creation decision from the calling code. Let's say when the requirements say that, okay, create a set of objects that must be consistent with each other, the pattern is abstract factory. The reason is that abstract factory guarantees family consistency. When the requirement describes an object with 5 or more parameters and many of them are optional, the pattern is builder. The reason is that builder avoids telescoping constructors and provides self-documenting construction. When the requirements describe an object that needs cross-field validation during construction, the pattern is also builder. The validation happens in the build method, which rejects the invalid states because the object is created. When the requirements say that, okay, exactly one instance for correctness reasons, the pattern is singleton, but used cautiously. Example includes connection pools and hardware controllers. And here's a signal that catches people. When the requirement says that, okay, I need global access to a shared service, the answer is not singleton. The answer is dependency injection. Dependency injection gives you the testability, visible dependencies, and loose coupling, all of which singleton sacrifices. And there are 3 questions that will guide your choice. First, how many types? If the answer is multiple types determined at runtime, use factory method. Second, how many parameters? If the answer is 5 or more with optional combinations, use builder. Third, how many instances? If the answer is exactly 1 for correctness, consider singleton, but do prefer dependency injection. Now use the decision tree when choosing a creation pattern in an interview. It starts with one question, which is, does the object creation involve multiple types determined at runtime? If yes, ask the follow-up question. Must these objects be created as a consistent family? If yes, use abstract factory. If no, use factory method. Now, if the first answer was no, meaning there's only one type, the next question is, does this object have 5 or more constructor parameters with optional fields? If yes, use builder. If no, ask if, is exactly one instance required for correctness. If yes, consider singleton or prefer dependency injection. If no, a simple constructor is the right approach, so no pattern is needed. Now, this tree takes roughly about 10 seconds to walk through mentally and gives you a justified answer every time. Now, creation patterns are often used in combination. A factory method might use a builder internally to construct complex objects. The factory decides which type to create, and the builder handles the detailed construction of that type. An abstract factory might return singletons for components that are expensive to create. The factory itself might be a singleton because you typically need one factory per theme or platform. Factory methods frequently create strategy objects, which we'll cover in section 6 on behavior patterns, and a builder's build method can force cross-field invariance, which means builder and validation go hand in hand. Now, having this decision tree internalized means you can justify your creation pattern choice quickly during an interview. Now let us walk through one final practice scenario that brings everything together in the section we have covered. Let's say you're designing a logging framework for a platform like Datadog. The framework supports multiple output destinations, console, file, and remote server. Each destination has a different configuration options. The console destination needs a color scheme, the file destination needs a path and a rotation policy, and the remote destination needs a URL and authentication token. The logger itself should exist as a single instance per application. And now let's say the interviewer asks you that, okay, walk me through your class design for creating these loggers. Now let's pause for a minute and just think deeply before we we cover the solution. Now here are the key design decisions. The output destinations are different types, created based on configuration. That is a factory method signal. Each destination has different construction parameters, and the file destination has 4 or more optional fields: path, rotation size, rotation count, and compression. That is a builder signal, specifically for the file destination class. The logger being a single instance is a singleton signal, but dependency injection is a stronger approach. A strong answer combines 3 patterns: factory method to create destination instances based on configuration, builder for the complex file destination class because it has multiple optional fields, and dependency injection, not singleton, for the logger instance. You create one logger at the startup and inject it where needed. Now let's look at the common mistakes for creation patterns and what the strong alternatives are. Using singleton for every shared service create hidden dependencies and block testability. The stronger approach is dependency injection through constructors. Using builder for two-field class add 30 or more lines of boilerplate for no benefits. A simple constructor is sufficient. Using factory method when there is only one type adds unnecessary interaction, so a direct constructor call is simpler and much more clearer. Putting creation logic in the calling class violates the single responsibility principle. The solution is to extract it into a factory. Using abstract factory when the objects are independent adds complexity without the consistency benefit. Individually factory methods are the right choice there, and making sure that every class a singleton just in case leads to a global mutable state, so you should avoid doing that because it also causes testability problems. The approach is to create once and inject everywhere. So these mistakes map directly to over-engineering and under-engineering signals that interviewers evaluate. Patterns should solve specific problems, not be applied as a default practice. Now here's a reference card for this entire section. The slide is essentially designed to be covered before interviews for a quick recap for the whole section. Essentially in this section we covered 6 areas. Factory method centralizes object creation behind a factory, decoupling callers from concrete types. Abstract factory creates families of related objects that must be used together consistently. Builder constructs the complex objects step by step with optional parameters and validation. Singleton ensures exactly one instance, but dependency injection is preferred for most use cases. The telescoping constructor is an anti-pattern where constructor overload grows to the point where the code becomes unreadable, and builder pattern is a solution. And the registry or dependency injection pattern is the alternative to Singleton pattern that provides testability and visible dependencies. Now for interviews, there are common mistakes to avoid and stronger phrasings to use instead. Instead of saying that I use Singleton because the service is shared, you should say that I created one instance at startup and injected it through the constructors for testability. Next, instead of saying that I use builder for the user class when it only has 2 required fields, you should say that a simple construct is sufficient here. Builder is for objects with many more optional patterns. Next, instead of saying that I put the creation switch in order service, you should say that I extracted a factory, so order service depends on the interface, not the creation logic. And next, instead of saying that I use abstract factory for creating notifications, you should say that since notification channels are independent and not a consistent family, factory method is sufficient. Now, the recognition signals to remember are multiple types determined at runtime means factory method, and the justification is adding a new type means writing one new class and updating the factory. Objects must be consistent as a family. When you hear that phrase in the interview, that means abstract factory, and the justification for that is that the factory guarantees all components belong to the same theme or platform. And when you hear in the interview that 5 or more parameters with optional combinations, that means builder pattern, and the justification is that the builder provides self-documenting construction and validates the invariants. And if you hear in the interview that exactly one for correctness phrase, that means Singleton, and the justification is that I prefer dependency injection for the same single instance behavior with better testability. Now this section connects directly to what we have covered and what is ahead in our course. Creational patterns build on the polymorphism from section 2 and the solid principle from section 3. Factory method relies on polymorphism. Builder protects the encapsulation. Factory method implements the open-close principle for object creation. Builder applies the single responsibility principle by separating the construction from the object itself, and choosing dependency injection over Singleton applies the dependency inversion principle. Now looking ahead, structural patterns in section 5 will use factories to create objects that get wrapped by adapters or decorators. Behavioral pattern in section 6 will use factory methods to create strategy objects, and the pattern selection framework in section 7 will bring together all the recognition signals from every section into one unified reference. In the previous section, we covered creational patterns. So those patterns solve a specific category of problem, which is how objects get created. How do you create objects without coupling your code to concrete classes? How do you ensure only one instance exists? And how do you construct complex objects step by step? So this is all we covered in the previous section, section 4. Now, structural patterns, they solve a different category of problem. They address how objects and classes are composed to form larger structures. Specifically, they answers questions like, how do you connect two classes that were never designed to work together? How do you add behavior to an object without changing its source code? And how do you take a complex subsystem with 6 or 7 moving parts and give callers a clean, simple entry point? These are the problems that come up constantly in real-time systems. Every time you integrate with a third-party API, every time you add logging or caching to an existing service, every time you build a workflow that, let's say, coordinates multiple services, you are dealing with structural design problems, and they are very important for building production systems. Now, in this section, we'll cover 4 structural patterns. So the first one will be adapter, which lets you integrate with incompatible interfaces without modifying either sides. The second is decorator, which lets you add behavior dynamically without creating subclass hierarchies. The third is facade, which simplifies complex subsystems behind a clean single entry point. And the fourth is proxy, which controls access to objects for purposes like lazy loading, caching, and authorization. Now, where do these show up in object-oriented design interviews? Let's talk about that. Let's say if the interviewer says that, okay, integrate with third-party API that has a different interface, that is an adapter signal. If they say that, okay, add logging or caching without modifying the core class, that is decorator pattern. And if they say that this subsystem has 6 services and let's say simplify the API, they said that is a facade pattern. And let's say if the interviewer says that, okay, controlled access to this expensive resource, that is proxy. Now there is also a second adapter signal, which is, let's say if the interviewer says that, okay, we might swap this external dependency later on. Adapter isolates your code from that change. Now these signal to pattern mappings are worth committing to your memory. In an interview, recognizing the signal quickly lets you move to the design phase instead of spending time deciding which pattern to use. Now let us start with adapter pattern. So the core problem adapter design pattern solves is pretty simple. Your code depends on an interface, but the concrete implementation you would want to use does not match the interface. The method names are different, the parameter types are different, and the return types are different as well. Now, you cannot modify the external implementation because it belongs to a third-party library or a legacy system, and you should not modify your own interface just to match someone else's API because that couples your entire codebase to their design decisions. Now, the adapter sits between your code and the incompatible implementation. It implements your interface and internally translates calls to the external implementation. Think of it like a power adapter when you travel. The wall outlet might be in a different country, which will have a different shape, but the adapter lets your device plug in without rewiring anything on the either side. Now let us look at the structure with a concrete example. Say you have an order service class that depends on a payment processor interface. That is your interface designed to match your domain. Now let's say you would want to, use Stripe for payments, but the Stripe client class has completely different method signatures. Now, the Stripe adapter sits in the middle. It implements the payment processor and internally it holds a reference to the Stripe client. When the order service calls a method on the payment processor, the adapter translates that call into the corresponding Stripe method call. Now, here's something worth connecting back to what we covered in section 3. Adapter is a direct application of the dependency inversion principle. So, in business logic, the order service depends on your own abstraction, the payment processor interface. It never knows that Stripe exists. If Stripe changes the SDK tomorrow, you update the adapter. Your order service and every other class that depends on payment processor remains completely untouched. Now, in an object-oriented design interview, adapter appears anytime the question involves third-party integrations. The interviewer is evaluating whether you isolate your code from external dependencies using your own interface or whether you couple directly to the third-party API. Wrapping the external dependency behind an adapter is the exact approach. Now let us walk through a full worked example to see exactly what the adapter does at the code level. Now let's say your system defines a payment processor interface with 2 methods. So the charge method takes a customer ID as a string and a money object and returns a payment result. The refund method takes a transaction ID and a money amount and it also returns a payment result. This is your interface designed around your domain concepts. Now Stripe's SDK looks completely different. Their create charge method takes the amount as long in cents and a currency as a string and a customer token which is Stripe's internal identifier for the customer. Their create refund method takes a charge ID and an amount in cents. They return their own types, which is stripe charge and stripe refund. So now every single parameter and return type is different. Your system uses a money object, Stripe uses cents as a long, your system has a customer ID, Stripe uses customer token, your system returns a payment result, and Stripe returns a Stripe charge. These are three distinct categories of mismatch that the adapter needs to handle. Now, the Stripe payment adapter class implements your payment processor interface and holds references to the Stripe client and a customer token resolver. In the charge method, the adapter first resolves a customer ID to a Stripe customer token using the token resolver. Then it converts the money object to cents by calling amount2.cents, extracts the currency code, and calls Stripe's createCharge method with those translated parameters. Finally, it maps the Stripe charge response back to your payment result type and using a private helper method. Now the refund method follows the same pattern. It translates the parameters into Stripe's expected format, calls the Stripe method, and maps the response back. Now there's also a status mapping method that converts the Stripe string-based status values like succeeded and pending into your own payment status enum values like completed and pending. This is a detail that is easy to overlook, but it matters. Your domain should not depend on the string values that a third party chooses for their own statuses. The result is that the order service sees only the payment processor interface. It passes in a customer ID and a money object and gets back a payment result. It has zero awareness that Stripe exists behind the scenes. Now, in an object-oriented interview, walking through these specific translations, data format conversion, identifier mapping, and return type mapping shows the interviewer that you understand the mechanical work that an adapter design pattern performs. It's not just a structural diagram, it is a set of concrete translation responsibilities. Now, adapter design pattern is not only for third-party libraries. It is equally valuable when integrating with legacy internal systems. This is a scenario that comes up frequently in real production environments, and it also appears in object-oriented design interviews as well. Now consider a modern order management system that needs to read customer data from a legacy CRM. This CRM was, let's say, built years ago. It uses a SOAP-based API, for example, with its own identifier scheme and its own data transfer objects. Now let's say the company wants to replace it eventually, but that is a multi-year migration. In the meantime, your modern system would need to work with it. The legacy CRM client has methods like getCustomer by SOAP ID, which takes a SOAP-specific customer ID, and updateCustomerAddress, which takes a SOAP-specific address object. Your modern system defines a customer repository interface with methods like findById, which takes a standard string ID and returns an optional customer, and updateAddress, which takes your own address object. The legacy CRM adapter implements your customer repository interface. In the findById method, it first maps your customer ID to the legacy SOAP ID using a customer ID mapper. Then it calls the legacy client's method, checks if the response indicates not found, and if the customer exists, map the SOAP response to your customer domain object. The updateAddress method does a reverse translation. It converts your address object into a SOAP address and calls the legacy method. Now the real value of this approach becomes clear when you think about what happens when the company finally replaces the legacy CRM with the modern REST API. You write a new adapter that implements the same customer repository interface but translates to the new REST API instead of the SOAP API. Every class in your system that depends on customer repository is completely untouched. You swap the adapter in your dependency injection configuration, and the migration is done from the perspective of all calling code. Now, this is what adapter design pattern does at a practical level. It creates a seam between your code base and the systems you cannot control, or the systems that are changing on a different timeline than yours. In an object-oriented design interview, when you integrate with an external or legacy system, wrap it in an adapter behind your own interface, and then you state explicitly in front of the interviewer that, okay, I'm wrapping the external dependency so that if it changes, only the adapter needs to be updated. That single sentence demonstrates both adapter pattern knowledge and dependency inversion principle compliance. Now let us move to the decorator pattern. So decorator pattern solves a fundamentally different problem for adapter pattern. Adapter pattern is about translating between interfaces. Decorator pattern is about adding behavior to an existing object without modifying it. Now here's the setup. Imagine you have a data storage service. The basic version reads and writes data to the files. Now the requirements grows. Okay, now you need to add logging for every operation. You need to compress data before storing it, and let's say you need to encrypt sensitive data as well. These are all optional capabilities. Some deployments, they need all three. Some need just logging, and some need encryption but not compression. Now, if you try to solve this with inheritance, you would need a separate class for every combination of behaviors. A logging file data store, a compressing file data store, an encrypting file data store, a logging compressing file data store, and so on. We'll look at the exact math on the next slide. Now, Decorator Pattern avoids this entirely. Each behavior gets its own class, the logging decorator, the compressor decorator, and the encryption decorator. Each of these classes implements the same data store interface as the base file data store, and each one holds a reference to another data store, which is the object it wraps. This means decorators can wrap the base implementation directly, or they can wrap other decorators. You can put a logging decorator around a compression decorator around an encryption decorator around a file data store. The chain is assembled at the runtime, not locked in at compile time. You decide which behaviors to stack based on the deployment context, the configuration, or even the specific request. The key structural requirement is that every decorator implements the same interface as the object it wraps. This is what makes them composable. The calling code does not know whether it's talking to a plain file data store or a 3-layer decorator chain. It just calls methods on the data store interface. So let's say now when the interviewer asks you that, okay, how would you add cross-cutting concerns like logging or caching without modifying the core class? Decorator is the answer, not inheritance. So yeah, keep that in mind. Now let us put concrete numbers of why Decorator Pattern is the right tool for combining behaviors and inheritance is not. Take one base class, file data store, and 3 optional behaviors, logging, compression, and encryption. With inheritance, you need a subclass for every possible combination. No behaviors is the base class. Each single behavior is one subclass, so that is 3. Each pair of behaviors is another subclass, so that is 3 more. All 3 behaviors together is 1 more, so that is total 7 subclasses. Now add a 4th optional behavior, say caching. The number of combination doubles, so you go from 7 subclasses to 15. This growth follows the formula of 2 to the power of n minus 1, where n is the number of optional behaviors. With 5 optional behaviors, you need 31 subclasses. With 6, you need 63. So you can see that it becomes unmanageable pretty quickly. Now with Decorator Pattern, with essentially you write 1 class per behavior. So 3 behaviors mean 3 decorator classes, 4 behaviors mean 4 decorator classes. So the growth is linear, not exponential. Now the code over here, it makes it concrete. A simple store with no extra behavior is just a new file data store. A log store is a new logging decorator wrapping a file data store. A fully wrapped store with all 3 behaviors is a logging decorator wrapping a compression decorator, wrapping an encryption decorator, wrapping a file data store. 3 decorator classes handle all 7 combinations. Adding a 4th behavior means writing 1 new class, not 8. Now, there are several other dimensions where the decorator pattern is stronger. Combination flexibility. So with inheritance, the combination is fixed at compile time. With decorator, you assemble it at runtime. The second is adding a new behavior. With inheritance, you double the class count. With decorator, you add just 1 class. The third is removing a behavior. So with inheritance, you cannot selectively remove a behavior from a subclass hierarchy. With decorator, you simply omit that decorator from the chain. Fourth is testing. So for the inheritance, you test with the full hierarchy. With decorator, you test each decorator in isolation against the interface. Now, let's say when the interviewer asks you that, okay, how would you add logging, caching, and rate limiting to this service? The answer is decorator. Now let us walk through the full implementation so you can see how each piece fits together. The data store interface has 2 methods, write, which takes a string key and a byte array of data, and read, which takes a key and returns a byte array. This is the interface that every component in the system, base implementation, and decorator alike will implement. So now the file data store class is a base implementation. The write method takes the key, constructs a file path from it, and writes the bytes to the disk. The read method constructs the same file path and reads the bytes back. Nothing else. So no logging, no compression, no encryption, just raw file I/O. The logging decorator implements the data store and holds a reference to another data store called delegate. In the write method, it logs the number of bytes being written and the key. Then it records the start time, calls delegate.write to pass the work through to the next layer, and after the write completes, it logs how long the operation took. The read method follows a similar pattern, so it logs before, then it delegates and log after. The decorator adds observability without touching the file storage logic. Now the encryption decorator also implements data store and holds a delegate. In the write method, it encrypts the data using an encryption service, then calls the delegate.write with the encrypted bytes. In the read method, it calls the delegate.read to get the encrypted bytes, then decrypts them before returning. The encryption concern is now fully isolated in this one class. Now the compression decorator follows the same structure. On write, it compresses the data before passing it to delegate. On read, it decompresses the data after getting it from the delegate. Now let's talk about the assembly. You create the chain by nesting the constructors, a logging decorator wrapping a compression decorator, wrapping an encryption decorator, wrapping a file data store. So when you call store.write with some profile data, here's what happens. The logging decorator logs the call, then it passes the data to compression decorator. The compression decorator compresses it and then passes the compressed bytes to the encryption decorator, encrypts the compressed file bytes, encrypted compressed data to the disk. Now on the read, the order reverses. File data store reads the raw bytes, encryption data decorator decrypts them, compression decorator decompresses them, logging decorator logs the operation. So each layer undoes, essentially undo, what it did on the write path. Now each decorator is independently testable, so you can test the encryption decorator with a simple in-memory data store implementation. Each decorator is independently removable, so if you no longer need compression, just take the compression decorator out of the chain. And each decorator is independently reusable, so the logging decorator works with any data store implementation, not just file data store. Now let us put adapter and decorator pattern together in a practice scenario. Let's say you're designing a metrics collection system for a platform like, let's say, Datadog. The system needs to record metrics, things like counters, timers, and gauges, to multiple backends, which is an in-memory store for testing, a StatsDB store server for the production, and a cloud monitoring API for long-term storage. On top of that, all metrics should optionally support tagging, which means adding key value labels, batching, which means buffering metrics and flushing them periodically, and sampling, which means recording only a percentage of metrics to reduce load. Now let's say the interviewer asks you that, okay, how would you structure this? Now let's take a minute to pause and think before we jump to the solution. So now I will first cover the weaker answer for the interview and then a stronger answer that ideally should be given in the interview. So a weaker answer would be something like, let's say candidate says that, okay, I'll create a metric service class with methods for each backend and Boolean flags for tagging, batching, and sampling. So this combines all backends and all optional behaviors into one class. Adding a new backend or a new optional behavior requires modifying the same class. However, now the thing is, it violates the single responsibility principle, also the open close principle, and again, it makes the class very difficult to test. Now, what would a strong answer look like? A strong answer essentially identifies two distinct structural problems and applies the correct approach pattern to each. The multiple backends, which is in-memory, StatsD, and Cloud API, are an adapter problem. So you define a metrics recorder interface and write a separate adapter for each backend. Each adapter translates from your interface to the backend's API. The in-memory adapter stores metrics in a map. The StatsD adapter sends UDP packets. The Cloud API adapter makes HTTP calls. So each translation is isolated. The optional behaviors tagging, batching, and sampling are a decorator problem. Each one is a cross-cutting concern that wraps a metrics recorder without modifying it. A tagging decorator adds key value labels to every metric. A batching decorator buffers metrics in memory and flushes them on a timer. A sampling decorator generates a random number and drops the metric if it falls below a sampling threshold. Now in a production scenario, the chain would look like this. Sampling decorator, wrapping, batching decorator, wrapping, tagging decorator, wrapping, StatsD adapter. In test, you just use the in-memory metrics recorder with no decorators at all. Now, the strength of this answer is that it identifies two different problems, applies the right pattern to each, and explains how the patterns compose together in a single system. Now let us move to the facade pattern. So facade solves a different structure problem for adapter pattern and decorator pattern. It is not about translating interfaces or adding behavior, it is about simplifying access to a complex subsystem. Now here's the problem that facade addresses. In real systems, many operations require coordinating multiple services in a specific order. Consider, let's say, placing an order on a platform like Shopify. The workflow will involve checking inventory to make sure the items are available, validating the payment method, charging the payment, reserving the inventory so that another order does not take the same items, then creating a shipping label, and then sending a confirmation email. That is essentially 6 steps, and they need to happen in a specific sequence. Now, without a facade pattern, every piece of code that places an order must know about all 6 services. It must call them in the right order, and it must handle partial failures. Now, what if the payment succeeds but the shipping label creation fails? The caller needs to refund the payment and release the inventory. That error recovery logic is pretty complex, and if it is duplicated across every controller or endpoint that places the order, it becomes a maintenance problem. One caller handles the edge case, another one, let's say, it forgets. Now, the facade pattern centralizes this. So you create an order facade class with a single method, something like, let's say, place order. That takes an order request and returns the result. Internally, the facade coordinates all the services in the correct sequence and handles error recovery in one place. The API controller calls one method and gets back a result. It does not know how many services are involved or what the sequence looks like. Now the structure is pretty straightforward. The REST API controller talks to the order facade. The order facade holds references to the inventory service, payment service, shipping service, and notification service. It coordinates them. The controller sees only a simple API, so the complexity is essentially behind the facade. Now in an object-oriented interview, facade appears whenever the interviewer asks you to design an API for a multi-step workflow. The signal is essentially that, okay, this operation involves coordinating multiple services. So extracting a facade shows the interviewer that you think about the API simplicity for callers, not just the internal implementation. Now let us walk through the full implementation of the order facade to see what the facade handles mechanically. The order facade class receives 4 services through its constructor: inventory service, payment service, shipping service, and notification service. This is standard dependency injection. The facade does not create these services, it just receives them. Now, the place order method takes an order request and returns an order result. Here is the sequence. First, it calls the inventory service.check availability with the items from the request. If the inventory check says the items are not available, the facade returns immediately with an out of stock result, including which items are unavailable. Now, there is no point proceeding the payment if the items do not exist. Second is, if the inventory is available, it charges the payment by calling paymentService.charge with the customer ID and total amount. If the payment fails, the facade returns a payment failed result with the error message, and again, no reason to continue. Now, third, after the payment succeeds, the facade reserves the inventory by calling the inventory service.reserve. This is a separate step from the availability check. Checking availability is a read. Reserving is a write that prevents the order from orders, from claiming those items. Fourth is that it creates a shipping label. And this is where the error recovery gets pretty interesting. The shipping label creation is wrapped in a try catch. So if it throws a shipping exception, the facade does not just return an error. It performs compensating actions. It refunds the payment by calling payment service.refund. It releases the inventory reservation by calling inventory service.release. Only then it returns a shipping failed result. This compensating transaction logic is exactly the kind of thing that breaks production systems when it's scattered across multiple callers. Now, fifth, when everything succeeds, the facade creates an order object and sends a confirmation email through the notification service. So essentially, the facade handles 3 distinct concerns: sequencing, so inventory must be shipping before notification. The order matters and the facade enforces it. The second is error recovery. So if a later step fails, the earlier steps are rolled back. The compensating logic lives in one place. And third is simplification. So the caller sees place order and gets a result. It does not need to deal with any of the coordination. Now, when presenting a facade in let's say an object-oriented interview, you have to make a point to explicitly discuss the error recovery logic. What happens if step 3 fails after step 2 has succeeded? This is where production systems actually break, and interviewers are looking for candidates who think about these partial failure scenarios. Now, it is also worth knowing that the facade is a structured answer for coordinating services within a single process. In distributed systems where these services are separate deployments, the equivalent concept is a saga pattern. Knowing both and when each applies demonstrates cross-domain knowledge. We know which we need to demonstrate in the interview as well. Facade simplifies the interface to a subsystem, but simplification has its limits. It is possible to build a facade that hides too much, and that creates its own problems. Now, the order facade from the previous slide is a good example of facade done right. It exposes place order and hides the coordination details. The caller does not need to know about any inventory checks, payment processing, or shipping label creation. The simplification matches what the caller actually wants to accomplish, which is to place an order. Now, let's consider a bad example. A database facade class that has a single method, let's say getData, which takes an entity name as a string and runs a, let's say, select star from that entity. That is too simplistic. It hides the ability to filter with where clauses, to sort, to paginate, or to join tables. Any caller that needs anything beyond okay, give me everything has to bypass the facade entirely. And once callers are bypassing it, the facade is not really adding value. It is just an extra layer. Now, the decision comes down to a few signals. So facade works really well when callers consistently need the same workflow, when the coordination sequence is complex enough that centralizing it prevents duplication, and when error recovery involves compensating actions that should not be repeated across callers. Facade works less well when workflows vary significantly between callers, when the coordination is trivial, like just 2 calls in sequence, and when callers need fine-grained control that the facade does not expose. Now, there's a practical rule here. A facade should simplify the common sense cases, without preventing the uncommon cases. Expose a facade for the 80% of the callers who want the standard workflow. Keep the underlying services accessible for the 20% who need finer control. This is not all or nothing, so you can have an order facade for the common case and still let a specialized admin tool called inventory service directly. Now, in the object-oriented design interview, this distinction matters. If the interviewer probes you whether your facade is too rigid, or asks you that what if a caller needs to do something supporting that the facade does not support, you should be ready to explain that facade does not replace the underlying services. It sits alongside them, providing a simpler path for a common use case. The last structural pattern we'll cover is proxy. So the proxy pattern provides a surrogate or placeholder of another object to control access to it. The key property is that the proxy has the same interface as the real object, so the calling code cannot distinguish between the proxy and the real thing. The proxy intercepts calls and add behavior before or after delegating to the real object. Now, there are 3 common types of proxy, and each solves a different access control problem. The first is caching proxy. It stores the results of expensive operations and returns the cache value on the subsequent calls. If the same query runs 100 times, the database gets hit once. The other 99 times, the cache serves the result. This is relevant anytime read operations far outnumber the write operations. The second is virtual proxy, also called lazy loading. So it delays the creation or loading of an expensive object until it is actually needed. The proxy holds a reference that starts as null and creates the real object on first access. If the object is never accessed, it is never created, saving memory and instantiation cost. The third is production proxy or access control proxy. So it checks whether the caller has the required permissions before delegating to the real object. This separates authorization logic from business logic. The real service does not need to know about permissions at all. Now, a question that comes up frequently is how proxy differs from decorator, since both involve wrapping an object behind the same interface. The difference is in the purpose and in the relationship to the wrapped object. Proxy controls access, which is caching, lazy loading, permission checks. Decorator adds behavior, so logging, compression, encryption. Proxy, it often creates or manages the lifecycle of wrapped object. Decorator always receives the wrapped object from the outside. In typical scenarios, there is one proxy per object, while decorators are often stacked in chains. And the calling code usually does not know if the proxy is involved, while with Decorator, the calling code often assembles the chain. Now the distinction matters because an interviewer may ask you to justify why you chose proxy or decorator or the other way around. The answer depends on whether you're controlling access to an object or adding behavior to it. Let us look at the most common proxy variant, which is a caching proxy for database queries. Consider product catalog service for platform, let's say like Amazon. Product details are read far more frequently than they are updated. So a product page might get viewed, let's say, millions of times per day. But the product data just changes maybe once a week when someone, updates like the price or description. Unless there is a machine like ML powered pricing, but we'll cover that later. Now, without caching, every page view hits the database, which means millions of unnecessary queries for data that has not been changed. Now, the caching proxy eliminates these redundant queries without modifying the repository class. The product repository interface had two methods, which is find by ID, which returns an optional of product, and find by category, which returns a list of products. The Postgres product repository class implements this interface and queries the database directly. It opens a connection, prepares a SQL statement, executes it, and maps the result. Standard data access code. So now the caching product repository class here also implements the product repository, but it adds a caching layer. It holds a reference to a delegate, which is a real repository, and two caches, one for individual products keyed by a product ID, and one for category results keyed by the category name. Both caches are configured with time to live duration and a maximum size. In the find by ID method, the proxy first checks the product cache. If the product is present, it returns the cache value immediately. No database call. If the cache does not have it, the proxy calls the delegate's find by ID method to query the database, store the result in the cache, and returns it. The find by category method follows the same pattern with the category cache. Now, the wiring is in single line. You create a new caching product repository, pass it into the Postgres product repository as a delegate, and set a cache duration of 5 minutes. Any service that depends on the product repository now gets the caching behavior transparently. The catalog service does not know whether it is talking to the database directly or going through the cache. That is the power of proxy maintaining the same interface. Now each layer is independently testable and independently modifiable. You can change the caching strategy, the cache duration, or the cache size without touching the database access code. You can test the caching logic with a simple in-memory implementation of the product repository. This cache side pattern, check cache, query on miss, populate the cache with the proper TDL configuration is what interviewers expect to see when caching comes up in an object-oriented design interview. Because the reason is it demonstrates the production level thinking, so that's super important that you cover it into during the interviews. The second proxy variant worth understanding is the virtual proxy, which delays creating expensive objects until they are actually needed. Now, here's the problem. Let's say you consider a document management system where each document has a large binary attachment. These could be PDFs, images, or files, potentially 10 megabytes or more each. Now, when a user opens the document list, the system loads the document metadata, which is titles, dates, and authors. If the system eagerly loads every attachment's binary content alongside the metadata, it wastes a significant amount of memory. Most users browse the list, reads a few titles, and open maybe one or two documents. Loading all attachments upfront means loading data that will never be used. Now the virtual proxy solves this. The document attachment interface has three methods. So get content, which returns the binary data as a byte array, get content type, and get file size. So the lazy document attachment class implements this interface. It stores the metadata fields, content type, and file size directly because those come from a database index and are cheap to load. But it does not load the actual binary content. The cache content fields start as null. Now, when the get content type or get file size is called, it returns the stored value immediately, so no additional work is needed. But when get content is called, it checks if the cache content is null. If it is, the proxy calls the attachment store.load content to fetch the binary data from the storage. It stores the result in the cache content so that the subsequent calls to get content method do not trigger another load. If get content is never called, the binary data is never loaded. Now, This pattern appears in many systems. So in document management, file attachments are lazy loaded so that listing documents does not pull all attachments into memory. In social media feeds, high resolution images are loaded only when the user clicks for the full image. In ORM frameworks like Hibernate, related entities are lazy loaded so that the loading an order object does not automatically load every order item. In IDE file browsers, file contents are loaded only when the user opens a file, not when the directory listing is displayed. Now, in an interview, when you're designing a system that manages large objects like files, images, or media, mention lazy loading proactively. Say something like, okay, the document object holds a lazy attachment proxy that loads the binary content only when the user requests it. This signals to the interviewer that you think about the resource efficiency in your design, not just correctness. Now let us do a practice scenario that combines Facade Pattern and Proxy Pattern. So let's say you're designing a user registration flow for a platform like LinkedIn. The flow involves validating input fields, checking if the email is already registered, hashing the password, and creating the user record, sending a verification email, and logging the registration event to an analytics service. On top of that, the analytics service is expensive to initialize because it requires loading machine learning models for user segmentation. And the analytics service is not needed for every registration path. In certain regions, registrations they skip the analytic entirely. Let's say for because it might be like, for example, to GDPR in EU. Now let's say the interviewer asks you that, okay, how would you structure that? So now let's take a pause for 60 seconds and let's think about it before we jump to the solution. So the weak answer, I'll first cover the weaker version of the answer and then I'll cover the stronger version of the answer. So a weaker answer would be like, let's say a candidate says that, okay, I would put all the steps in a registration service and add an if check for analytics. Now, if you say that, that places 6 different concerns in one class, which violates the single responsibility principle, and it mixes analytics lazy loading logic directly into the registration flow. Now, a stronger answer separates the two structural problems. The multi-step registration workflow is a facade problem. So you create a registration facade that coordinates input validator, user repository, password service, email service, analytics service in one sequence. The facade handles the sequencing and the error recovery. For example, if the email sends fails after the user record has already been created, the facade handles the partial failure scenario. Now, the expensive initialization of the analytics service is a virtual proxy problem. You create an analytics service proxy that implements the analytics service interface. So when this proxy is constructed, it does not load the ML models. It defers that until the first analytics call actually happens. In regions where analytics is skipped, these models are never loaded and the initialization cost is never paid. Now, the facade handles coordination and sequencing. So the proxy handles the lazy loading concern. Each pattern solves a different problem in the same system, and each can be understood, tested, and modified independently. Now that we have covered all 4 structured patterns, let us put together a decision framework for choosing between them. The decision tree here works as a sequence of 4 questions. So the first question is, do you need to integrate with, let's say, an incompatible external interface? If the answer is yes, you use adapter. If no, you move to the next question. The second question is, do you need to add optional behaviors without modifying the class? If yes, you use the decorator pattern. If no, then you continue. The third question is, do you need to coordinate multiple services behind a simple API? If yes, then you use facade pattern. If no, then you move on. The fourth question is, do you need to control access, cache results, or delay initialization? If yes, you use proxy. If the answers to all the 4 questions is no, then you likely do not need a structural pattern for that particular part of the design. Now let's look at how these 4 patterns compare across several dimensions. Now, adapter's purpose is to translate between interfaces, and decorator's purpose is to add behavior dynamically. Facade's purpose is to simplify subsystem access, and proxy's purpose is to control access to an object. Now, on the question of whether the wrapper maintains the same interface, adapter does not. That is the whole point, right? Decorator does. That is how decorators stack. Facade does not, and provides a new simpler API. Proxy does, and this is how it stays transparent to the caller. Now, creating the wrapped object, adapter wraps an existing object. Decorator receives the wrapped object from outside. Facade coordinates existing services. And Proxy sometimes creates a wrapped object, as in the lazy initialization case. Now, in an object-oriented design interview, you may use multiple structure patterns in a single design. Adapter for external integrations, Decorator for cross-cutting concerns like logging and metrics, Facade for workflow coordination, and Proxy for caching or lazy loading. Recognizing which pattern fits which problem and being able to explain why you chose it is what separates, a strong answer from a not so strong answer. Now, this is something you would want to write down for interviews as part of your notes. So these are the signals that you tell you actually which structure pattern to reach for, and memorizing this mapping will help you recognize the right pattern quickly during an interview. Now, when the requirements given to you in the interview, let's say they say that phrases like integrate with third party, that pattern is adapter. You wrap the external APIs behind your own interface. Let's say the interview requirements say you that we might switch from provider A to provider B, so that pattern is adapter. Only the adapter changes, all callers are untouched. When the requirement says that add logging, caching, or metrics to an existing services, that pattern is decorator. So each concern becomes a separate decorator stackable at runtime. And let's say when the requirement says that this operation involves coordinating 4 or more services, so that pattern is facade, one entry point, centralized sequencing, and error recovery. And let's say when the requirement says that this resource is expensive to load, that pattern is virtual proxy, lazy load on first access, keep if it's never needed. And let's say when the requirement says that cache results are expensive queries, that pattern is caching proxy. Check cache first, query your own mess, and store the result. When the requirement says that check permissions before accessing this resource, this pattern is production proxy, so authorization logic stays separate from business logic. When the requirements mention that legacy system with an outdated API, that pattern is adapter, so the adapter translates legacy calls to your modern interface. And there are 3 questions you can ask yourself as a quick filter. First, is the interface incompatible? If yes, then you choose adapter pattern. Second, do I need to add an optional stackable behavior? If yes, then you choose a decorator pattern. Third, am I coordinating multiple services or controlling access to one? If yes, if coordinating, that is the situation, then you use facade pattern. And if you're controlling access, that is a proxy pattern. So these are like some mappings you should remember during your interview, because that will save time on the selection phase for the interview part. So yeah. Now let us work through a comprehensive practice scenario that brings together multiple structure patterns. Now let's say you're designing a reporting API for a platform like, let's say, Salesforce. The API must pull data from 3 internal services: CRM, billing, and usage analytics. It needs to aggregate and format the data. It should optionally export to a PDF or CSV. Reports should be cached for 15 minutes since generating them is expensive, and the CRM service uses a legacy SOAP interface while your system, let's say, uses REST style interfaces. Now let's pause for a bit and reflect and then think about how to approach this, and then we'll cover solution. So now here are the key design decisions. The legacy CRM SOAP interface is an adapter problem. You write an adapter that implements your modern service interface and translates calls to legacy SOAP API. The coordination of 3 services, CRM, billing, and analytics, is a facade problem. You create a report facade that orchestrates the data gathering, aggregation, and formatting. The caching of expensive reports is a cache mess with the 15-minute TDL. The optional export formats, PDF and CSV, are a strategy problem which we will cover in section 6, with a factory to create the right exporter, which we covered in section 4. Now, strong answer identifies all 4 patterns and explains where each one applies and why. It does not over-engineer any of them. Each pattern solves one specific structure concern. Now let us go through the common mistakes in structure pattern usage. The first mistake is coupling directly to third-party SDK. If the SDK changes its API, your entire codebase is affected. The correction is to wrap it in an adapter behind your own interface. The second mistake is using inheritance to add logging to, let's say, like 5 classes. That creates 5 subclasses, each duplicating the logging logic. The correction for that is having one login decorator that is reusable across all 5 classes. The third mistake is building a facade that hides everything with no direct access to the underlying services. Callers who need fine-grained control are forced to bypass the facade. The correction for that is to expose the facade for common cases and keep the underlying services accessible. The fourth mistake is that putting caching logic inside the repository class itself. This mixes the caching concern with the data access in the same class. The correction for that is a caching proxy wrapping the repository, keeping the concerns separate. And the fifth mistake is using decorator when the proxy is more appropriate. So adding access control is not the same as adding behavior. Access control is a proxy concern. Behavior enhancement is a decorator concern. The sixth mistake is using proxy when simple dependency injection would suffice. So for example, wrapping an object just to inject it adds unnecessary complexity. Constructor injection handles that case without a pattern. Now, these mistakes tend to come from choosing the wrong pattern for the problem. Each pattern has a specific structure concern it addresses, and using it outside that concern creates complexity without any benefit. Now, here's a reference card for the entire section on structured design patterns. We have essentially covered 6 structural pattern variants and incompatible interface to match your expected interface. Decorator adds stackable behavior at runtime without modifying the wrap class. Facade simplifies a complex subsystem behind a single coordinating class. Caching proxy, caches the results of expensive calls transparent to the caller. Virtual proxy delays the creation of expensive objects until first access. Protection proxy checks permissions before delegating to a real object. And here's how the section connects to the rest of the course. So back in section 2 on object-oriented programming, we covered polymorphism and composition over inheritance. Decorator relies directly on both of these concepts. In section 3 on solid principles, we covered the dependency inversion principle, the open-close principle, and the single responsibility principle. Adapter enables the dependency inversion principle. Decorator enables the open-close principle. And Facade applies the single responsibility principle to subsystem coordination. Now in section 4 on creational patterns, we covered factory method and builder. So adapters are often created by factory methods, and decorator chains can be assembled using a builder-like Fluent API. Now in section 6 on behavioral patterns, strategy objects often sit behind adapter when they wrap external algorithms, and chain of responsibility is structurally similar to decorator as a pipeline of handlers. In section 7 of pattern selection, the structural pattern signals from this section feed directly into the signal to pattern mapping table for rapid interview pattern recognition. Now every section builds on the ones before it, and the patterns we covered here will keep appearing as we move forward. So now let's move to section 6. In the last section, we covered structural patterns and how objects are composed and connected. Now we shift to something that comes up even more frequently in object-oriented design interviews, which is behavioral design patterns. So behavioral design patterns address a different type of question entirely. So instead of asking how objects are built or how they assemble together, behavioral patterns ask how objects communicate with each other and how responsibility is distributed among them at runtime. This also includes which objects makes a decision, how are events propagated, how are algorithms selected, and how are processing pipelines organized. Now, these are the questions that directly map to the business logic, and the business logic is exactly what interviewer asks you to design. Now, as you can see on the screen, in this section, we'll be covering 6 behavioral patterns plus how they combine in real-world designs. First, we'll be covering strategy design pattern, which lets you swap algorithms at runtime. Second, then after that, we'll be covering observer design pattern, which gives you event-driven decoupling between objects. Third, after that, we'll be covering command design pattern, which turns requests into standalone objects that can be stored, queued, and undone. Fourth, we'll be covering state design pattern, which lets object chain behavior based on the internal state. Fifth, chain responsibility design pattern, in which we'll which organizes processing into different pipelines. And after that, we'll be covering template design pattern, which gives you a fixed algorithm skeleton with customizable steps. Now, here's why this section matters so much for interview preparation. Now, there is a direct mapping between requirement signals and behavioral patterns, and learning that mapping lets you identify the right pattern within seconds of hearing that requirement when it's given to you during the interview. Let's say when the interviewer tells you that, okay, they say like a phrase like, okay, support multiple algorithms for X. So that is a hint for strategy design pattern. And if the interviewer says a phrase like, okay, when they say that, okay, when X happens, then you have to notify Y and Z, that means that there is a hint for the observer design pattern. Let's say if they say phrases like supports undo or redo operation or queue operation, that hints to the command design pattern. And if you hear statements in the interview by the interviewer that, okay, like something like object behaves differently in each state, that maps to the state design pattern. By end of this section, you'll have the signal to pattern mapping internalized along with full working implementations and the ability to combine these design patterns in a single design. So let's get started. Now let us start with strategy design pattern because it's a behavioral design pattern that appears in object-oriented design interviews more than any other. Now the problem strategy design pattern solves is pretty straightforward. You have a piece of functionality, let's say pricing, routing, compression, or sorting, and you need to support multiple ways of doing it. The calling code should not need to know which specific algorithm is in use. It just delegates the work to whatever algorithm has been configured. Now, the strategy design pattern solves this by defining a family of algorithms, encapsulating each one behind a common interface and making them interchangeable. The calling code, which we call the context, holds a reference to that interface. It calls a method on the interface, and polymorphism ensures that the right algorithm executes. Now, the context never knows or cares which specific implementation is behind the interface. Now, let's think about, for example, a ride-sharing platform's pricing engine. The pricing engine class holds a reference to a pricing strategy interface. Behind the interface, you might have a flat rate strategy class, or maybe a per hour strategy class, or maybe even a dynamic search strategy class. Now, the pricing engine delegates the fare calculation to whatever strategy that has been assigned. The strategy can be set at a construction time, loaded from a configuration file, or even swapped mid-request based on the business rules. Now, if you recall from section 3, this is a direct implementation of the open-close principle. Adding a new algorithm means writing one new class that implements that interface, so no existing code needs to be modified. Now, here are the signals that tell you the strategy is the right pattern and when to use it. First, let's say the requirements given to you say that, okay, you have to support multiple ways to do X. Now, X could be any operation, whether that is pricing, sorting, compression, routing, or even validation. Second, let's say you spot an existing if-else or if-switch statement that selects behavior based on a type or a configuration value. Third, let's say when an algorithm needs to change independently of the code that uses it, so that will be third condition when to apply the strategy pattern. And fourth, different customers, tiers, or contexts, they all need different behaviors based on the same operation. So that's the fourth use case to consider strategy pattern. Now, when you hear any of these signals in an interview, strategy should be your first instinct. You should state it explicitly in the interviewer to the interviewer. And, for example, you should say a statement like, okay, since we need multiple pricing strategies, you'll define a pricing strategy interface and then let each algorithm implement it. Now, let us make this concrete with a full worked example. Consider a ride-sharing platform like Uber that needs to support multiple pricing models. The pricing model depends on the city, the time of the day, the rider subscription tier, and the current demand. This is a perfect strategy scenario because the core operation, calculating a fare, stays the same, but the algorithm behind it changes. Now, the starting point is the pricing strategy interface. It declares two methods: calculate fare, which takes the ride request object and returns a money object, and get strategy name, which returns a string identifier for the strategy. Now, every pricing algorithm implements this interface. Now, the first implementation is a flat rate strategy class. It takes a base fare and a per kilometer rate as the constructor parameters. When calculate fare is called, it multiplies the per kilometer rate by the ride distance and adds the base fare. So if the base fare is, let's say, $5 and the per kilometer rate is $2, a 10 kilometer ride will cost you $25. So that is simple, predictable, easy to reason about. Now let's look at the second implementation, which is the dynamic search strategy class, and this is where things get interesting. This strategy wraps another pricing strategy. So it takes a base strategy and a demand tracker as a constructor parameters. When calculate fare is called, It first delegates to the base strategy to get the base fare, and then it asks the demand tracker for the current surge multiplier in the pickup zone and multiplies the base fare by that multiplier. So the base fare is $25 and the surge multiplier is, let's say, 1.5. So the final fare will be 25 times 1.5, which is $37.50. Now, the third implementation could be a subscription discount strategy class. So it also wraps another pricing strategy. It takes a base strategy and a discount percentage. When, let's say, calculate fare method is called, it calculates the base fare from the wrap strategy, then applies the discount. So if the base fare is $25 and the discount is 20%, so the final fare becomes $20. Now notice something important here. Both dynamic search strategy and the subscription discount strategy wrap another pricing strategy. This is the strategy pattern combined with the decorator pattern from section 5. The base strategy calculates the fare. The wrapping strategies modified it. You can essentially compose them: a subscription discount strategy wrapping a dynamic search strategy wrapping a flat rate strategy. This composability is a direct benefit of programming to interfaces rather than concrete classes. Now, the context class is the pricing engine. It takes the pricing strategy resolver as a constructor parameter. When calculate fare method is called, the resolver determines which strategy applies to this particular request. The strategy calculates the fare, and the engine returns a fare estimate that includes both the fare amount and the strategy name. The pricing engine never knows which algorithm ran, it just delegates and returns the result. Now, in an interview, this example demonstrates essentially three things the interviewers are looking for. Number one, the interface extraction that separates the contract from the implementations. Second, the composability of the strategies through wrapping. And third, the separation of strategy resolution from strategy execution. Now that we have a working strategy implementation, let us connect it back to solid principles from section 3. So strategy is not just a pattern, it is the open-close principle made concrete. So the connection is direct, and stating it explicitly in an interview demonstrates that you're a senior level candidate, so please do that. Now consider what the code looks like here without strategy. You have a single calculate fare method with a string parameter called pricing type. Inside the method there is an if-else chain. So if the pricing type equals flat rate, calculate one way. If it equals per minute, you calculate another way. And if equals surge, you calculate the third way. And then at the bottom, as you can see, if none of the type matches, we throw an exception. Now every time the business needs a new pricing time, a developer opens this method and adds another else if branch. Essentially, the class is modified for every new requirement. So essentially, that is the open-close principle violation we identified in section 3. Now, with strategy, adding a new pricing type means writing one new class that implements the pricing strategy interface. The pricing engine class is never edited. The pricing strategy resolver is never edited. All existing strategies are untouched. The system is open for extension through new classes and closed for modification of existing code. Now, the mapping between the solid principle and the pattern is pretty precise. Open for extension means writing a new pricing strategy implementation. Closed for modification means the pricing engine is never edited. The interface abstraction is the pricing strategy interface that defines the contract, and polymorphic dispatch means strategy.calculate fare method on the request routes to whichever implementation is assigned without the calling code knowing which one. Now when you refactor an if-else chain into a strategy pattern in an interview, connect the 2 points explicitly. You should say something like, okay, like this follows the open-close principle. Adding a new pricing type requires one new class and no existing code is modified. So when you say that one single sentence in the interview, that tells the interviewer that you understand the reasoning behind the pattern and you also the benefits in terms of open-close principle. So we have covered how to swap algorithms at runtime with strategy design pattern. The natural next question is, what about situations where one event in a system needs to trigger reactions in multiple other parts of the system? This is where the observer pattern comes in. Now the observer pattern defines a one-to-many dependency between objects. When one object called the subject changes states, all of its dependents called observers are notified automatically. The subject does not know what the observers do with the notification. It just fires the event and moves on. Now let us look at why this matters with a concrete scenario. Think about an order management system. When an order status changes to shipped, the system needs to do several things: send an email to the customer, update the inventory count, log the event for analytics, and notify the warehouse management system. That is 4 separate reactions to a single event. Now, without the observer design pattern, the order class must know about all of those 4 systems. It has to import the email service, the inventory service, the analytics client, and the warehouse notifier. It calls each one directly inside this update status method. Now imagine the business, let's say it adds a 5th requirement that you have to update a loyalty points tracker when an order ships. Now the developer has to open the order class, adds a new dependency, and adds a new method call. The order class now has become the center of gravity for every reaction to every status change. Now with the observer design pattern, the order class fires the status change event. Any number of listeners can subscribe to that event. The email notifier class handles email. The inventory updater class handles inventory. The analytics tracker class handles analytics. And each one implements the same order event listener interface. Now adding the loyalty points tracker means writing a new loyalty points updater class that implements the order event listener interface and registering it. The order class itself never changes. Now, let us compare the two approaches across a few dimensions. So with the direct calls, the order class knows about every listener. With the observer design pattern, the order class only knows about the listener interface. With direct calls, adding a new reaction means, modifying the order class, but with the observer, it means registering a new listener. Then with direct calls, removing a reaction only means modifying the order class. With the observer design pattern, you just unregistered the listener. For testing purposes, direct calls require mocking all listeners to test the order class in isolation. With observer design pattern, you can test with 0 listeners. And for runtime functions flexibility, direct calls are fixed at compile time, while observer listeners can be added or removed at runtime. Now, essentially, during the interviews, if you hear statements by the interviewer like, okay, if they say something like, okay, when X event happens, Y and Z events should also happen. They might not even use the word event, but if they say something like this one thing happened in one part of the system and then other 2-3 things should happen in other parts of the system, that is exactly the hint for the observer design pattern. So that's something you should remember for the interviews. Let us build out the observer implementation for the order management system example step by step. Now, the first thing we need is an event object. The order event class captures everything a listener needs to know: the order ID, the previous status, the new status, and a timestamp. This event object is what gets passed to every listener when a status change occurs. Notice that it captures the previous status as well as the new status. This is important because different listeners may care about different transitions. A listener that handles shipping notifications cares specifically about transitions to the ship status. A listener that handles analytics wants to log every transition regardless. Now, next is the listener interface. So the order event listener interface declares a single method, which is onOrderState status change, which takes an order event parameter. Every listener implements this interface. So one interface, one method. Any class that wants to interact to order status changes just implements that. Now the subject is the order class itself. It maintains a list of order event listener objects. It provides add listener and remove listener methods for managing the subscriptions. The key method is update status. When update status method is called, it saves the previous status, sets the new status, creates an order event object, and calls the notify listeners. The notify listeners method iterates through the listener list and calls on order status change on each of those listeners. Now let us look at 2 concrete listeners. So the email notifier class implements the order event listener interface. It takes an email service and a customer repository as dependencies. In its on order status change method, it checks whether the new status is shipped. As shipped. So if it is, then it looks up the customer by order ID, sends a shipping notification email. If the status is something other than quote unquote shipped, the email notifier simply does not do anything. It filters for the events that it cares about. Then the analytics tracker class also implements order events listener interface. It takes an analytics client as a dependency. In its on-order status change method, it tracks every status change event without filtering. It sends the order ID and the from status, the to status, and the timestamp to the analytics system. Each listener handles exactly one concern. The order class does not know that the emails are being sent. It does not know that the analytics are being tracked. It fires events and it just moves on. That is the separation of concern that makes observer design patterns so effective in object-oriented designs. Now the structure, an event object, a listener interface, a subject with a listener list, and a notify loop is a standard observer implementation. Using a realistic domain like, let's say, order management system instead of textbook examples signals more production experience to interviewers, so you should follow examples like these. Now here is a connection that helps in both object-oriented design interviews and system design interviews. Observer pattern at the class level is the same concept as a pub-sub at publisher-subscriber model, at the system level. So the mechanics might differ, but the idea is pretty same. So decouple the producer events from the consumer of the events. Now let us walk through the mapping. So in the observer pattern, the subject, like our order class, is a publisher. In a distributed system, the equivalent is an order service that publishes the messages. Then, the observer interface, which defines the event contract, maps to a message schema or event contract in a distributed system. Then, the listener list inside the subject maps to a message broker like Kafka, RabbitMQ, or SNS. And then, the notify listeners method mapped to a broker.publish call. And then, the listeners.onEvent method maps to a consumer that processes messages from the queue. Now, the key difference is the execution model. Object-level observer is an in-process and synchronous. The subject calls each listener directly, and the listener executes in the same thread. System-level pub-sub model is a cross-service and asynchronous. The publisher sends a message to the broker, and consumer picks it up independently, potentially seconds, or it might be even minutes later. So, when should you be using each one? If all the listeners are in the same process, object-level observer pattern is pretty appropriate. Bringing in a message broker for in-process communication adds complexity without any additional benefit. However, if the listeners are in different services, you cannot use object-level observer pattern because you cannot call methods from across service boundaries. So then you do need a message broker. If you need guaranteed delivery, object-level observer pattern does not provide it. If a listener throws an exception, the event is pretty much lost. A message broker provides retry and dead letter queues. For latency, object-level observer operates in microseconds. System-level pub-sub operates in milliseconds to seconds. And then for complexity, observer design pattern is about, let's say 30 lines of code. Pub-sub requires broken infrastructure, serialization, and consumer group management. So in object-oriented design interview, you are designing within a single service. So object-level observer pattern is the appropriate choice. But when you use it, mention the connection to the interviewer. That's something like, with a statement like that, okay, at the class level, I'm using observer design pattern for in-process event notification. If this system scales to, let's say, multiple microservices, this pattern maps directly to a pub-sub architecture with a message broker like Kafka. When you say the statement in the interview, that essentially bridges between the object-oriented design thinking and the system design thinking, and it shows the interviewer that you can think across different abstraction levels. Now let us test what we have covered so far with a practice scenario. Let's say you're designing a content moderation system for a platform like YouTube. User-uploaded content must be checked against multiple moderation strategies like a profanity filter, spam detection, a copyright check. So each strategy produces a moderation decision: approve, flag for review, or reject. Now when the content is rejected, the system should notify the content creator, log the decision for compliance, and update the creator's trust score. Now let's say if the interviewer asks you that, okay, how would you structure this? Now I'll first cover the weaker version of the answer, and then I'll cover the stronger version of the answer. Let's say if the candidate says that, okay, I would create a content moderator class with methods for each check type with if-else logic for notifications. That is not a good answer because the problem with this answer is that it puts all moderation logic and all notification logic into a single class. That violates the single responsibility principle. And then adding a new moderation strategy or a new notification type requires modifying the same class. Now let's talk about a stronger version of the answer, so which actually identifies two patterns and explains where each of them applies. The multiple moderation strategies, like for example profanity, spam, copyright, are a strategy design pattern problem. You define a moderation strategy interface with a moderate method that takes content and returns a moderation decision. Then each tech type is a separate implementation. So a moderation pipeline class essentially iterates through all registered strategies and aggregate their decisions. The notification reactions, which is notifying the creator, logging for compliance, updating the trust score, are an observer design pattern problem. The moderation pipeline fires a moderation decision event when the content is rejected, so these three listeners handle the reactions independently. Now here's the result. Adding a new moderation check means writing one new strategy class. Adding a new notification reaction means registering one new observer listener. Neither change modifies existing code, and this is the power of combining design patterns deliberately. Each pattern solves one specific aspect of the problem. So we have covered swapping algorithms with strategy design pattern and decoupling events with the observer design pattern. Now let's look at a pattern that solves a fundamentally different problem, which is what happens when you need to treat an action itself as a thing you can store, pass around, queue, or even undo itself. So that is a command design pattern which turns a request or operation into a standalone object. Instead of calling a method directly, you create a command object that represents the method call with all its parameters. The object itself contains everything needed to perform the action. Once the action is an object, you can do everything with it, you can with any other object. For example, you can store it in a list, pass it to another method, serialize it to a database, or even reverse it. Now there are 4 scenarios where command design pattern is the right choice. First, undo and redo operations. Each command knows how to execute itself and how to reverse itself. You maintain a stack of executed commands, and undoing pops the last one and calls this undo method. Second is queuing operations. So commands are stored in a queue and executed later, which is useful for task processing and job scheduling. Third is logging operations. So commands can be persistent for audit trails or even replay. And fourth is batch operations. So multiple commands are collected and executed as a group. Now the structure involves 3 key components. The invoker, which is let's say a text editor class. It does not perform text operations directly. It creates command objects and then it executes them. Second is the command interface that declares execute, undo, and get description methods. The concrete implementations like insert text command, delete text command, and format text command each implement those methods. And the command history class maintains the undo and redo stacks. The invoker creates a command and passes it to the history, and the history calls execute. Each executed command is pushed onto the undo stack. Undoing pops the last command and calls this undo method. Now interviews command design pattern appears for text editors, drawing applications, task schedulers, and any system that needs undo or redo operations or operation queuing. The phrases that you should listen for in the interview is that, let's say, interviewers say as part of a business, the problem given to you is like, okay, it needs to support undo operations, or you need to queue operations for later execution. So when you hear that phrases, that is a signal for applying, command design pattern. So please keep that in mind. Now let us build a full undo redo system for our text editor. The text command interface declares 3 methods: execute, undo, and get description. So execute performs the action, undo reverses it, and get description returns a human readable label, which is pretty useful for displaying an undo history to the user. Now the first concrete command is the insert text command. It takes 3 parameters: the text document it operates on, the position to insert at, and the text to insert. When execute is called, it inserts the text at the specified position using the document's insert at method. When undo is called, it removes the inserted text by calling delete range from the insertion position to the insertion position plus the length of the inserted text. So if we insert the word hello at position 10, undo deletes from position 10 to position 15. Everything the command needs to reverse itself is captured at the construction time. The second concrete command is delete text command, and this one has a subtle but important detail. It takes the document, a start position and an end position, but notice that it also has a field called delete text, which is not set in the constructor. It is set during execute. When execute is called, the first it saves the text that is about to be deleted by calling get text range on the document. Then it deletes the range. When undo is called, it restores the saved text by inserting it back at the start position. Now this is a critical point about command design pattern. The command must capture everything it needs to reverse itself. For insert text command, the text to remove is known at the construction time because it is the text that was inserted. For delete text command, the text to restore is not known until the deletion actually happens. So the command saves it during the execute. If a command it does not capture enough state, undo will not work correctly. Now the command history class manages two stacks, an undo stack and a redo stack, both implemented as array dequeue collections. The execute command method calls execute on the command, pushes it onto the undo stack and clears the redo stack. Now the last step is important. When a new command is executed after one or more undos, the redo history becomes invalid. If you type A, then type B, then undo B, then type C, you cannot redo B because that document state has diverged. Now the undo method pops from the undo stack and call undo on the command and pushes onto the redo stack. The redo method pops from the redo stack, calls execute again, pushes it back on the undo stack. Now this is a popular interview question. The key details interviewers evaluate are whether each command captures enough state to support reversal and whether the history correctly handles the undo, then new action edge case by clearing the redo stack. Now the command design pattern is not limited to redo undo operations. In production systems, command design pattern is frequently used for a completely different purpose, which is queuing operations for deferred or asynchronous execution. Now think about what happens when an order is confirmed on a platform like, let's say, Shopify. The system needs to generate an invoice PDF, update the inventory across multiple warehouses, and notify the shipping provider. If all three of these tasks are asynchronously, inside the order confirmation request, the customer waits for all of them to finish before seeing the confirmation page. That could take several seconds. Instead, these tasks should be queued and processed in the background. Now the command pattern makes this pretty, easy to implement. So the task command interface declares three methods: execute to perform the work, get task type to return the string identifier, and get max retries to specify how many times the task can be retried on failure. A concrete example is the generate invoice command class. It takes an order ID, an invoice generator, and a document store as a constructor parameters. When execute is called, it generates the invoice PDF and stores it. It identifies itself as a type, generate invoice, and allows 3 retries. Now, the task queue processor class takes a blocking queue of task command objects. It provides an enqueue method that adds a task to the queue and process next method that pulls the next task, attempts to execute it, and retries up to the command's maximum retry count. If all the retries fails, it calls a handle fail task method for error handling. Now the flow is pretty straightforward. The order confirmation endpoints create 3 command objects: generate invoice command, update inventory command, and notify shipping command. It enqueues all 3 and returns the confirmation response immediately. The process handles execution, retries, and failure recovery on a separate thread. Now adding a new post-order task means creating a new order command class and enqueuing it. No existing code changes. So when the interviewer asks you about the asynchronous processing or background jobs, there is a structure that you should be describing. Each task is a command object, the queue stores the commands, and the processor executes them with the retry logic. Okay, now let us talk about a pattern that looks structurally identical to strategy pattern, but it solves a completely different problem. The state pattern allows an object to change its behavior when its internal state changes. Instead of using if, else, or switch statements to check the current state, you encapsulate each state's behavior in a separate class. The object delegates to its current state object, and transitions between states are explicit. Now, let's consider an order in an e-commerce system. An order moves through several states, which is created, confirmed, shipped, delivered, and cancelled. The behavior of the order depends on which state it is in. Now, when the order is in the created state, it can be confirmed or cancelled. When it is in the confirmed state, it can be shipped or cancelled with a refund. When it is the shipped state, in the shipped state, it can be delivered, but it cannot be cancelled. And if it's in the delivered state, no further transitions are allowed. Now, without the state pattern, every method that operates on the order will have an if-else chain checking the current state. The cancel method checks if the status is created, set it to cancelled. If the status is confirmed, set it to cancelled and process a refund. If the status is shipped, then you throw an exception. And if the status is delivered, you throw an exception as well. And similarly, the confirm method has a similar chain, and the ship method has a similar chain as well, just like the deliver method. Now, every method has a similar if-else structure, so the behavior for the confirm state is scattered across the cancel method, the ship method, the confirm method, and the deliver method. If you add a new state like let's say return, you have to find and modify every method in this class. Now with the state pattern, all behavior for the confirmed state lives in one confirmed state class. All behavior for the shipped state lives in one shipped state class. Adding a return state means writing one new return state class that defines its own behavior for every operation. Existing state classes remain unchanged. Now the state design pattern appears in pretty much any object-oriented design interview involving lifecycle management. So for example, order processing, document workflows, game character behavior, connection management, or even payment processing. The signal phrase is that to listen through the interview is that if this says a statement like, okay, object behaves differently depending on its state, that's a hint for a state design pattern. Let us build the full state pattern implementation for the order lifecycle. The order state interface delivers 5 methods: confirm, ship, deliver, cancel, and get state name. Each method takes an order context as a parameter. The context is how state objects access the order's data and trigger state transitions. Now the order context class, which represents the order itself, holds a reference to its current order state, an order ID, a payment service for processing refunds, and a transaction ID. It initializes it in the created state. So when the context confirm method is called, it delegates to current state.confirm. When ship is called, it delegates to the current state.ship. The context does not contain any if-else logic. It simply delegates every operation to the current state. Now, the context also provides the set state method that state objects uses to trigger. So the context also provides the set state method that state objects use to trigger transitions. This is a key design decision so that state objects manage transitions into the context. Now let us look at two state implementations. So the created state class defines what operations are valid when the order is newly created. Calling confirm transitions the order to confirm state, calling cancel transitions it to the cancel state, but calling ship throws an invalid transition exception with the message like, okay, cannot ship an unconfirmed order. And then calling a deliver, throws an invalid transition exception with this message like, the invalid operations are handled explicitly with clear error messages, and they are not silently ignored. Now the confirm state class defines different behavior. So calling confirm throws an exception because the order is already confirmed. Calling ship transitions to ship state. Calling delivers throws an exception because you cannot deliver before shipping. And calling cancel processes the refund through the payment service and then transition it to the cancel state. Notice that the confirm state's cancel method has a side effect. It triggers a refund. The side effect is specific to canceling from the confirm state. The created state's cancel method has no refund because no payment has been made yet. Now each state class defines exactly which transitions are valid and what side effects accompany each transition. Adding a return state means writing a return state class and adding a return method to the order state interface. Existing states simply throw invalid transition exception from the return method unless the transition is valid from their state. Now, interviewers over here evaluate two things here: whether you handle invalid transitions explicitly rather than silently ignoring them, and whether side effects like refunds are placed in the appropriate state class. Now this is a question that comes up pretty regularly in object-oriented design reviews, which is that, okay, what is the difference between state design pattern and strategy design pattern? So they do have identical structure, both involve an interface, multiple implementations, and a context that delegates to the current implementation. If you look at the UML diagrams, they are pretty similar as well. The difference is entirely in the intent and lifecycle. Now let me walk you through the distinction across several dimensions. Number one is intent. Strategy is about choosing one algorithm from a set. State is about an object changing behavior as its internal state changes. Second point is who selects the implementation. So in strategy, external code or configuration selects the implementation. In state, the current state determines the next state. The third point is transitions. So in strategy, the implementation is typically set once and rarely changes. In state, transitions happen throughout the object's lifetime. The fourth distinction is awareness. So in strategies, they do not know about each other. A flat rate strategy has no knowledge that a dynamic search strategy exists. In state, each state knows which states it can transition to. For example, the confirm state knows about a shift state and cancel state because it transitions to them. And then what they replace has a distinction. So for example, strategy design pattern replaces an if-else change that selects an algorithm, and state design pattern replaces an if-else change that checks the current state. Now this is a simple test you can apply. You should ask yourself that, okay, does this object change its state, behavior over time? If yes, then it's a state design pattern. For example, the order starts as created, transitions to confirmed, then to shipped. The behavior changes, as the object progresses through its life cycle. If it's not, then it's a strategy design pattern. The pricing algorithm, for example, is selected once based on the consumer's tier and does not change during the request. Now, a common mistake in interviews is confusing the two because the class diagram, they look pretty identical. Here's how to differentiate more clearly. If the object transitions between the implementations during its lifetime and each implementation knows which further implementations it can transition to, that is the state design pattern. If the implementation is selected externally and it stays fixed, that is the strategy design pattern. Now let's say if the interviewer asks you directly, okay, is this state design pattern or strategy? Then you apply the transition test. In state design pattern, the current implementation determines the next implementation. In strategy design pattern, external code selects the implementation. Here the order's current state determines valid next states. So this is the state design pattern that we have just covered. Let's say you're designing a drawing application like Figma, eraser, shape tool, and text tool. Each tool behaves differently when the user clicks on the canvas. The application also needs full undo redo support for all the drawing operations. Now let's say the interviewer asks you that, okay, how would you structure the tool behavior and the undo system? So now let's work on that. I'll first give the weaker answer and then I'll move to the stronger version of the answer. A weaker answer would sound something like this. But okay, let's say if the candidate says that, okay, I would use the if-else check statements to check the current tool and then create a list of operations for undo operation. Now, if the candidate says that, that's not a good answer because the problem is that this conflates two separate concerns. The tool behavior selection and the undo system are two different problems that need different solutions. Now, a stronger answer actually separates them cleanly. The tool behavior that changes based on which tool is selected is a state design pattern problem. A tool state interface defines, let's say, like on canvas click, on canvas drag, and on canvas release methods. Each tool, pen, eraser, shape, text is a separate state implementation. When the user switches tools, the application transitions to corresponding state. So the pen state handles click differently than the eraser state, and each state encapsulates its own behavior completely. The undo redo system is a command or design pattern problem. So for example, each drawing action creates a command object. A draw line command captures the line coordinates and the color. An erase area command captures the area being erased and saves the pixel data before erasing so it can store them on the undo operation. And an insert shape command, captures the shape type, position, and the dimensions. So these two patterns work together naturally. The current tool state creates the appropriate command when the user interacts with the canvas. The pen state creates the draw line commands. The eraser state creates erase area commands. and the command history manages the lifecycle of those commands, handling undo and redo through the stack mechanism we built earlier. And this is exactly where the chain of responsibility comes in. So we have covered patterns for swapping algorithms, decoupling events, encapsulating actions, and managing state transitions. But what about scenarios where a request needs to pass through a series of checks or transformations in sequence, and any check can reject the request and stop the pipeline? The chain of responsibility design pattern passes a request along a chain of handlers. Each handler decides whether either to process the request or pass it forward, or to reject the request and stop the chain. The request moves through the chain until the handler fully processes it or the chain ends. Now, if you use HTTP middleware in a web framework, let's say like Node.js or Python Flask, you have essentially used chain of responsibility design principle. A web request passes through authentication middleware, then authorization middleware, the rate limiting, the input validation, then logging, and finally reaching the business logic. Each middleware can process the request and pass it forward, or reject it and return an error response. If the authentication fails, the request never reaches rate limiting. If the rate limiting rejects the request, validation is skipped. First, multiple checks or transformations must be applied to a request in sequence. Second, the set of checks can vary because some requests skip certain checks. Third, each check is independent and has a single responsibility. And fourth, a chain can short circuit, meaning a failed check stops further processing. The structure is linked list of handlers, so each handler holds a reference to the next handler in the chain. If the handler succeeds, it passes the request to the next handler. If it fails, it returns an error directly and the remaining handlers never execute. Now, chain of responsibility appears in interviewers for request processing, validation pipelines, approval workflows, and middleware design. Now, let us build a request validation pipeline step by step. The request handler interface declares two methods: handle, which takes an API request and returns a handler result, and setNext, which takes the setNext request handler in the chain. The handler result is either a success or rejection, with a status code and an error message. Now, to avoid duplicating the chain linking logic in every handler, we use an abstract request handler base class. It implements the setNext by storing the reference to the next handler. It provides a protected pass-to-next method that checks whether a next handler exists. If one does, it calls the handle on the next handler. If not, it returns success, meaning the request has passed through the entire chain. Now, the first concrete handler is the authentication handler. It takes a token validator as a dependency. When handle is called, it extracts the authorization header from the request. If the header is null or blank, it returns the rejection with status code 401 and the message, for example, missing authentication token. If the token is present, it validates it. If the validation fails, it returns a 401 rejection. If validation succeeds, it sets the authenticated user ID on the request and calls pass to next. The request then continues to the next handler. The second handler is rate limit handler. So it takes a rate limiter as a dependency. When handle is called, it gets the authenticated user ID from the request and checks whether the user is within the rate limit. If not, it returns a 429 rejection. If the user is allowed, then it passes. It calls the pass to next. The third handler is the input validation handler. So it takes a request validator as a dependency. It validates the request body. If the validation fails, it returns the HTTP 400. If it passes, it calls the pass to next. Now, assembling the chain is pretty straightforward. You create the three handlers, link them by calling setNext on each one, and then call handle on the first handler with the incoming request. The request flows through authentication, the rate limiting, and then validation. Each handler checks one concern. If authentication fails, the request never reaches the rate limiting. If rate limiting rejects the request, validation is skipped entirely. Each handler is independently testable because you can set its next handler to null and test it in isolation, and each handler is reusable across different API endpoints because it handles one generic concern. The key detailed interface look for in the chain of responsibility and design pattern is the short-circuiting behavior. Reject a request, skip all the remaining handlers in the chain. So we have covered 5 behavioral patterns. The last one in this section is the template design pattern and solves a specific scenario that the other patterns do not address well, which is when multiple classes share the same algorithm structure but differ in specific steps. Now, template design pattern defines the skeleton of an algorithm in a base class. The overall structure, meaning which steps execute and in what order, is fixed, but the implementation of individual steps are deferred to the subclasses. The what happens in what order is locked down, but the how each step is performed is varies. Now consider data import pipeline, for example, whether you're importing data from a CSV file, a JSON API, or an XML field. The steps are the same, which is read from the source, pass the raw data into records, validate the records, transform them into a target format, and save them to a database. The sequence is always the same, but how each step executes and differs. Reading a CSV file means opening a file on the disk. Reading from a JSON API means making an HTTP request. Parsing CSV means splitting by commas. Parsing JSON means deserializing JSON objects. Now, the base class data import pipeline defines a final method called runImport that executes the 5 steps in order: read from source, parse, validate, transform, and save to database. The method is final, which means subclasses cannot change the sequence. 3 of the methods, read from source, parse, and transform, are abstract. Subclasses must implement them. 2 methods, validate and save to database, have default implementation that the subclasses can override if needed. Now let us compare template method, strategy design method, design pattern. So in template method, customization happens through inheritance. You override the methods. In strategy, customization happens through composition. So you inject an interface. Then the template method fixes the algorithm structure in the base class. Strategy design pattern leaves the entire algorithm up to the strategy implementation. Then template method creates coupling between the subclass and the base class. Strategy design pattern keeps the strategy independent. And then the template method design pattern is actually configured at the compile time, whereas the strategy design pattern can be swapped at the runtime. Now, template method design pattern actually appears in interviews for data processing pipelines, report generation, and ATL workflows. So the statement to listen to to the interviewer is like, let's say if they get the requirements where they say that okay, the steps are always the same, but the implementation in each step varies. That statement is a signal in the interview that it points to the template method design pattern. Now let us build 2 concrete implementations of the data import pipeline. Now, the CSV import pipeline class extends the data import pipeline. It reads from the source method, which reads the file from the disk using a file reader utility. Parse method actually takes the raw content and splits it by comma using a CSV parser. Its transform method trims the white space from all fields and normalizes the dates to the year, month, and day format. The validate and the save to database method are inherited from the base class because the default behavior is sufficient. Now the JSON API import pipeline class also extends the data import pipeline. Its read from the source method makes an HTTP GET request to the source URL using an HTTP client. Its parse method deserializes the JSON array into records using a JSON parser and a JSON mapper. Its transform method flattens the nested JSON fields and converts units to metric. Again, validate and save to database methods that uses the default implementation. So both pipelines follow the exact same sequence, which is read, parse, validate, transform, and save. The steps themselves are different because CSV and JSON have different data access patterns, parsing logic, and transformation needs. But the overall algorithm is pretty same. Adding a new data source, which is XML, Parquet, or a database dump, means writing one new subclass that implements the 3 abstract methods. The pipeline sequence is guaranteed to be consistent because it is defined once in the base class and locked with the final modifier. Now, there is a trade-off to be aware of. Template method uses inheritance, which means inheritance is the fragile base class risk we discussed in section 2. If the base class data import pipeline changes the order of steps or adds a new required step, all required subclasses may break. For systems where the pipeline steps themselves need to be swapped at runtime, or where you want to avoid the deep inheritance hierarchies, strategy or chain of responsibility would be a better fit. Now, in an interview where you use template method, mention this trade-off more proactively. You should say statements like, okay, I'm using template method here because the algorithm structure is fixed and shared across data sources. If the pipeline steps needed to vary at runtime, I would use a strategy or a chain of responsibility design pattern instead. This tells the interviewer that you are made a deliberate trade-off, not a default choice. So far in this course, we have covered 14 design patterns across 3 sections: creation patterns, structure patterns, and behavior patterns. Each of those sections taught us, the mechanics of individual patterns, how they work, when to apply them, and what they look like in code. But here's the gap that separates someone who knows the patterns from someone who can use them in an interview. So knowing 14 patterns is not enough if you're not able to apply them clearly in the interview. So the real skill is actually hearing a requirement and instantly recognizing which pattern it maps to. And equally important is recognizing when applying a pattern would actually make your design actually worse. So this is what this section is about. We're going to build a repeatable selection framework. Think of it like the pattern recognition you already do in algorithm interviews. Let's say when you hear a phrase that, find the shortest path, you think BFS or Dijkstra's algorithm. When you hear like optimize overlapping subproblems, you think of dynamic programming. So pattern selection in object-oriented design works very similarly. You hear a signal in the requirements in the interview, and that signal maps to a specific pattern. Now we'll start with 5-step selection process you can apply systematically in any object-oriented design interview. And then we'll walk through a complete signal to pattern mapping table that covers every pattern from sections 4 through 6. After that, we'll work through 3 full examples from raw requirements all the way to a justified pattern selection. We'll also cover over-engineering, which is the single most common mistake candidates make in object-oriented design interviews. And we'll also look at which patterns get tested more frequently and at which companies. After that, we will cover 6 production anti-patterns, which are God class, feature envy, shotgun surgery, circular dependencies, premature abstraction, and inappropriate intimacy. Finally, we'll talk about how to actually, present and structure your answer during the interview itself. Now, let me frame why this section matters. Essentially, without this section, 14 patterns, but you would have no system for choosing between them. So you end up applying patterns because you know them, but not because the requirements demand them. So sometimes what candidates do, they over-engineer with 6 patterns when 2 would have been enough. And essentially, you cannot spot design flaws in your own code or in code an interviewer puts in front of you at that current moment. But the goal with this section is that you hear a requirement signal and you instantly know which pattern will fit. You justify every pattern with a specific problem it solves, you apply the minimum set of patterns that address the actual requirements, and then you recognize anti-patterns by name and know the specific refactoring for each one. So this is a section that ties everything together, so let's get into it. So pattern selection is not intuition. It is not something that comes with experience, and essentially you cannot just memorize it. It is a repeatable 5-step process that you can apply systematically during any object-oriented design interview. So let me walk through each step. Now step 1 is to identify the objects and their responsibilities. Before you reach for any pattern, you need to identify the core objects in the system and assign each object a single clear responsibility. This is the object-oriented programming fundamentals from section 2 and the single responsibility principle from section 3. Now, if your objects are wrong, if the responsibilities are misallocated, no pattern will essentially save the design. The foundation has to be right first. Then step 2 is to identify the dimensions of variation. This is where pattern selection actually begins. You ask one question, which is, what in the system changes or varies? If the algorithm varies, like different pricing strategies or different sorting approaches, that is a strategy signal. If the object's behavior varies based on the current state, like a ticket moving from open to in progress to resolved, that is a state signal. If the reaction to an event varies, meaning different parts of the system need to respond when something happens, that is an observer signal. And if the type of object being created varies based on some configuration, that is a factory method signal. And if the construction process is complex with many optional parameters, so that is a builder's pattern signal. Then step 3 is to identify the cross-cutting concerns. So essentially you should ask that, what behaviors need to be added to the system without modifying the core logic? If you need to add logging, caching, metrics, or any encryption layers as layers on top of existing functionality, that is a decorator signal. If you need access control, lazy loading, or caching at the proxy level, that is a proxy signal. If you need to translate between a systems interface and an external systems interface, that is an adapter signal. And then if you need to coordinate 3 or more services behind a simplified API, that is a facade signal. Now step 4 is to check for for undo, queuing, or pipeline needs. So if the operation needs to be undone or queued for later execution, that is a command signal. If the request pass through a sequence of checks where each check can stop the pipeline, that is a chain responsibility signal. And if the overall algorithm structure is shared, but specific steps differ between implementations, that is a template method signal. After that, step 5 is validation. So for each pattern you selected in the previous steps, you verify, does the requirement actually demand this pattern, or am I just adding it because I just know it? If a simple solution works, let's say a plain interface, a simple method call, a constructor, you should prefer that simpler solution. Patterns sometimes, they add indirection. So indirection is only justified when it solves a specific, extensibility, decoupling, or maintainability problem. Now, walking through these 5 steps out loud during your interview shows the interviewer, that you have a structured thought process rather than ad hoc guessing, and that structured thought process is exactly, what earns strong evaluation interviews. Now let us apply that 5-step process to a concrete requirement so you can see how it works in practice. Let's say the requirement is given to you in the interview that, okay, design a notification service that sends alerts through email, SMS, and push notification. Now, different notification types such as marketing, transaction, and alert should be routed to different channels. When a notification is sent, log it for compliance and update analytics. So step 1, identify the core objects. So we have a notification service class that acts as an orchestrator. We have a notification channel that handles delivery. We have a notification router that handles routing logic, a compliance logger for logging, and an analytics tracker for analytics. So that is 5 objects, each with a clear single responsibility. Step 2 is to identify the dimensions of variation. So the delivery channel varies. We have email, SMS, and push, and more channels could be added in the future. So that is a strategy signal. The routing logic selects, which channel to use based on the notification type. So that is a factory signal. Step 3 is to identify the cross-cutting concerns. So compliance logging and analytics tracking are both reactions to the event of a notification being sent. They are not part of the core delivery logic. They should not be hardcoded into the delivery flow. So when a notification is being sent, 2 independent systems need to react to that event. So that is an observer pattern signal. So step 4, let's check for undo, queuing, or pipeline needs. So essentially in this example, no undo is required. There's no pipeline of sequential checks. There's no shared algorithm structure with varying steps. So step 4 produces no patterns. Then step 5 is validate. So we have identified 3 patterns: strategy for channels, factory for the routing, and observer for the post and no reactions. Each one maps directly to a specific requirement, and each pattern actually solves the stated problem. Now the resulting architecture has a notification service using the notification router, which is the factory, to select the right notification channel. The notification channel is the strategy interface with the email channel, SMS channel, and push channel as implementations. And the notification service notifies the notification listener interface, which is the observer with compliance logger and analytics trackers as listeners. Now there are 3 patterns, each justified by a specific requirement with no over-engineering. This walkthrough is exactly what interviewers would want to see. A structured approach that maps requirements to patterns with explicit justification. So that is something you should try to follow in interviews. Now let us build the master reference table. So this maps every pattern from sections 4, 5, and 6 to a recognition signal and the phrase or the requirement characteristic that tells you this pattern is the right fit. Now starting with the creation patterns, when you hear a phrase in the interview like, okay, let's say the interviewer tells you, okay, create different types based on configuration, that maps to factory method. The justification is centralizing creation logic and decoupling callers from concrete types. Let's say when the requirement in the interview says, okay, create a family of objects that must be consistent with each other, that maps to abstract factory. It guarantees that all created objects will belong to the same family. When an object has 5 or more parameters, many of which are optional, then that maps to builder. Builder gives you self-documenting construction with validation in the build method. And then when exactly you need one instance is required for correctness, like a connection pool or a configuration registry, that maps to Singleton Pattern. That too through dependency injection, which is almost always a better approach. Now for structural patterns, when you need to integrate with an external API that has a different interface from yours, that is the adapter pattern signal. Adapter pattern translates between incompatible interfaces, so when you need to add logging, caching, or metrics without modifying the class itself, that is decorator pattern. Decorator pattern gives you stackable behaviors with linear class growth. Then when you need to coordinate 3 or more services behind a simple API, that is facade pattern. Facade pattern centralizes sequencing and error recovery. And when you need to cache resources like lazy load, expensive resources, or check permissions before accessing an object, that is proxy pattern. Proxy pattern controls access transparently. Now for behavior patterns, for example, there's a interview tells you something like, okay, you have to support multiple algorithms for X, that maps to strategy pattern. Or if you hear in the interview, a statement like, okay, when X happens, you have to notify Y and Z, so that maps to observer pattern. If you hear a phrase like, okay, support, undo, or redo, or queue operations, that map to command pattern. And if you hear phrases like, object has to behave differently in each state, or if you notice that in the requirement, that maps to state patterns. Similarly, if you hear a phrase like, or if you notice the problem talks about, okay, processing through a pipeline of checks, that maps to chain responsibility pattern. And if you notice, the problem deals with like same algorithm structure but different steps, that maps to template pattern. Now here's something worth noting. You don't need to memorize pattern names to succeed in the object-oriented design interview. But what matters is actually recognizing the signal in the requirements and knowing the structural solution. If you here support multiple types of X and your extent is to extract an interface with one implementation per type, you have essentially applied strategy pattern, whether you can name it or not. The structural thinking is what counts. Now, internalizing these signals is some of the highest leverage preparation you can do for object-oriented design interviews. It is the equivalence of internalizing, algorithm pattern recognition. The faster you match signals to patterns, the more time you will have for the detailed design phase where the strongest evaluation signal comes from. Now let us work through a full example end-to-end. So let's say if there's a checkout flow for a platform like Shopify. So let's say you're given requirements in the interview that are, okay, you have to support multiple payment methods, including credit card, bank transfer, and digital wallet. Then you also have to apply digital discount codes for different discount types such as percentage, flat amount, and buy one, get one free. Then you have to validate the order through a series of checks, including, covering inventory, payment method, validity, shipping address, and fraud detection. Then the fourth requirement is that, okay, you have to process post-checkout actions, including sending a confirmation email, updating inventory, and generating an invoice. And the fifth requirement given to you is that, okay, there has to be an invoice generator. So it's expensive to initialize, but it's not needed for every order since some orders are digital only. Now, let's walk through the pattern selection for each of these requirements given to you. Number one is multiple payment methods. So the signal is essentially different types of X, so that each payment method is a separate algorithm for processing a payment. Credit card process, it includes tokenization and charge capture. Bank transfer involves ACH initiation and settlement. Digital wallet involves wallet-specific API calls. So these are all different algorithms for the same operation. So that maps to a strategy pattern, and let's say we call the interface payment processor. Now selecting which payment method to use based on the order. So the signal is essentially, okay, you have to create based on some configuration. The system needs to decide which payment processor implementation to use based on the order details. That maps to a factory. So essentially, let's say we name it a payment processor factory. So for that, that will encapsulate that decision. The third requirement that we can target is multiple discount types. So the signal to look for is, okay, different algorithms for X. So that is essentially, percentage discounts, flat amount discounts, and buy one, get one discounts. So they all calculate the final price differently. Each discount type is a separate calculation algorithm. So that is another strategy application. And let's say this time we call the interface and discount strategy interface. Now next requirement to target is the series of validation checks. So the signal for that would be, okay, when you hit the pipeline of checks, essentially, so that is inventory validation, payment method validity, shipping address validation, and fraud detection. So they all form a pipeline where each check can reject the order and stop the flow. So that maps to chain responsibility pattern. Each validator in the chain either passes the order to the next validator or rejects it. The next requirement to target is post-checkout actions. So for that, the signal is, okay, essentially when X happens, then you do Y, Z, and let's say Z. Now for that, as you can see in the requirement, it was mentioned that when checkout completes, 3 independent actions need to happen. Send a confirmation email, update inventory counts, and generate an invoice. So the checkout flow should not know about each of these individually. That maps to observer pattern. Let's say we create an interface for that called checkout event listener. Now the last one is the expensive invoice generator. So the signal for that is expensive resource, not always needed. So the invoice generator is costly to initialize and not every order requires an invoice. So that maps to virtual proxy. The proxy holds a reference to the invoice generator but only creates the full actual instance when the first invoice generation request comes in. Now here's an important part of this worked example. The checkout orchestration, the sequence of steps from validation to payment to order creation, is a method in the checkout service class. Not every piece of coordination needs a facade. If only one caller performs the checkout, a well-structured method is pretty sufficient. Patterns solve extensibility and decoupling problems, not sequencing problems. So as you can see, 6 requirements have mapped to 6 patterns. A 7th consideration would be the checkout orchestration. So explicitly, essentially, we decided that did not get a facade pattern. That selectivity, essentially applying patterns only when justified, is actually earns you better signals in the interview. Now let us work through a second example. So this is a messaging subsystem for, let's say, a platform like Slack. So requirements for, let's say, given to you in the interview are, okay, the number 1 is you have to support multiple message types including text, image, and file and code snippet, each with different rendering. Let's say the second requirement given to you is messages transition through states, so draft, sent, and delivered. Also, in addition to that, the third requirement is that, okay, when the message is sent, you have to notify the recipient, update the unread count, index it for search. Fourth requirement is, okay, the messages can be edited and deleted, so you have to maintain full edit history. Then the system integrates with third-party spam detection API that has a proprietary interface. And the last requirement given to you is essentially the message content should be optionally encrypted and compressed before storage. Now, multiple message types with multiple rendering. That's the first requirement we'll target. So the signal for that is, okay, again, different types of X. So essentially that becomes each message type renders differently. So a text message renders with a formatted text, an image message renders with a preview thumbnail, a code snippet renders with the syntax highlighting. So these are essentially different algorithms for the same operation, which is rendering. So that maps to a strategy interface. Let's say with the interface we'll name as message renderer. And selecting which renderer to use based on the message type maps to the factory pattern. Requirement we'll target is message state transitions. So the signal over here is that, okay, object behaves differently based on state. So a draft message can be edited and sent but cannot be delivered. A sent message can be delivered but not edited. A delivered message can be read. Similarly, each state defines which operations are valid and what happens when those operations are called. So that maps directly to the state pattern with the message state interface and implementations for draft state, send state, deliver state, and so on. The next requirement we'll target is post-send notifications. So the signal over here is that, okay, when X happens, you have to notify Y and Z. So when the message is sent, 3 independent systems has to react. The recipient gets notified, the unread count updates, and the search index get updated. The message sending logic should not be coupled to any of those reactions, so that maps to observer pattern, and with the interface, let's say we name it as message event listener. So next requirement target is the edit history with undo capability. So the signal for that is you have to store and reverse operations. So each edit to a message needs to be stored as an operation that can be reviewed and potentially reversed. So that maps to command pattern. Each edit is encapsulated as a command object that captures what has changed and can undo the change. The next requirement to target is third-party spam detection API with a proprietary interface. So signal for that is you have to integrate with the incompatible API. So for that, your system would use one interface for spam detection. The third-party API uses a completely different interface. So that maps to adapter pattern. The spam detector adapter interface translates between your interface and the third-party API interface. The next requirement to target is optional encryption and compression before storage. So the signal for that is you have to add behavior without modifying the core logic. Encryption and compression are optional layers that wrap the storage operation. You might want encryption alone and compression alone, both or neither of them. So again, that maps to decorator pattern. The encryption decorator wraps a message store and the compression decorator wraps another message store, and you can essentially chain them in any combination. Now the architecture shows 6 patterns, each solving a distinct requirement. The decorator chain for storage, where encryption wraps compression which wraps a database store, operates independently from the state machine from message lifecycle. Each pattern is isolated and testable. A chat messaging system is a common object-oriented design interview question at companies like Meta and Slack. So having a practice pattern mapping for this domain will save you valuable time doing the actual interview that you spend on instead you can spend on other detailed design questions. So let us work through a third example. So this is a file storage service like Dropbox. So let's say the requirements given to you in an interview are, okay, number 1, you have to support uploading, downloading and deleting files. Then files they have to pass through processing pipeline covering virus scan, metadata extraction, thumbnail generation for images, and indexing for search. Then the processing steps vary by file type. So images get thumbnails, documents get text extraction, and videos get transcoding. Then the fourth requirement given to you is that, okay, the large files should be lazy loaded with metadata first and content only on demand. The fifth requirement given to you is that, okay, the system integrates with multiple cloud storage backends, including AWS S3, Google Cloud Storage, and Azure Blob Storage. And then the last requirement given to you is that, okay, all operations need to be logged for audit compliance. Now let's look at the first requirement to target. So essentially the processing pipeline with sequential steps. So the signal here is pipeline of checks. So that is pipeline of processing, virus scan, metadata extraction, thumbnail generation, and search indexing are run in a sequence. Each step processes the file and passes it to the next step. So that is chain of responsibility pattern. It is not strategy because multiple steps run in a sequence. With strategy pattern, you select one algorithm with chain of responsibility, multiple handlers execute in order. Now, the second requirement target is steps vary by file type. So images get thumbnail generation, documents get text extraction, videos get transcoding. The overall pipeline structure is the same: scan, then extract, then process, then index, but individual steps differ. Now, this maps to the template pattern if the sequence is fixed, or strategy if per individual step, if each step needs to be independently swappable. The choice depends on whether the pipeline order is rigid or configurable. Now, the third requirement target is lazy loaded file content. So the signal for this is, okay, expensive resource, you have to load on demand. So when browsing files, you would want to see the metadata immediately, like file name, size, upload date. But the actual file content, which could be hundreds of megabytes, should only be loaded when the user actually requests a download. And that maps to virtual proxy pattern. The proxy serves metadata immediately and fetches the actual content only on fast access. This is not decorator pattern because the concern here is access control, specifically when to load the content, not behavior addition. Now, fourth requirement to target is multiple cloud storage backends. AWS S3, Google Cloud Storage, and Azure Blob Storage each have different SDKs and different API signatures. Your system needs a signals consistent interface for storage operations. That mapped to adapter pattern. Each backend gets its own adapter that translates from your common file storage service interface to the specific SDK calls. Now the next requirement to target is audit logging for all operations. The signal to target here is that, okay, you have to add behavior without modifying the core class. So logging wraps the storage interface. You can add it, remove it, or stack it with other cross-cutting concerns independently. That maps to a decorator pattern. Essentially, a logging file storage decorator wraps whatever storage implementation is underneath and logs every operation. And here's the important insight. The core CRUD operations, which is upload, download, and delete, are just methods on the file storage server interface. They do not need a pattern. The adapter wraps the cloud backends behind this interface. So decorator adds actually logging on top. But the operations themselves are plain methods, wrapping simple method calls in command objects or strategy objects where there's only one algorithm would actually be over-engineering. So now after identifying which patterns you will be using, you have to explicitly state what requirements do not get a pattern. Saying a statement like, okay, upload and download are simple interface methods, so I do not need to add a pattern here because there's no extensibility requirement and there's no variation to manage. If you say that statement in an interview, that will essentially demonstrate the restraint that separates, just like a habit of applying patterns to pretty much every requirement, and then, applying patterns very selectively where they actually make sense. Let us talk about the most common anti-patterns for object-oriented design interviews. So number one is over-engineering. It occurs when a candidate essentially applies patterns, abstractions, or extensibility mechanisms that are not justified by the current requirement. So what this signals to the interviewer is that, okay, the candidate cannot distinguish between what might change someday and what the requirements actually demand. Now let me paint a picture of what over-engineering looks like. Essentially, a candidate is designing, let's say, a parking lot system. They create a vehicle factory even though there are only 3 vehicle types and a simple enum would work. They create a parking strategy factory that produces parking strategy objects even though there is only one strategy, which is to find the nearest spot. Then they create a spot observer that fires events when spots are taken even though there are no parts of the system that subscribe to those events. And let's say they create a spot state pattern for each spot. Even though spots are either available or occupied, and a boolean value field would be sufficient. So as you can see in this example, the candidate has applied 4 patterns and none justified by the actual requirements. The resulting design is harder to understand, harder to implement in the remaining interview time, and harder to maintain than a straightforward solution using enums, simple classes, and boolean fields. Now, over-engineering usually comes from one of the 3 places. The first is wanting to demonstrate pattern knowledge. Let's very commonly that, okay, a pattern candidate would think that, okay, if I show the interviewer that I know these patterns, I will score well. However, in practice, interviewers kind of penalize unjustified patterns. They do not reward them. So make sure you use the patterns, but you make sure they actually need it. The second is designing for hypothetical future requirements. Let's say, okay, if the candidate is thinking that, okay, what if we need multiple parking strategies in the future? The answer is that you have to design for today's requirements. If the interviewer wants to explore future extensibility, they will ask you. The third is textbook conditioning. So textbook essentially teach patterns in isolation. Each pattern is presented as a correct solution to the chapter's problem. Production code is different. Production code uses patterns selectively only when the complexity they add is justified by a real problem. So design with 2 well-justified patterns scores higher than a design with 6 unjustified patterns. Interviewers specifically watch for this. So less is more when each choice is deliberate. So if over-engineering is the problem, what is the solution? The solution is what's called as the minimum viable design principle, or MVD. So MVD states that, okay, you have to apply the fewest patterns and abstractions that satisfy the given requirements and make the design testable. You should add only more patterns when the interviewer explicitly asks for extensibility or when the requirement desires it. So essentially, the MVD process has 4 steps. First, you start with plain classes, simple constructors, and direct method calls. So no patterns, no interfaces, just the straightforward implementation. Second, you extract an interface only when there are, or the requirements explicitly state there will be multiple implementations. Third, you apply a pattern only when you can name the specific requirement it satisfies. If you cannot point to a requirement and say that, okay, this pattern solves a specific problem, you should not add that pattern. And fourth, if the interviewer asks you that, okay, what if we need to add X functionality, then you apply the pattern that enables that X functionality. This is the interviewer inviting you to demonstrate extensibility, and now the pattern is justified. Now let me show you how this works with, let's say, the parking lot example. For vehicle type, the MVD approach is an enum, so vehicle type with car, motorcycle, and truck. The over-engineered approach is a vehicle factory, a vehicle interface, and 3 implementation classes. For parking logic, the MVD approach is to find the nearest spot method directly, on the parking lot class, whereas the over-engineering approach actually, has a parking strategy interface with a single nearest spot strategy implementation. Similarly, for the third category for spot status, the MVD approach is a boolean field, which is occupied. The over-engineered approach will be something like, okay, is that a spot state interface with the occupied state and available state classes. And lastly, for notifications, the MVD approach will be that, okay, the requirement does not ask for notifications, so we just do not build them. Now, the MVD approach has roughly 4 classes. The over-engineered approach on the right side column has roughly 15 classes, solving problems that essentially do not exist in the requirements. Now, the MVD approach does not mean that, okay, we never use patterns. If the requirements explicitly state that, okay, let's say supporting multiple parking lot strategies or notify when a floor is full, as you can see, the corresponding patterns are absolutely justified. MVD means matching your design to the requirements, not minimizing patterns for their own sake. So a strong approach in an interview is to present your design and then say that, okay, the design satisfies the stated requirements with 2 patterns. If you would like to, me to add more extensibility for a specific scenario, I can show that with a specific pattern that would enable that. When you give that answer in the interviewer, that gives the interviewer the option to probe deeper while demonstrating that your initial design is intentionally minimal. That is the kind of judgment senior engineers exercise in production, and interviewers also reward it. So not all patterns are equally likely to appear in object-oriented design interviews. So that we know. So now knowing when to focus and where to focus your preparation will give you essentially the best ROI, which is like the best return on the study time. So the tier 1 patterns here are essentially tested in almost every object-oriented design interview. These are strategy pattern, observer pattern, factory method, and state. These are tier 1 because the signals that trigger them appear in nearly every object-oriented design question. So for example, multiple types, phrase, statement trigger strategy, event notification statements trigger observer, object, creation based on type triggers factory, and lifecycle behavior, statements, they trigger state pattern. So if you deeply understand these 4 patterns and can recognize these signals instantly, you will be essentially able to handle majority of the object-oriented design questions. Now, tier 2 patterns are also frequently tested, so I would say that roughly appears in 40 to 60% of the interviews. These are builder patterns, decorator pattern, command pattern, facade pattern, and chain responsibility pattern. They appear when the problem involves complex object construction, cross-cutting concerns like logging or metrics, undo-redo functionality, or multi-service coordination. Tier 2 patterns are the ones that differentiate essentially a hire from a strong hire because it solves secondary requirements that many candidates actually overlook. Tier 3 patterns are essentially occasionally tested, so these are adapter, proxy, template method, abstract factory. They appear in specific domains like legacy system integration, caching, data processing pipelines, or themed user interfaces. They are worth knowing, but essentially they appear very less frequently. And then tier 4 are essentially patterns that are rarely tested. So Singleton, Flyweight, Mediator, Memento, Visitor, and Bridge. These are essentially either too simple to test like Singleton or too niche to appear broadly like Visitor or effectively covered by other patterns in practice. So the practical takeaway is this. Spending 80% of your preparation time on tier 1 and tier 2 patterns gives you the highest coverage across companies and levels. If you have mastered tier 1 and tier 2, then investing time in tier 3 and tier 4 adds incremental value. But if your tier 1 pattern recognition is not yet instant, that is where your time is best spent. So now different companies and different interview levels essentially emphasize different aspects of object-oriented design. Knowing this will help you allocate preparation time based on your specific targets. So by company type, like e-commerce companies like Amazon and Shopify, they focus the object-oriented design interviews around order lifecycle, payment processing, and inventory management. The patterns they tested most frequently are state for order lifecycle, strategy for payment processing, observer for post-order notifications, facade for coordinating checkout services, and factory for creating order-related objects. Social media companies like Meta and LinkedIn, they focus on feed systems, notifications, and content moderation. The patterns they test most, are observer for feed updates and notifications, strategy for ranking algorithms and content policies, chain of responsibility for content moderation pipelines, and decorator for layering features onto content. Now, infrastructure companies like Google focus on data pipelines and storage systems and API design. They frequently test template method for pipeline processing, adapter for integrating with different backends, Proxy for caching and lazy loading, and chain responsibility for request processing. Ride-sharing companies like Uber and Lyft focus on dynamic pricing, driver-rider matching, and state machines. Strategy for pricing algorithms, state for rider lifecycle, observe state updates, and factory for creating ride-related objects are their most tested patterns. In fintech companies like Stripe and Square, they focus on payment workflows, fraud detection, and audit trails. State pattern for payment lifecycle, command pattern for transaction logging and reversal, chain responsibility pattern for fraud detection pipelines, and observer pattern for compliance notifications are the most common in their interviews. Now, if you look at the level, the expectations shift pretty significantly. At mid-level L4 or L5, interviewer is expected to correctly apply 2 or 3 patterns and demonstrate solid object-oriented programming and solid principle understanding. At senior, which is L5 and L6, they expect you to select patterns deliberately with trade-off justification, spot anti-patterns, and combine patterns effectively. At staff level and above, L7 and higher, they expect the minimal viable design, an explanation of why you would choose not to use certain patterns, and the ability to connect class-level design to system-level architecture concerns like scalability, team ownership, and deployment boundaries. Now at mid-level, showing the department that the patterns are there, that is pretty sufficient. At senior level and above, showing restraint and connecting class design to broader system concerns is what earns top ratings. So essentially, you have to calibrate your preparation to your target level. So a circular dependency occurs when class A depends on class B, and then class B depends on class A, either directly or through a chain. Circular dependencies create systems where you cannot understand, test, or deploy one class without the other. Now let me walk through the example. Let's say we have an order service with a dependency of billing service, and the order service place order method calls billing service.creates invoice a method. Then we have the billing service with a dependency on order service. Now the billing service process payment method calls order service.getOrder method to retrieve the order details. Now order service depends on billing service and billing service depends on order service. Essentially, you cannot instantiate either one without the other. You cannot test either one without the real or a mock instance of the other. And if these classes live in different modules or services, you have a deployment cycle. Neither can be deployed independently. Now there are 3 standard fixes for circular dependencies. Fix 1 is to extract a shared interface. Instead of billing service depending on order service directly, it depends on an order repository interface, an abstraction that provides order lookup without coupling to the full order service. The dependency arrow now points to the interface, not the concrete class, and the cycle is broken. Fix 2 is to introduce an event. So order service publishes an order placed event, billing service listens for it, neither class references the other. The observer pattern breaks the cycle by introducing an indirection through the events. Order service does not know billing service exists, and billing service does not call any method nor order service. Fix 3 is to extract a third class. So a new order billing coordinator class depends on both order service and billing service. It manages the interaction between them. Neither order service nor billing service depends on the other. Now each fix works in different contexts. So interaction interface extraction works well when the dependency is on a specific capability like a data lookup. Events work well when the dependency is on reacting to something that has happened. And a coordinator works well when there is a genuine bidirectional orchestration that needs to be managed. Now circular dependencies are a design smell that interviewers ask you to detect and resolve. And these 3 fixes cover the scenario that you will most likely encounter. Now premature abstraction is when you create interfaces, abstract classes, or pattern-based interaction before there is evidence that the abstraction is needed. It is the abstraction equivalent of premature or optimization. You add complexity now for a benefit that actually may never materialize. Now here's an example. A user repository interface with 2 methods, find by ID and save, and a Postgres user repository class that implements it. The interface exists, the implementation exists, but there's only one implementation. There is no in-memory user repository used in test, just Postgres, and there has been just Postgres for let's say last 5 years. Now the cost of this unnecessary interface is pretty real. Every developer who navigates the code base jumps from the interface to find the implementation. Every refactoring tool that renames a method must update both the interface and the implementation. The interface adds a layer of interaction with zero current benefit. So now, when is just abstraction actually justified? There are four scenarios. First, when there are currently two or more implementations, that is strategy, factory, the patterns, where multiple implementations are the whole point. Second, when the requirement explicitly states that the component will be swapped. If the spec says that, okay, we need to support both Postgres and DynamoDB, okay, the interface is justified by a stated requirement. Third, when the abstraction enables testability that would otherwise be impossible. If you need to mock an external service in a unit test, the interface enables that. Fourth, when multiple consumers depend on the contract and the interface stabilizes the API across those concerns. And then, when is abstraction premature? When there is a single implementation with no concrete plan for a second, when the interface mirrors the implementation exactly with no behavioral contract beyond what the implementation provides, when the abstraction is added for flexibility without any specific flexibility requirement, when adding the abstraction makes the code base harder to navigate by the new team members. So the practical guideline is this: you should wait until you need the abstraction and then you add it. Extracting an interface from an existing class takes about 30 seconds with the modern IDE tooling. There is no penalty for adding it when the second implementation actually arrives, but there is a real ongoing cost to maintaining an unnecessary layer of interaction. Now, in an object-oriented design interview, you should not add interface for every class. You should add them where the requirements demand multiple implementations or where dependency inversion is needed for testability. The interviewer will actually recognize the restraint as a sign of practical judgment.